Welcome to this section. Let's start by talking a little bit about object-oriented programming, what it is, and why it is important. First of all, you need to know that object-oriented programming is a programming paradigm that organizes software design around objects. Objects will be the main elements of this programming paradigm, so that is why it is called object-oriented. And you may ask, what is a programming paradigm? Well, let's see. A programming paradigm is just an approach that we use to solve problems with our code. It is basically a style or a way of programming, a way of analyzing the problem and writing our solution in our code. Object-oriented programming is one of those paradigms, but there are many other programming paradigms, including imperative programming, functional programming, declarative programming, logic programming, and so on. Imperative programming is what we typically use when we start learning how to code, when we write each line of code as a command telling the program what we want to do. Now we will go from the imperative programming paradigm that I'm sure you must have used in the past to object-oriented programming, where we will structure our code in a way that will be based on messages that are sent to objects that we define in our code that we create. Instead of writing the commands line by line, we will structure our code in a way that will be centered around objects. These objects will exchange messages, and they will respond to the messages by performing actions. They will also have their own state or set of attributes. So we have behavior and we have state. We will basically have to write something that works like a blueprint. That is called a class. Remember that term because that will be very important in the next section. Class. Classes work like blueprints that we can use to create objects. We can use the blueprint as many times as we need to, because in our code, we'll be able to generate copies of the object based on the blueprint that we define. Each object will have its own state and behavior, the set of actions that it can perform. The objects will interact in the program in such a way that will let us perform more complex functionality and achieve exactly what we need with our program. You can think of them as Legos that we can combine to create more complex functionality or structures. A very important thing that you have to know is that programming paradigms are not mutually exclusive. They are not mutually exclusive, so you can actually combine them in the same program. The same program can have multiple programming paradigms. Okay? We can use, for example, object-oriented programming and imperative programming in the same program. And we will do this during the course. You will learn object-oriented programming, but we will also combine the objects that we create with programs like the ones that we traditionally write, with lines of code that indicate commands or actions that the program has to take. Now, please take a moment to think about the possible advantages of object-oriented programming, based on what you just learned. Why do you think that structuring your code this way could be helpful? Think about this and then move on to the next video, where you will learn about the advantages of object-oriented programming. Great! So now let's start diving into the advantages of object-oriented programming, why it is helpful, and why we should use it in our programs. The three main advantages of object-oriented programming are modularity, extensibility, and reusability. Let's start by talking about modularity. In object-oriented programming, we define certain elements called classes that serve as blueprints. These blueprints work like modules because they are sort of isolated, or as isolated as possible from the outside world. This means that they are mostly independent from each other and from other parts of the program. So that is a great advantage because any changes can be made easily to only that specific part of the code without affecting the overall program. We can define as many blueprints as needed for the program, and we can use them to create their corresponding objects. These blueprints will interact with each other, the objects will interact with each other in the program, but they will still be mostly independent from each other. They will be like Legos. They are separate and independent pieces, but we can combine them to create more elaborate structures and functionality. There is also separation of duties or separation of concerns, because each blueprint represents an object that has a particular purpose in the program. The second advantage of object-oriented programming is reusability. Objects can be reused within the program and in future projects. This is really awesome, because if we wrote certain blueprints or classes for a project, and these blueprints were independent from each other, we can select the ones that we need for a future project and reuse their code. This leads to faster development and lower cost of development because we save all the resources and the time that it would take to write this code again. A third advantage of object-oriented programming is extensibility. Objects can be extended to include new attributes and behaviors. So the blueprints that we write don't necessarily have to stay fixed. We can add new attributes and behavior and extend their functionality. In these blueprints, we define the state and the behavior of the objects. So if we modify the blueprint, we modify the objects that will be created from the blueprint. And that is awesome. We can add new functionality very easily. These three advantages lead to the fourth advantage, that object-oriented programming makes your code easier to maintain. Since the design is modular, we can make changes to the modules without making large-scale changes. For example, if we have these blueprints, and we change only this one, the other ones and the other parts of the program should not be greatly affected, and we shouldn't have to make any large-scale changes, since they are mostly independent from each other. These advantages result in higher quality software, because more time and resources can be used to test the software. And we can also find and fix bugs more easily. Why? Because blueprints define the state and the behavior of the objects. These elements, the blueprints, the classes, have their own individual components that define the behavior and the attributes of the objects, just like pieces of a puzzle that work together. All of these pieces define what an object can do and what an object has. So, we can test the individual components to make sure that the class works correctly. And if we find a bug in one of the objects in the program, then we know where to go. We need to fix the blueprint that created the object, and that will fix the bug for all the objects created from the class. So we can fix it easily. Therefore, always remember that these are the three main advantages of object-oriented programming: modularity, extensibility, and reusability. You will see examples of these advantages during the course when we start writing the code and working with the examples. Overall, they result in improved software development productivity. Take a moment to analyze how these advantages can impact large projects compared to the traditional imperative approach. Think about how object-oriented programming can be helpful in this case. And I'll see you in the next video. Hello and welcome to this section. Now we will start talking about classes and how they help us define the objects that we will create in our program. The concept of a class is essential in object-oriented programming. Let's see why. A class is a blueprint that we define in our code for creating objects. It is an essential building block of any program written with object-oriented programming. So we can say that a class is like a blueprint that we write in our code to define the attributes or characteristics of an object and its behavior. This is the visual representation that we will use throughout the course to refer to a class. You will also see other images of blueprints, but whenever you see a blueprint, know that we are referring to a class that is used to create this particular type of object. In a class, we define the state and the behavior of the objects that will be created. Right here, we have our representation, our visual representation of an object created from a class. In our program, we can define classes to represent basically anything that we need to represent in our program or system. For example, a machine, a patient, a client, a dog. A data structure, a student, a player, even a game board. If you are developing a game, you can represent the player as well. You can represent more abstract concepts like a data structure. And actually, we will implement this as the final project of the course. You will implement a fully functional data structure called a linked list. So you can see that this programming paradigm is extremely powerful. But to actually write this representation in our code, first we have to analyze the characteristics of the object that we are going to represent. After this initial analysis, we can actually start writing the blueprint, the class, in our Python code. This is the basic process that we have to follow. First, we identify an object that is relevant to our system. Then we analyze its attributes and behaviors, and then we actually go to our code to start writing the class. After we have our blueprint defined, in the code we can use it as many times as we need to create as many objects as we need to. So this blueprint is reusable. We define it once and we can use it as many times as we need to. From the class, we are going to have code that will work as a factory, because we can use the blueprint to create as many objects as needed, just like we can use the same blueprint to build multiple houses. Let's say, for example, that we're creating a system where we have to represent a backpack. We write the class or the blueprint that represents a backpack with a list of items that it contains, and we can use that blueprint to create as many backpack objects in the system as needed. That is the power of object-oriented programming. We write it once, and then we reuse it as many times as needed. The key takeaway from this lecture is that you are in charge of designing the class. You have to analyze the object and decide which attributes and behaviors of that object are relevant to the system. In the class, we define the state of an object and its behavior. These are the two main elements that we have to represent. Now, think about this for a moment. Think about the objects that are currently surrounding you as you watch the video. How can you represent them as classes? Make a mental list of their attributes and their behaviors, and what might be relevant to represent in a system. Think about this for a moment, and then go to the next video, so you can learn more about how to identify classes and how to start writing them in Python. Now that you know what classes are and why they are relevant, let's have a quick overview of how you can identify classes that could be relevant to your program. You learned that the process of actually writing a class starts by analyzing the characteristics of an object. This object can be either physical or more abstract, like for example, a data structure. What they all have in common or share is that they have their own characteristics and actions that you can perform with those objects. But before we actually identify the characteristics of an object, we have to identify the objects themselves. We start with an initial description of the problem, and from that description we have to identify the objects that will be relevant for our program or system. Usually, you will have a problem description that you develop or write after talking to the person or client that is interested in creating a system or program. Or perhaps you might make the problem description yourself from your own description of the problem. You will write down a written description of all the elements of the problem in your own words, and then you will have to extract the elements that are relevant to the system or program. This is what we usually call a problem statement. It is an initial description of the problem that we're trying to solve with our code. Usually, we can identify the relevant classes by listing the nouns that we find in this problem description. Let's see our first example. Think about the potential classes that you might need to define for a fast food shop system. This fast food shop serves pizza, burgers, and hot dogs. Right here we have our initial problem statement. Our store serves fast food. The items sold include pizza, burgers, and hot dogs. We also sell soda, water, and French fries. Clients may choose to buy one or more items. If they choose to buy more than one item, then they receive a special discount of 20%. The store has 5 employees. As you can see, this is just an initial description, but this is very helpful to practice how to identify potential classes. Try to identify the nouns in this problem statement and which ones can be relevant for the program. Some of them might not be as relevant as they might seem initially, but that is part of the analysis. First, you have to identify potential classes and then discard the ones that are not relevant to your problem scope. Pause the video, identify the potential classes, and then come back. Welcome back. These are the relevant nouns for the program. We have food, pizza, burgers, hot dogs, soda, water, French fries, clients, and employees. The relevant nouns really depend on the scope of the project that you are trying to build. For example, if you're trying to create a system for the items that are sold at the store, then these would be the relevant nouns: pizza, burgers, hot dogs, soda, water, and French fries. But if you also want to keep track of the clients and employees, these would also be relevant nouns. After this initial analysis, we might conclude that, for example, the term food is too general or that is not as helpful as representing these specific items in our system, so we might discard it. This is an example of what you can conclude after this initial analysis. You are sort of like refining your initial analysis or prototype. Right here we have a summary of the relevant classes that we identified in the problem description: pizza, burger, water, hot dog, soda, client, French fries, and employee. Some of the questions that you might want to ask yourself when you are identifying these relevant classes are: is the term that you selected needed for the scope of the project? For example, if you're not keeping track of clients or employees, then that would not be a term that you would actually need for the project. Does the term represent an example of a class? Then you might ask, is this class important for the program that we are creating? I think this is one of the most important questions. Is the class important? Do we have to use it in the program? Awesome. So now let's see another example. This time we have an electronics store. Right here we have the problem statement. We see our electronics store sells laptops, desktops, tablets, smartphones, notebooks, pen drives, and headphones. We also sell accessories for these devices. The store has 10 employees and 1 manager. Clients are registered when they make the first purchase. Take a moment to analyze this statement and identify the relevant nouns that could be classes in our program. Pause the video for a moment, think about this, and then come back. Welcome back. Right here we have the relevant classes. We see laptops, desktops, tablets, smartphones, notebooks, pen drives, headphones. Accessories could also be a relevant class: employees, manager, clients, and purchase. These are all examples of relevant classes for our system, depending on the scope, of course. Remember that right here we're just extracting the nouns. But after this initial analysis, we might decide that some of them are not actually needed. Right here, we're not counting store as a noun because this is like too general. If we decide in a subsequent analysis that we might need to represent this, we could also add it. Right here, we see the relevant classes: laptop, desktop, tablet, notebook, headphone, client, smartphone, and employee. Awesome. Great work so far. Right here, let's go to our third example, so you can practice identifying these nouns a little bit more. Try to think about the potential classes that you will need for a simple game. A simple video game where you have a player and you have enemies. This is our problem statement. We see our maze game will have 5 levels. The player will move to each level once it reaches the goal. There are 2 types of enemies: ants and toads. If the player collides with either one of them, the level starts again, until the player has no more lives left. Take a moment to read this problem statement again and identify the relevant classes. Think about this, pause the video, and then come back. Welcome back. In this case, the relevant nouns could be maze, game, levels, player, goal, enemies, ants, and toads. We could also include lives as well if we need to add a life counter. But after this, you might determine that this is actually an attribute of the player. The player has a particular number of lives. So this would actually not be a very helpful class in our system. Just by defining player, we could add a lives counter. Okay? Here we have a summary of the classes that we identified: maze, game, level, player, enemy, ant, toad, life, and goal. After our initial analysis, we might determine that we don't need all of these classes. We only need these ones right here: game, player, enemy, and goal. This is just an example of how you might refine your initial analysis of the potential classes after you actually analyze how you're going to implement the game. So these are examples of the kind of process that you will have to perform to identify the classes that you will need for your program. It all starts with an initial analysis of the problem statement. Awesome, now you know how to identify classes and why they are important. So we will start diving into the actual Python syntax in the coming video. Great work so far. Now you will start learning how you can actually start writing a class in Python. A class has two main parts: a header and a body. Just like functions, we have the first line of the function and the content of the function. In classes, we have a header and a body as well. Right now, you will learn how to write the header of the class, which is the very first line in the class definition. And what is a class definition? Well, a class definition is the actual implementation of a class in a programming language. In this case, we are implementing it in Python. Particularly, the class header is the first line of a class definition. This line specifies the name of the class. We explicitly write the name of the class, and we also specify if the class inherits from another class. You will learn more about this in a future section of the course about inheritance, because this is a little bit more advanced and you need to learn the basic concepts first. But for now, let's focus on this part right here, the name of the class, and how we can write this initial line, the class header. This is the most basic syntax of the class header. First, we find the class keyword. You will see it highlighted in a different color if you are using a code editor with syntax highlighting. Right here, you can see it in blue. And then we find right here the name of the class. I am using right here like angle brackets to specify that this is the description of the element. Right here, we will just have the name of the class without the angle brackets. We write the name of the class just like we write, for example, the name of a function. We assign a particular name for the class so we can use it in our program. And after the name of the class, we find a colon, which is very important because if you don't include the colon at the end of the header, you will get a syntax error when the program runs. Great, so let's see an example where we are going to write the first line of a class. We will be working with this class throughout the course. If we go to PyCharm, to our Python OP project, and to our main file, we can start actually defining our class. In this case, we are going to define the header of a backpack class. This is a class that we will be working with throughout the course as you learn the different elements of the class. So let's start writing it. We can zoom in and we start by writing the class keyword right here. After this, we need to write the name of the class, which is backpack, right here. Notice that I'm writing this with an uppercase letter. This is a convention in Python. Class names should start with an uppercase letter, and each one of the words in the name, if it has more than one word, should be capitalized. It should start with an uppercase letter as well. This naming convention is called Pascal case, or upper camel case. You will learn more about this naming convention in the coming article after this video. But for now, we just define the name of the class with an uppercase letter, and at the end of the header, we have to add a colon. You can see that the error that was right here, if we remove the colon, disappears. If we don't include the colon, we will get a syntax error. And after that, what can we do? Well, we see an error right here because the class body, the body of the class, cannot be empty. So how can we fill that? Well, we have a particular statement in Python called pass. This is a statement that we can use to fill the body of an empty element. We have to write something in the body of the class. But since right now we are only writing this line, we can add this as a placeholder. We say this is empty right now, but at some point it will be filled with some code. If we save the file and we run our code, we see nothing as the output, which is exactly what we expected. Notice that if we remove the colon right here, we see the error, and if we run the code, we get this error. Syntax error, invalid syntax. And right here we see something like an arrow that is pointing to the place where the colon should be located. Right here. This solves the problem. Awesome, so now you know how to define the class header. Great work! We had our first practical example, and now you know how to write the class header. So let's learn more about the body of the class. The class body contains the elements of the blueprint, the elements of the class. This is where we define the attributes and the behavior of the objects. So we're basically writing a description in the blueprint of what we want the objects to be like and what they should be able to do. These are the main elements that you will find in a class body. Some classes may have all of these elements, and some classes may only have some of these elements. First, we find the class attributes. Then we find init, and finally we find the methods. We will cover init. You will learn more about this in detail in a coming section, because this is very important to define the characteristics or attributes of the objects when they are created. And the methods right here define the actions that the objects can perform. Right here we have a visual summary of the basic structure of a class. We have the class header, which you already know how to write. This will be replaced by the name of the class. And right here we see the different elements of the body. We see the class attributes, init, and the methods. Notice that all of these elements are indented, and this is very, very important. For the elements to be part of the class, they have to be indented. Just like we indent the body of a function, we have to indent the body of the class. In this case, they are represented as comments, but they will be elements in our code, and they will be part of the class. During the course, you will learn how each one of these elements works in detail, and you will also learn how to implement them in your classes. Great work so far! Right here we have another example to help you practice how to identify the classes that you might need to implement in a program. This time, let's say that you're meeting with a client that is asking you to create a program for an animal shelter. This is part of the problem statement right here. Our shelter takes care of dogs, cats, parrots, lizards, and snakes. 6 employees work for the shelter and volunteers help the staff. The shelter regularly receives donations, and the donors are registered in the system. Think about this for a moment. Try to identify the relevant nouns for the system, and then come back. Pause the video. Right here, you can see the relevant nouns for this system. Dogs, cats, parrots, lizards, and snakes are the animals in the shelter, and then we have these nouns: employees, shelter, volunteers, donations, and donors. Remember that if a noun is relevant or not for a particular problem depends on the scope of the project that you're working on and the type of program or system that you're trying to build. But right now, we are just identifying all the nouns that could be relevant for the system. We have basically 2 categories of nouns. We have animals and we have people. Animals include dogs, cats, parrots, lizards, and snakes. And people include employees, volunteers, and donors. We also have donations, which could be represented in the system. Right here, we can see a visual summary of these classes. Right here. When you translate these terms from the terms that you find in the problem description to the actual names of the classes, you need to remember that classes are usually written in singular form. So if you find them like this in the problem description in plural, when you write the actual name of the class, you have to write it in singular, because you are representing a dog, a cat, a parrot, a snake, or a lizard. You're not representing the plural form of these elements. After you identified the classes that you need to create, then you would actually start implementing the classes and creating the blueprints to create the objects. You will learn how to write the body of the classes during the course. For now, we're just identifying the classes and determining if they are important. The same guidelines apply to people. We have 3 potential classes right here: employees, volunteers, and donors. And when we translate that into potential class names, we see them in singular form: employee, volunteer, and donor. And then we would have to start writing the code and the blueprints that we will use to create the objects in the program. This is a simplified version of the initial analysis that you will have to make in object-oriented programming, identifying the relevant objects for the program or system from the problem description, their characteristics, and then start writing the code. Now think about how you would write the class headers for all of these classes that we discussed for the pet shelter system. This will be great practice to help you solidify your knowledge of how to write the class header and how to assign proper class names. You can fill the body of the classes with the pass statement so that you can run your code without any errors and confirm that the header was written correctly. Welcome to this section. Now you will learn how you can use these blueprints to create objects, also called instances. We said that classes work like blueprints and that we can use them to create objects. In this section, you will learn how to actually define the attributes of an object in the class and how to create an object or instance in the program, just like the workers build a house from a blueprint. Basically, you're going to learn how to put this machine to work. We're using the blueprint to create the actual objects that we can work with in a program. First of all, what is an instance? An instance is just an object created from the class. You may find that these 2 terms are often used interchangeably, object and instance. Instance usually tends to be more theoretical, and it refers to a particular example of a class or of a theoretical definition. An object is usually used to refer to something more concrete, the actual object that is stored in memory. Let's see the relationship between classes and instances. A class is like a more abstract representation of an object. Like a blueprint, it describes what any object of a particular type should be like and behave like. For example, when we create a class to represent a backpack, this blueprint represents, in general, the attributes and actions of any backpack. However, instances are more concrete. They are the concrete individual objects that we will create from the class or from the blueprint. We take something that is more abstract and represents the objects in a general way, and we use our code to create concrete instances of the class with their own attributes and behaviors that we can use in our code. In this case, if we have a backpack blueprint, we would create backpack instances or objects in our code. Instances have attributes, and these attributes are called instance attributes. They are the attributes of an object. They are variables that belong to a particular object. So, a backpack may have, for example, a size, a color, a weight, a material, number of pockets, number of zippers, or even a list of items that it contains. These can all be instance attributes, and they describe the characteristics of the backpack and what it contains. Similarly, a player, for example in a video game, may have an associated sprite, a score, a number of lives, speed, and X and Y coordinates to determine its location on the screen. These are all examples of possible instance attributes that we may assign to the player object in our program. We would define these attributes in the player class in that blueprint that we will use to create player objects. A very important thing that you must know is that instance attributes are independent. They belong to the object. Classes are used to define the attributes, like a blueprint, but the attributes can have unique values for each instance. This is very important. They can have unique values for each instance. So, if we have multiple instances of, for example, the backpack class, we may find that a particular instance is small. It is red, it weighs 3 kilograms, it is made of leather, and it has 5 pockets. While another instance may be medium, green. It weighs 5 kilograms, it is made of fabric, and it has 2 pockets. While the instances do not share the same characteristics necessarily, they do share the same attributes that were defined in the blueprint. They all have a size, they all have a color, they all have a weight, a material, and number of pockets. They have all of these characteristics or attributes, but the values of those attributes can be different. Here we have another example with the player class. All the instances of the player class have the same set of attributes that we define in that blueprint in the class. For example, they may have a sprite, a score, number of lives, speed, and x and y coordinates. But their values will not necessarily be the same. They are independent from other instances. So, for example, if we change the score of this particular instance or object in our code, the other instances will not be affected. And that is what makes instance attributes so powerful. We define what attributes all objects will have, but their values can be different and they are completely independent from each other. Great! Now you know why instances are so important. Think about why it is important for instance attributes to be independent. Think about this for a moment, and when you're ready, go to the next video. I will see you there. Let's see how you can define instance attributes in Python with the init method. Now we will start diving into the actual elements of the body of the class, so you can start writing the code to define the blueprint and create objects. For this example, we will represent a house in our code. So let's start by writing the class header like you learned in the previous section. Let's write the class header. First of all, we write the class keyword and then we write the name of the class. In this case, it's going to be the house class. And since we cannot have an empty class body, we just write the pass statement to use it as a placeholder and indicate that we will write something right here at some point. Okay, if we run the code, then we don't see any output, which is exactly what we needed. We don't get an error because the header was defined correctly. Now we have to write the init method. We have to define this method in our class. And what is this method? Well, this is a special method that is used to define the initial state of an object. It is called automatically when an instance is created. When you create an object in your code, this method is called automatically. Just like when you call a function, this method is called automatically to initialize the values of the attributes of the instance that is being created. In this case, we will define a price attribute for the house instances. So each house that we create can have its price attribute with its own unique and independent value. Let's do this in our code. We have the header of the house class, and right here, now we're going to start writing the body of the class. For that, we will just delete the pass statement, and we will start writing the init method. And how can we do that? Well, we just write the def keyword first to indicate that this will be a method. This keyword has to be indented to be part of the class, okay? One level of indentation. That would be 4 spaces, 1, 2, 3, 4, or 1 tab, but it is recommended to use spaces. Okay, after the def keyword, what we have to do is to write this right here. PyCharm already suggests what method we can define right here, init. You can see that it has 2 leading and 2 trailing underscores, and in the middle we see the word init, and by default we have a self parameter. Init always has to take self as the first parameter, so we have to include it as the first parameter. You will see why and the meaning of self in a coming video, but basically we use it to refer to the instance or the object that is being created. Since we want to customize the price of the house, we will also need to take the price as an argument. We have to specify the price of the object or the instance that we are creating, so we add it right here as a parameter. After that, we have to start writing the body of this method right here. A method is just like a function. This is like a function that is called immediately and automatically when we create a house object. So what's going to happen? Well, we are going to create or assign a price instance attribute to the instance. This is what we are doing right here. Let me complete this line so we can analyze it. We say, take the price as an argument and use that value that we passed as argument, assign it to the price attribute of the instance. This is basically what we are doing right here with this line. Self refers to the instance, so we are saying, take the instance that is currently being created, add a price attribute to that instance, and then assign the value of price right here. This is a parameter and this is an attribute. They are different, okay? Now let's continue working on our backpack class. I told you that we will be working with this class during the course, so let's see how we can define an items instance attribute for this class. Every backpack has a particular list of items that it contains, so that should be an instance attribute for a class. Try to implement this in your code, define an items instance attribute. Pause the video, and then come back so we can start writing the code. Okay, so now we're going to create or define a backpack class in our code. First of all, we write the class header. We say class backpack and a colon. After that, we click enter and we will immediately have indented code in PyCharm. We start by defining the init method because we need to define an items instance attribute in that method. So all the instances that we create of the backpack class can have an items attribute. So what are we going to do right here? We have self. Self always has to be the first parameter in init, okay, in this list within parentheses. But in this case, we don't want to take any arguments when we create the backpack class. We don't need to customize any of the values for the instance, so we will just have self in this list. And what are we going to do? Well, we are going to assign or create an items instance attribute for the instance that is being created. Okay? And the initial value of that attribute will just be an empty list. This is representing the fact that when we just create a backpack in the real world, it is empty. And it is only filled with items when we choose to put items in the backpack. Initially, all backpacks are empty. So we are creating an items attribute for the instance that is being created, and initially that attribute will be the same for all instances, an empty list. Great work so far. Now you know how to define the init method in a class. You know how to write the class header and how to define this method. Remember that self should always be the first parameter in the init method, and that you can add as many parameters as you need in this list if you want to customize any of the values of these attributes when you create an instance. You use self, the name of the attribute, and then the value that you want to assign. Now you will learn more about a very important word that we use in object-oriented programming, and that is self. Self right here. I know that you must be curious to know why we added this word when we defined the house class and the backpack class in our previous examples. What is the purpose of this word in the method or in the class? Well, classes define the state and the behavior of the objects in sort of like a generic way, in a way that applies to all the objects of the class. They are general. The code that we write in a class is not specific. The code in the class has to work for any instance of the class. So, what is the purpose of self? Well, self is just a generic way of referring to the current instance of the class. The instance that is being created in the case of init, or the instance that is sort of like calling or executing an action in the case of methods. Let's see what we can learn about self in the documentation. If we go right here to PEP 8, the style guide for Python code, we can go to the section where it says naming conventions and then click on function and method arguments. If we click right here, we will be taken directly to the part where it mentions self. And we see that we should always use self for the first argument to instance methods, okay? Init is an instance method, and we should use self as the first argument. So as you can see, classes are like general blueprints that apply to any object of the class that we create. But when we use self, we actually refer to concrete objects or instances of the class. It is a way to refer in general to the object that is calling a method or being created. Like in this example. In this example, we use self to refer to the instance that is being created. Remember that init is called automatically when we create an instance. When the instance is created, self is automatically assigned a particular value, the instance that is being created. So when we write self.price, this is what it basically says. Assign the value of the variable price to the instance attribute price of the instance that is being created. That is what self represents, the instance that is being created. That is the purpose of this line. It's very important to know that these two elements are not equal. They are completely independent. This is the parameter that we defined in the init method. It is like any other parameter, like the parameters that we define in any regular function that we write. And this right here is the attribute of the instance, okay? This is the actual name of the attribute that we are creating. And this is the value that we are assigning to that attribute. For example, we could just assign a fixed value to the attribute, so all instances can have the same initial value. This is just to show you that these two elements are completely independent. Great! Before we start diving into our example, think about the purpose of self in the backpack class. Try to add new attributes to the init method, so you can experiment working with self in the class. Pause the video for a moment, try this, and then come back, so we can start writing the code. To help you practice using the concept of self, let's add a few more instance attributes to our backpack class in the init method. Let's say that now we want our backpacks to have a color and a size. Okay? Items will still be an empty list initially, so we don't have to add this to the list of parameters. We don't want to customize this when we create an instance. All the backpacks will have the same initial value for that attribute. So if we want to create a new color attribute for the instance that is being created, we just write self.color and we assign the value of this parameter that we have right here. It is gray because it has not been used. You can see it right here. Parameter color value is not used. So if we write it right here, it will turn black because right now we are using that value, that parameter. Now we have our color instance attribute. So let's also define the size attribute for the backpack. We use the same syntax, self, dot, and the name of the attribute, which is size in this case. And now we have our backpack class with 3 instance attributes for each backpack instance that we will create. Each backpack object will have an empty list of items. Initially, we'll have a color and a size. When we create the backpack, we will have to specify the color and the size because we are adding them right here as parameters for the init method. So now you know how to define instance attributes and how to work with init. Great work so far. When you're ready, go to the next video and I'll see you there. Now let's see how you can define instance attributes in a circle class, a rectangle class, and a movie class. We will define the init method for each one of those classes. Take a moment to think about how you would define the instance attribute in the circle class. Let's say that we want to define a circle class with a radius instance attribute. This attribute should be customized when you create an instance. Think about this for a moment, try to implement this in your code, and then come back. Welcome back. To write the circle class, we just have to start by writing the class header. We write the keyword class followed by the name of the class, which is circle. After that, we have to define the init method. We write double leading and double trailing underscores surrounding the word init, and we add self as the first parameter. After that, we just add a second parameter called radius, because we want to customize the radius of the circle. To create the radius instance attribute, we just have to write this instance attribute like this and assign it the value of the parameter. Right here we are saying, take the instance that is currently being created, add a radius instance attribute, and assign the value that we pass to this parameter. That will be executed automatically when we create a circle instance. And we can add as many attributes as we need. In this method, for example, we could add a color attribute and like this assign the value of color. Or we could also omit this parameter and assign an initial color for all circle instances. Let's say that we want all the circles that we create to be blue initially. So we can just assign this string as a value for the color attribute, and all instances will have this same value when they are created. Of course, we can modify this later, but initially they will have the same value. Great, so now let's go to our rectangle example. For a rectangle class, we have to first, of course, write the class header. We write class followed by the name of the class, rectangle. And we define the init method right here. For the rectangle, we will have to specify 2 arguments because we need to know the length of the rectangle and the width. Okay? After that, we can just define the instance attributes. Self.length, the length attribute, and we assign the length, the value of the length that was passed as argument. And then self.width, and we assign the width that was passed as argument. Right here. So now, when we create a rectangle instance in our program, each one of them will have a length and a width that we will specify as arguments. You will learn how to create instances in this section. But for now, we're just defining this in the blueprint. Awesome! Let's go to our third and final example, a movie class. For a movie class, right here, we will have to start with the class header, class and then movie. We start by defining the init method. Always remember that you have to write double leading and double trailing underscores for this particular method. Let's say that we want to add multiple parameters to this method because we want to be able to specify the title of the movie, the year when it was made, the language, the original language, and the rating of that movie. What are we going to do with these values? Well, we are going to create their corresponding instance attributes. Each movie instance will have a title attribute. It will also have a year attribute, and it will also have a language attribute and a rating. So we're defining in our blueprint what all movie instances will have. Each instance represented by self will have a title, a year, a language, and a rating instance attribute. And these values will be customized when we create the instance because we are assigning them right here to the list of parameters. Awesome! We've worked through 3 examples of classes and how you can define the init method. So now you know how to define instance attributes in this method, which is called automatically when you create an instance. Now let's see how you can create instances in Python. If you have a blueprint or a class that you've already defined in your code, then you will want to use that code to create objects that you can work with in your program. In that case, you will just have to use this particular syntax. So the creation will start behind the scenes, and Python will handle this process automatically by calling the init method and creating all the necessary elements of the object behind the scenes. It is important to know that self is sort of like skipped in the arguments list when we create an instance. You just have to assume that self already has a value because it does have a value and it is assigned behind the scenes when you try to create an instance. But you don't have to count it as an argument for the arguments list. You don't have to pass a value for that parameter. You will see what I mean in just a moment when we start diving into the examples. First, let's see the syntax that you need to use when you want to create an instance for a class that doesn't take any arguments in the init method. This is the syntax. First, we write the class name, the name of the class, and then we write empty parentheses. We can also assign this object, the resulting object, to a variable, and that is what we typically do to be able to work with that object in our program. Let's see an example in our code. In this case, we're going to start by defining our backpack class. We're going to do this real quick, and we're going to have our init method with self as the parameter. We're also going to define the items instance attribute, which will be an empty list initially. Once we have our class defined in the program, we can go back to writing our main program, because classes work like building blocks. They are part of the main program, but we can still write other lines in our file, like this, if we don't indent the code. In that case, the code is not considered part of the class. Okay? What are we going to do? We are going to create an instance of backpack, and we are going to assign it to a variable. We're going to say my backpack is going to store a backpack object. We write the name of the class right here, and we have to analyze the init method. The init method only has self as the parameter, but remember that self has to be skipped when we pass the arguments. So actually we don't have to pass any arguments, like this. And we write an empty pair of parentheses. It is recommended to add 2 lines between a class definition and the rest of your code. So we will do that to follow the Python style guide. We are creating a backpack instance and we are assigning it to this variable. So let's see what we get if we try to print the backpack instance. Okay, let's save the file and run the code. If we zoom in right here, we can see that this is the output when we try to print the backpack instance. Let's see what it says. It says main.backpack object. Right here, we can see the type or the data type of the object. It is a backpack object, which is correct. And right here, we have its memory location, where the object is located in our computer's memory. And we've confirmed that right here, we have an instance of the backpack class. Awesome. Great work. Now you know how to create instances when you don't need to pass any arguments. Now, if we need to create an instance from a class that does take 1 argument, in addition to self, of course, in the init method, then we just need to pass that argument or that value within parentheses. We write the class name, the name of the class, and within parentheses, instead of writing a pair of empty parentheses, we just write a value. The value that corresponds to that parameter. Let's see an example in our code. Now let's define the circle class. We write the keyword class followed by the name of the class circle, and we're going to define the init method right here. This class is going to take 1 argument. This argument will be the radius of the circle. Right here we define it as a parameter for the method and we create a radius instance attribute for the circle. How are we going to create a circle instance now? Well, we have to assign it to a variable. This is what we commonly do so we can continue working with the object in our program. We assign it to a variable. And then we write the name of the class right here. Within parentheses, now we have to specify the value for this parameter. Previously, we just used empty parentheses. But now you can see that right here we have this like a sort of yellow warning. That says, if we click right here, it says that parameter radius is unfilled. Right here on this line. Why? Because we have to pass a value or an argument for this parameter. Let's say that we want to specify that the circle has a radius of 5. So we can do exactly that by passing the argument right here that corresponds to this parameter. Awesome! Now the warning is gone and we can create our circle instance correctly. Let's print the instance to confirm that it was successfully created. We run the code and we see this right here. We have a circle object at this particular memory location. But it is a circle object, so we confirm that this contains an object of the circle class that we've created. Awesome, now you know how to create instances when 1 argument is required in the init method. Finally, we might also need to pass multiple arguments if there are more parameters defined in the init method. And in that case, we just have to pass the necessary arguments. We write the name of the class, and within parentheses the list of arguments. The arguments have to be separated by a comma, and it is recommended to add a space after each comma to make the code cleaner and more readable. Let's see an example. Now we will define our rectangle class. Let's do this real quick right here because we have to focus on this part. Right now we're going to add two parameters, length and width, and we're going to assign them as instance attributes, like this. After that, we can go back to writing our main program, and using this class, we say, my rectangle, you can assign any valid variable name to this variable right here. I am just calling it my rectangle for simplicity purposes. After that, if we want to create an instance of the rectangle class, we now see that we have a yellow warning, like before, when we had to pass one argument. Right here we see two warnings, parameter length unfilled and parameter width unfilled, because we have to pass a value for length and a value for width. So what are we going to do? We're going to specify these values, separated by a comma and a space after the comma, like this. We add two lines after the class because this is recommended by the Python style guide. And right here we create our instance, passing the two values. 3 will be assigned to length and 6 will be assigned to width. Just like when we call a normal function in Python, the arguments are assigned to their corresponding parameters in the order that they were defined. Awesome! So now we have our instance. Let's print it to confirm that it is actually an instance of the rectangle class. Right here you can see it, rectangle object at this particular memory location. So this variable holds or references an object of the rectangle class, the object that we just created. Great, so now you know how to create instances with classes that don't take any arguments, that take only one argument, and that take multiple arguments. If this init method had more arguments, then we would just have to pass the corresponding arguments separated by a comma and a space after the comma. Okay, great work so far. Now you know how to create instances. Once you have your instances in the program, you will definitely need to access their instance attributes. So let's see how you can do that. This is the basic syntax to access an instance attribute. First, we write the variable that holds or stores the instance or object. Then we write a dot, and after the dot we write the name of the instance attribute. This syntax is called dot notation because it has a dot. It is a syntax used to access the members of an object. When we refer to the members of an object, we refer to its variables and methods, its attributes and methods. To access an instance attribute inside the class, we just use self before the dot to refer to the instance in a general way, because remember that we are making a blueprint, and this blueprint has to work with any instance of the class. Let's see an example. If we have the backpack class already defined right here with the items instance attribute, we can also access the attribute within the class using this syntax, self dot the name of the attribute. Let's say, for example, that we want to print the value of this attribute when we create the instance. We just want to check that it is an empty list. We are accessing the attribute by using the syntax self dot the name of the instance attribute. So let's see how this works. We're going to create an instance, my backpack. We use empty parentheses, remember, because we don't have any parameters right here. When this instance is created, this method will be called and this print statement will run. Let's run the code to see what we get. Right here you can see this as the output. We see the empty list that was assigned to this attribute. Right here we are printing the attribute because we are accessing it, and then we are passing it as the argument to print. So this is how you can access an attribute within the class. This will be very helpful when we start working with methods, which are the actions of the objects, because we can work with their attributes within the class. But outside of the class, we do need to specify the variable that holds the object before the dot. Because we have to specify the instance to access its corresponding instance attribute. Let's see an example. Now let's see how you can access an instance attribute from outside of the class through the instance that we created in our main program. We need to use the same syntax, but now instead of self, we are going to use the name of the variable that holds the object, which in this case is my backpack. Let's see this. If we print myBackpack.items, we will be accessing the items instance attribute of the object myBackpack right here. Notice that right here we are working outside of the class. This is the class definition, and this is part of our main program. Let's save the file and run the code. And right here you can see the empty list that we assigned as the initial value for this attribute. To illustrate this better, let's add some values to this list so you can see that we are actually printing this value. Let's say that initially our backpack will have a water bottle and some pencils. Let's say that it is a school backpack. Now if we run the code again, we see this list right here, the initial value of the items list for the instance myBackpack. So this is the syntax that you have to use. First, the name of the variable that holds the instance, then a dot, and then the name of the attribute. Now let's practice your skills and how you can access instance attributes inside and outside of the class with the movie class. First, let's start by defining the movie class. We have the class header, then we have init, and we have the same attributes that we defined previously. So let's do this quickly. Okay, so we have our class definition right here. Each movie is going to have a title, a year, a language, and a rating. Let's create an instance and let's say, for example, favorite movie. This is the name of the variable that will hold or store our instance. To create the movie instance, we use the name of the class, and within parentheses, we pass a value for each one of these parameters. We say pride and from the year 2005, it was recorded originally in English, and 4.8, let's say that it is the average rating on our movie platform that we are creating. So right now, we have our movie instance right here. Let's see how we can access its instance attributes. To see those values, we are going to print them. But you can also work with these values in your program as you need to. Let's take the instance favorite movie and let's print the title, for example. Then we are going to take the instance favorite movie and print the year. Then favorite movie and the language, and then favorite movie and the rating. This is how we can access these attributes using the name of the instance followed by a dot and then its corresponding instance attribute. If we save the file and run the code, we can see these values right here. This line prints the title, Pride and Prejudice. This line prints the year, 2005. This line prints the language, English, and this line prints the rating. Awesome, and just to show you that two instances can have different values for these attributes, let's create another instance. Let's say my favorite movie and your favorite movie. Let's say that your favorite movie is Titanic and the year is 1997. Language is English, and rating, let's say that it is 4.6 on our platform. Right now, since we changed the name of this instance, we will have to update it right here. Okay? And we print. Let's print a message. My favorite movie. And then we are going to print the data for your favorite movie. We can just copy and paste this very carefully. It's just 4 lines and we just need to update this name to be the instance that we created for your favorite movie. Let's save the file and run the code and see the output. We see this right here. My favorite movie, Pride and Prejudice, 2005, English, and 4.8. We are printing all the instance attributes. And then we go to your favorite movie right here. Titanic, 1997, English, and 4.6. You can see how each one of the instances has its own values for these attributes. The syntax is the same, and the attributes are the same, but their values are different, and they are completely independent from each other. Awesome! So now you know how instances work and how you can access their attributes. Great work so far! We can also assign default arguments for the parameters that we define in the init method when we create the instances. And this can be very helpful. First of all, default arguments are just default values that are assigned to the parameters of a method when their corresponding arguments are omitted. So we're basically saying, if I don't give you a value for that parameter, then use the default value that I assigned. This is the basic syntax that you need to use to assign a default value or argument to a particular parameter. You write this in the list of parameters. We write the name of the parameter followed by an equal sign and then the value or the default argument. Let's have a quick tour of the documentation to see what it recommends. If we go to PEP8, the style guide for Python code, and then we go to the subsection white spaces in expressions and statements, we can click on other recommendations and we will see a recommendation that mentions default values for parameters. Right here. It says don't use spaces around the equal sign when used to indicate a keyword argument, or when used to indicate a default value for an unannotated function parameter. It says that this is correct and this is wrong. We always want to follow best practices when we write our code. Right here, we're going to define a circle class with an init method. And in that method, we are going to add a radius parameter. But this parameter is going to have something different. We are going to assign a default value or a default argument for the parameter. In this case, the default value will be 5. So if we omit the radius when we create the instance, 5 will be assigned by default. Let's also create an instance attribute, radius. Okay? So we're basically telling the program, if I don't pass a value for the radius, I want that value to be 5. Assign this value to this parameter, and then assign it as the instance attribute, as the initial value for this attribute. Okay, so let's create the instance, myCircle, with the name of the class, and let's see both versions. What happens if I don't pass a value for radius, and what happens if I do pass a value for radius? If we don't pass a value for the radius, you can see that there are no errors. Previously, if we didn't have a default value, we would have this yellow warning right here that said parameter radius unfilled. Okay, but now, since we are assigning a default value, we don't get that warning anymore. We can still create the instance. So let's use a print statement to display the current value of the radius. The instance will still have a radius attribute. So let's check this value. If we zoom in right here, we can see that the value of the radius is indeed the value that we assigned by default, 5. This value was assigned to the parameter and that value was assigned to the instance attribute. Awesome. Now let's see what happens if instead of doing that, we pass a value for the radius. For example, 8, right here. Since we are specifying a value for this parameter, we will use this value. Let's confirm. We save the file and we run the code and we see that now the radius is 8 instead of 5. Because this is just a backup in case we don't specify this value. Great, so now you know how to define default values for the parameters of the init method. A very important thing that you need to remember is that parameters that have default arguments must be the last parameters in the list of parameters. Otherwise, you will get an error. Let's see an example. Let's say that we have right here a circle class with the default argument that we defined. And let's pretend that we are going to add a parameter color after the radius. Okay? We immediately see an error right here that says non-default parameter follows default parameter. This is just telling us that we cannot add a parameter without a default value after a parameter that does have a default value. Let me show you why. First, let's complete the class definition and let's define an instance. Let's say that we are passing the value 7 for the radius and the color blue as a string for the color. This will throw an error, but we are just pretending like we don't know that this error will ever be thrown. Okay? We just continue writing our code, we save the file, and we run the code. And when we run the code, we see this error right here. Syntax error, non-default argument follows default argument. And what happens right here, we see this symbol that is sort of like an arrow pointing right here. It is telling us that we cannot define this parameter right here. And what is the logic behind this? Why does the parameter have to be the last parameter in the list? Well, since we are assigning a default value for the radius, that means that in theory we can omit this parameter when we create the instance. And what happens if we omit it? Well, let's say that we want to use the default value for the radius. So instead of passing the value 7 right here, we omit it and we just pass the color blue. But that will be very problematic because the color blue is now the first argument in the list. And the first argument should correspond to the radius in the definition. But it corresponds to the color. So that is not correct. The argument will not be matched to its corresponding parameter. So that is why this type of parameters with default values have to be the last parameters in the list, like this. Because if we omit them, we just omit them. We are not changing the order of these arguments that do require a specific order when we pass the arguments. Right here, we can specify that the color is blue. And this is the first parameter in the definition. And if we want to omit the radius, we can omit it, and we are not affecting the order at all. But if we do want to specify it, we can do it as well, and we will not affect the list of arguments. Great, so now you know why they should be the last parameters in the list. Awesome, great work so far. You can, and you definitely will, modify the value of instance attributes in your program. This is very helpful because we can update the state of an object, and objects usually change. For example, a player moves across the screen. A backpack can have more items or less items, so updating their attributes is very important. To do that, we just use this syntax right here that is very similar to assigning a value to a variable. First, we write the variable that references the object or that holds the object. Then we write a dot because we are still using dot notation. Then we write the name of the attribute that we are trying to modify. And then we use the equal sign to assign the new value for that attribute. As you can see, this is very similar to assigning a value to a variable. We are just using dot notation right here to specify that we want to change the attribute. Inside the class, you just need to replace the object by self, because remember that the class is a general blueprint. Let's see an example. Actually, to show you that we've already been working with this syntax before, here we have the backpack class with the items instance attribute. When we write this line of code, we are actually modifying or updating the attribute. We're creating it because this is the first time that we actually use this line of code with this attribute. But if you use this line again anywhere in your class, you will be updating the value. It is equivalent. Creating the attribute and updating the attribute has the same syntax in Python. So you have already been using the syntax since you started learning about instances. We have self followed by a dot, the name of the attribute that we want to update, create, or modify, then the equal sign and the value that we assign to that particular attribute of the instance. When you try to modify an attribute outside of the class, you just need to specify the variable that references or holds the object. And that will do all the magic, because we are specifying the attribute of the instance that we want to modify. Let's see an example in our code. Now we're going to use the syntax that you just learned to modify an instance attribute outside of the class. In this case, we're going to add a second attribute to the backpack, which is going to be color. Okay? We add that instance attribute and we are going to create the backpack instance. Backpack. We have to specify a color for the backpack, so we are going to choose the color blue. We have 2 lines right here, and then we are going to confirm that the color is actually blue, the color that we assigned initially. Let's save the file and run the code. If we zoom in, we can see that indeed the value is blue. Okay, so we want to update the value of the color of the backpack, and we want to change it to the color green. What do? We write the name of the variable that references the object, my backpack, and we are going to specify the attribute that we want to modify, the color. We're going to change this to green. This is the value that we will assign to this attribute for this instance. After that line, after we update the color right here, the attribute will have a new value. So let's check this new value with another print statement that prints the color. If we save the file and we run the code, now we see this, blue and then green. Initially, the color was blue right here, and then it was updated to green right here after we run this line of code. Great, now you know how to update an instance attribute outside of the class. Let's create another instance of backpack so you can see that this change is independent for the instances, okay? If we change an attribute of one of the instances, the other instances will not be affected. Let's check this with another instance, let's say your backpack. We create another instance of backpack, and now this backpack will be initially red. Let's print the initial values of the 2 instances. First we have the color of my backpack, and then we have the color of your backpack. This should be blue and this should be red. Then we are going to print a message. Let's say changing color. We change the color of the backpack, but only the color of my backpack. We're not changing the color of the other instance. We have 2 instances right here. We will print their initial colors, and we will only modify the color of my backpack. Your backpack should be kept intact. If we print the colors again, right here, we save the file and we run the code, we see exactly what we expected. Initially, we have the 2 colors that we assigned, blue for my backpack and red for your backpack. Then we are changing the color of the my backpack instance. We change it to green. So now when we print it again, this color is now green. But the color of your backpack was not modified. It is still red. So you can see that changing the value of an instance attribute does not affect the values of other instances. They are completely independent from each other. And that is part of why object-oriented programming is so powerful. We are using this blueprint to create objects, but each object is independent from the other objects in the program. Now you know how to update instance attributes in your code. Please take a moment to think about how you can update the items attribute of a backpack instance. This is a list, remember, so you should assign another list. Try to do this, check that it is updated correctly, and then move on to the next lecture. I will see you there. Let's practice how you can modify instance attributes and update their values outside of the class. First of all, we are going to define a circle class, and we are going to define the init method in this class. We're going to take 2 parameters, radius and color, and we are going to assign them as instance attributes, radius and color, okay? If we create the instance myCircle, we have to use the name of the class and then pass a value for each one of these parameters. We have radius of 6 and color yellow. Great! Let's print the value of the instance attributes of the instance. Let's print the radius and let's print the color. After we print these two values, we can run the code and see that they are indeed the values that we passed to create the instance, which is 6 and yellow. We've confirmed that the values are what we expected. So now we have to update the values. Let's say that we need to update them to, for example, 15 and to the color, let's say black. After we have these new values, we can print them again to check that they were updated successfully. If we save the file and we run the code, we see the old values, the previous values, which were 6 and yellow, right here, and then we see the updated values printed right here after we run these two lines of code, 15 and black. Great! So now you know how to update instance attributes. Remember to use this syntax. The name of the variable that references or stores or holds the instance, followed by a dot, and then the name of the attribute that you want to modify. After that, an equal sign and the new value that you want to assign to the attribute. Great work so far! Now that you know how to work with instance attributes, we will dive into class attributes. A class attribute is an attribute of the class. Class attributes belong to the class, not to a particular instance. Previously, instance attributes belong to the actual object that we were creating, but now class attributes belong to the class. So all instances share this attribute, and they take their value from the same source. All instances of the class have access to this attribute, and they share the same value. So any changes made to this value affects all instances. That is something that you really have to be aware of when you decide to make an attribute a class attribute. Any changes that you make to the value affects all instances. For example, if we have a class attribute defined in our class and we change it, all instances are affected because they take the value from the same source. Class attributes are usually written or defined before the init method in a class. This is the basic structure of the class. You will learn how to define them in the coming video, so I'll see you there. Let's see how you can define class attributes in your Python classes. This is the basic syntax. It is very similar to a simple assignment statement that we use when we assign a value to a variable. We write the name of the attribute, followed by an equal sign, which is the assignment operator, and then the value that we want to assign to the attribute. Remember that they are usually defined before the init method in the class, and they have to be indented to be part of the class. This indentation right here would be 4 spaces or 1 tab, but it is recommended to use 4 spaces according to the Python style guide. Think about how you would define a species class attribute for a dog class based on the syntax that you just learned. Research the species of a dog and define this attribute in the class. Try to do this and then move on to the next video to check your work. We will write this in our code. Welcome back and welcome to this example. In this case, we're going to define a dog class with a species class attribute. First, let's write the part of the class that you're already familiar with, like the class header, which has the class keyword and the name of the class, and right here we are going to write the init method to define some instance attributes to make the class a little bit more realistic. Let's define a name, then the age, and then the breed of the dog, okay? Now, how are we going to define our class attribute? We said that class attributes are typically written or defined before the init method. So what do we have to do? We just click right here, click enter, we add a few blank lines between the class header and the init method, and right here in the middle, we write our class attribute. We say species is equal to the value that we want to assign. Dog species is Canis lupus. We can confirm this if we go to, for example, Wikipedia, we search for dog, we click on this article right here, and then We reach the article, and right here you can see that the species of a dog is C. lupus. If you hover over this link right here, you will see right here that we have Canis lupus. So we are going to write that in our code right here. So now we have our class attribute. All dog instances that we create from this class will have this attribute. It will be shared because it belongs to the class, not to a particular instance. These attributes belong to the instance, name, age, and breed. But this attribute, you can see that we are not using self anywhere in this line. We are not using self because we don't need the instance. This attribute only belongs to the class, and this value is shared across all instances of the class. Great, so now let's go to our second example. We're going to continue working with our backpack class, but now we are going to add a class attribute. We're going to specify the maximum number of items that we can have in a backpack. Let's define the init method and the items attribute, which is initially an empty list. Now, how can we add a class attribute to the class? We just add a few blank lines right here, and in the middle, we just define the attribute. We say the maximum number of items that we can have in the backpack is equal to, let's say, 10. Let's say that this is the maximum number of items that we want to set for the backpack. If we do this, all the backpack instances that we create will have a maximum number of items attribute with the value 10. And if we change or modify this value, they will all be affected by the change. Okay? You can see that we don't have self anywhere in this line because we are not using or referring to the instance. We are just writing an attribute that belongs to the class. Awesome! Now you know how to add class attributes to your classes. Great work so far! When you're ready, go to the next video to continue learning more about class attributes and how you can work with them. You can access class attributes using dot notation, and this is very helpful because we can work with their values and use them in our code. From outside of the class, we just need to write the name of the class, followed by a dot, and then the name of the attribute. Let's see an example. Right here we have our dog class with the species class attribute. Let's see how we can access this attribute outside of the class. This is the class definition, so if we don't indent our code, that code will not be part of the class. It will just be part of the main program. So what are we going to do? We are going to print the value of this attribute, the species attribute. And how can we access it? Well, we use the syntax that you just learned. First, we write the name of the class, which is dog, and then we write the name of the attribute, species. Right here, we are using dot notation. We are specifying the name of the class, and then we are using a dot to specify the attribute right here after the dot. We say access the species attribute of the dog class. So let's save the file and run our code to see the output. Right here you can see this. The output is Canis lupus, exactly what we have right here, the value of the species attribute of the dog class. So you can use the syntax not just to print the value, you can use it anywhere in your program where you need to. Now you know how to access class attributes outside of the class. Now inside the class, if we have to refer to this attribute, we just use the same syntax. The class name followed by a dot and then the name of the attribute. Great, let's see an example of how we can use class attributes inside the class. Now in this example, we're going to define a movie class. Right here we have two instance attributes, title and rating. But we also want to add a third instance attribute called ID. We're going to add this right here. And what will be the value of the ID? Well, we want each movie to have a unique identifier. For example, when we add the first movie to the system, we want the movie's ID to be 1. Then the second movie should have an ID of 2, and so on. How can we do this? How can we get a unique number and increment it each time that we create a movie instance? Let's see. We could define a class attribute that will serve as a counter, like this. we will just call it, for example, ID counter, and initialize its value to 1. This attribute belongs to the movie class, not to the instances, so this will be shared across all instances. How can we assign this value of this attribute, to the instance attribute? Well, we just use the syntax that you learned. The name of the class followed by the name of the attribute. Right here, we are taking the value of the counter of the movie class, and we are assigning it to the ID attribute of the instance. We're basically taking the current value of the counter and assigning it to the instance. But there is a small issue right here. What happens if we don't update this value? Then all the movies will have the same ID. So for that, what we can do is something that you will learn in the coming video in more detail, but we can update this value. We take the counter of the movie class and we can increment it by 1 each time that we create an instance. First, we assign it to the attribute ID, and then we increment it by 1. That way, when we create our first movie, this value will be 1. Then it will be updated, and for the second instance, it will be 2. Then for the third instance, it will be 3, and so on. Let's see how this works in detail by creating movie instances. For example, let's say my movie. We say movie, title, Sense and Sensibility, and with a rating, for example, of 4.5. And then let's say your movie. Let's say, for example, Legends of the Fall with a rating of 4.7. What can we do with these two instances? Let's check the value of their IDs, okay? To see if we have exactly what we expected. Each movie instance should have its own unique ID, because we are keeping track of a counter that will be incremented each time that we create a movie instance. For this movie, the ID should be 1. For this movie, the ID should be 2. Because right here, we are assigning that updated value to the instance attribute. We are assigning a class attribute to an instance attribute. So if we print these two values, let's see the output. We see exactly what we expected, 1 and 2. This movie's ID is 1, and this movie's ID is 2. And this is an example of how you can combine the power of class attributes with instance attributes. Class attributes are shared across all instances, and instance attributes are independent for each instance that we create. Awesome! Now you know how to access class attributes outside and inside of the class. And we also had a quick preview of how you can update a class attribute. When you're ready, go to the next video, and I'll see you there. Welcome to this example. Now we will work with our backpack class. We will define a class attribute, and we will review all the principles of class attributes with this example. First of all, let's define a class attribute max number of items, like we did in a previous video. And real quick, let's define the init method with the empty list of items that we initially have for each backpack instance. This is our class at the moment. So what are we going to do? We're going to create two instances of backpack. My backpack and your backpack. After we have our two instances, let's confirm that they actually have this attribute, max number of items, because we said that all the instances that we create from the class will share this attribute, and they will all take it from the same source. So let's confirm this. Print my backpack dot max number of items and your backpack dot max number of items. Let's save the file and run the code. Right here we can see this as the output, exactly what we expected. We see the value 10 for the two instances. Right here we have the my backpack instance and your backpack instance. They both have a max number of items attribute that we defined right here, and the value is 10 for both instances. They share the same value. Let's also check that we can access this attribute just by using the name of the class, like you learned in the previous lectures. Let's see. We write the name of the class, which is backpack, and then right here we specify the name of the attribute. If we save the file and we run the code, right here we see that all three values are exactly the same, the value 10. So we can access this attribute through an instance or through the class directly. Why can we do this? Why can't we just write the name of the class and then the attribute? Well, because the attribute belongs to the class, not to a particular instance. All instances of the class will have this attribute, but it is not necessary to have an instance. We can just access it with the name of the class. And this is what we usually do when we are working with a class attribute. Awesome! Now you know how class attributes work and how to access them inside and outside of the class, and you've practiced these principles with an example. Now you will learn how to modify the value of these attributes, because sometimes you will need to update them. For example, let's say that you are designing a larger backpack that has, for example, 15 as the maximum number of items. You will need to update that in your code, and you can do that. That is what you will learn in the coming videos. You can modify the value of a class attribute. Let's see how you can do this. You have to analyze this carefully before updating a class attribute, because changing the value of a class attribute will definitely affect all instances of the class, because they take that value from the same source. So if you change the value at the source, they will all be affected. This is the syntax. First, we write the name of the class. Then we write a dot, then the name of the class attribute that we want to update, and the new value after the assignment operator, the equal sign. As you can see, this is very similar to assigning a value to a variable. But right now, with the dot and the name of the attribute, we are specifying which attribute we want to update. You had a quick preview of this syntax in the last lecture, but let's see an example in detail so you can review this. Let's start by writing a circle class, like this. We're going to assign the class attribute radius, which will be equal to 5. This will result in that all the instances of circle will share this value. They will all have the same radius, and if we update this radius, they will all change, okay? So right here, let's also define the init method, and let's just assign a color for the circles. So we can work with instance attributes and with class attributes in the same class. Let's see how we can update this value, but first let's check that this value is what we want the value to be. Let's print the value of circle.radius. Save the file, we run the code, and right here we see the value 5, which is exactly what we wrote in our class. So this is correct. Now let's create two instances, okay? My circle and your circle. Right here, we have to specify the color of the circle. Let's say blue. And right here, let's say green. We have our two instances. Let's confirm that they both have a radius attribute with these lines of code. Okay, we're printing the value of their attribute, like this. And we can confirm that indeed these values are all equal. The radius class attribute is equal to 5, and each one of the instances has that attribute, radius, and it is equal to 5. Now, let's see what happens if we try to update the class attribute. Like this. We write the name of the class, followed by the name of the attribute, and then we assign the new value to the attribute. Previously, it was 5, and now it will be 10. Okay? Let's see the effect that this has on the instance attribute. What are we going to do? Well, we are going to print the radius again using the class, and we are also going to print the value of the radius for each one of the instances. So you will see that the radius changed for the class and for each one of the instances, because they all take the value from the same source. Now let's save the file and run the code. And right here you can see how the values changed. Let me resize this so you can see this a little bit better. Right here we have our initial values, 5. these are the result of this print statement and these two print statements. And then we update the value of the radius in the circle class to 10. After that, we have these three print statements, and we can see that the value was updated for the class and for each one of the instances that we created with the class. Awesome, so now you know how to update class attributes outside of the class. And we use the same syntax to update a class attribute inside of the class. The class name followed by a dot, the name of the attribute, an equal sign, and finally the value. Now let's see another example. But first, please take a moment to think about how you can update a class attribute price of a pizza class. Let's say that in our store, all pizzas have the same price. So we want to define price as a class attribute to make all instances share this value. Think about this, pause the video, and then come back so we can start writing the code. Now let's go to our second example, which will be a pizza class. Let's write the class header, class pizza. We said that we wanted to add or define a class attribute named price because we have a brand new store and we've decided that all pizzas in our store will cost exactly the same. So let's say that we assigned a price of $12.99 and the clients can have as many toppings as they wish for that fixed price. That would be really awesome, right? So after that, we're going to create the init method. What are we going to assign as instance attributes? Well, each pizza will have a description, will have a list of toppings, and will have a type of crust. Awesome, so we just have to create this instance attribute, self.description, self.toppings. We use these parameters right here, and self.crust. We have our class already defined with a class attribute price. Typically, in a typical store, this would be an instance attribute because each pizza would have its own unique price based on the toppings and based on the type of pizza. But right now, we are simulating this scenario where all pizzas in our store have a fixed price. And if we change this price, all pizzas will be affected. Okay, so what are we going to do? We are going to confirm that the price attribute is indeed $12.99. Let's save the program, and right here we see the output. $12.99 is the value of the class attribute price of the pizza class. So now let's create a pizza instance. We say my pizza will be a pizza of type margarita. It will have basil and mushrooms. And the crust will be New York style. This is really delicious. What are we going to do with that instance? We are going to confirm that the price of that pizza instance is really $12.99. So let's save the file and run our code. And right here we can see that it is $12.99. Okay, so now we're going to update our class attribute. Let's say that at some point in our program we need to update that value. How can we do that? Well, we just write the name of the class, which is pizza, and then we write the name of the attribute, price. We're going to change this from $12.99 to $13.99. Okay? We are incrementing the price of our pizzas by $1 because our store was really successful. After that, what are we going to do? We are going to print again the value of price for the pizza class and the value of that attribute for the instance that we just created to confirm that they are the same and that the price was updated successfully. Let's save the file and run our code, and right here we can see this. We see the old price, which is the output from these two print statements, and we also see the new price, $13.99. This line updated the price, and right here we have the two print statements that print these two values. Awesome, now you know how to define, access, and modify class attributes in Python. Remember that this value is shared across all instances, and if you change this value, all instances will be affected. Welcome to this practical example where we will review the principles that you learned about class attributes in Python. We're going to use, as an example, our backpack class. with the attribute maximum number of items. Let's say that we initially defined this to be 10. 10 items is the maximum number of items that our backpacks can contain. Okay, so what are we going to do first? We are going to check that this attribute has indeed the value 10. So we're going to print it. We access it outside of the class with the name of the class, followed by a dot and then the name of the attribute. If we save the file and we run the code, we see that this value is indeed 10. After that, we are going to create an instance, my backpack, right here. And we are going to check if this instance has a maximum number of items attribute and that its value is 10. Since you learned that class attributes are shared and they take the value from the same source, which is the class. And indeed, that is exactly what happens. The instance automatically has this attribute and the value is 10 like we assigned right here. Awesome. We checked that things are working as we expected, but now let's say that we want to make our backpacks have a greater capacity. Let's say that now the maximum number of items will be 15. We can do that by writing the name of the class followed by the name of the attribute and then the new value, which is 15. After this line, the value will be updated. So to check that, we are going to write two print statements again. To check that this attribute, when we try to access it with the class, has the value 15, and when we try to access it with the instance. They should both have the same value. And right here you can see that this works as we expected. Initially, the capacity was 10 items. And after we run this line, we have a maximum number of items equal to 15. Okay, all the instances that we create from the class in our program will be affected or impacted by this change because they take this value from the same source, which is the class. Great work so far. Now you know how to work with class attributes in Python, how they work, how to access them, and how to modify them both inside and outside of the class. Welcome to this section. Now you will learn two basic pillars of object-oriented programming: encapsulation and abstraction. Let's start with encapsulation. Encapsulation is one of the main pillars of object-oriented programming. It is the bundling of data and methods that act on that data into a single unit. This unit is called a class. So the class acts like a capsule that holds the attributes and the methods of the object, and it separates them or kind of isolates them from the rest of the program, because they are part of this larger unit called a class. The purpose of the class, or the purpose of this larger unit that contains these elements, is to be able to restrict access to these elements, following the principle of information hiding. This capsule that is made by the class serves as a shield, because its goal is to prevent direct access to the attributes and to the data of the object, in order to avoid making potentially problematic changes to its state. So basically, we only let the outside world, the rest of the program, see what we want it to see of the class or of the object. We can only see public members of the class. We only see what the developer of the class chose to make public. And we can choose to make some elements not public, so they are kept safely within the class, without any external access. This is the core of the principle of encapsulation. Getters and setters are methods, specific methods, that help us follow this principle by protecting the data and providing an indirect way to access that data. You will learn more about them in this section. And you will also learn about properties, which are the way we implement getters and setters in Python. Making members of a class public and non-public helps us to preserve their integrity and keeps them safe, because we can choose which elements are public so they can be accessed from outside of the class, and which members are non-public and shouldn't be accessed outside of the class. They should only be accessed within the class, and they are restricted to live and work within the capsule. Awesome, now you know why we have public and non-public attributes. So please take a moment to analyze why it is important to avoid making unexpected changes to an attribute. Think of an example of an attribute that shouldn't be modified unexpectedly. Think about the consequences of changing it to an invalid value, and analyze why it might be helpful to make this attribute non-public, so it can only be accessed within the capsule, within the class. Think about this, and when you're ready, go to the next video to continue learning about these basic pillars of object-oriented programming. Now let's see the principle of abstraction and what this principle is all about. It is one of the basic pillars of object-oriented programming, and it basically states that we should show only the essential attributes of a class or of an object, only the essential members, and hide unnecessary details from the user, of the class in this case. So this principle lets us hide the complexity of the internal implementation of the class from the user. For example, having a real-world analogy, when you use a smartphone, you use the graphical user interface that developers created for you to interact with the phone, like buttons and elements, that let you use the phone in a user-friendly way. You don't need to understand all the complex details or steps that occur behind the scenes in the electronic device when you actually use your phone. So this is an example of abstraction in the real world. The same happens with a car. When you turn on a car with the key, you don't actually know what is happening behind the scenes in the engine. And you don't need to, because engineers created a way for users to just use the key and the wheel to drive the car without knowing the internal complexity of the engine. This is another example of abstraction, in the real world of course, and we are taking that concept and applying it to software development. A class has two main parts, an interface and an implementation. We can sort of divide the class into these two parts. The interface is the visible part of the class that the program can interact with. It is basically what we choose to show from that capsule. Now the implementation is the other part, the internal part of the class with the code that performs the functionality behind the scenes. It is the actual code that makes all the functionality of the class work. If we use the analogy of a car, the wheel would sort of be like its interface with the user, and the engine would be the actual implementation of the class. In the class, we choose to expose only the members that should be exposed, and all other members are non-public, so they cannot or should not be accessed from outside of the class. We sort of like create a black box, where the user of the class knows how to interact with that box, but doesn't know the details of the internal implementation. He or she only knows the effect that the box will have. This way, we are hiding the implementation from the user, and we can change it without affecting how the user interacts with a member of the class. We are not affecting the program at all if we change the internal implementation, but not the interface with the user. The users, or anywhere else in the program where we use the class, will still be kept intact, but we can change the internal implementation. The principle of abstraction also allows us to abstract out common parts of the code to avoid repetition. This is another part of the principle, another aspect of this principle. We can abstract out common parts of the code to avoid code repetition by using abstractions or representations of more abstract objects. For example, if we need to define two classes in our program, Poodle and Schnauzer, these are both dog breeds. So they will have a lot of repeated code because they will have similar attributes because they are both dogs and functionality. Instead of writing these two classes and repeating the code in both of them, we can create a new class called dog with the shared attributes of these two classes. This class would of course be more abstract in nature, and it would be reusable. So if we ever need to represent another dog breed in our program, we could do it without code repetition. These two classes would inherit, that is how we call this, inherit, and you will learn more about inheritance during the course, but they will inherit the attributes and the functionality of this general class, and they would reuse that code without us having to write it explicitly in these two classes. This is the principle of abstraction. You can see that it is very helpful because we hide the internal complexity of the class from the user and we can avoid code repetition. Please take a moment to analyze why abstraction can be helpful. And when you're ready, go to the next video. I will see you there. Public and non-public attributes play a key role in object-oriented programming because they help us follow the principle of encapsulation. By making some attributes public and others non-public, we can restrict the access to these elements and protect them from unexpected changes. We will be following the principle of information hiding. In Python, attributes can be either public or non-public. A public attribute is an attribute that can be accessed and modified directly without any access restrictions. So we can access and modify it anywhere in our program. Let's see an example in our code. So far, we have been defining public attributes in our classes. So let's start by defining our car class. We're going to represent cars with a brand, a model, and a year. All of these attributes are public. Let's create a car instance. The model will be 911 Carrera and the year will be 2020. Awesome, that is a really beautiful car, right? So let's see if we can get or access outside of the class the year of the car. Let's save the file and run our code. And indeed we can, it is 2020. So far, so good, right? We can define the attributes and we can access them. But let's see the risks of making an attribute public, completely public and accessible from anywhere in our program. Let's say that somewhere in our code, we write this line of code. We are actually updating the year of the car to 5600. Right now, that would cause a serious bug in the system. Let's see if this update is allowed by the program. If we run the code, we see that before the change, the year was 2020, like we specified. But after we run this line, the year is now 5600. So we have a futuristic car that was manufactured before this year. That is one of the risks of making an attribute completely public, that we can access it and modify it directly outside of the class without any validation. We cannot validate this value. We cannot check if it is appropriate for the attribute of our class. And that makes our code more error-prone. We can make unexpected changes that affect our program. However, public attributes are really helpful as well when we do want to allow direct access to these attributes and modifications. Now that you know what public attributes are and how to work with them, let's go to non-public attributes. A non-public attribute is an attribute that shouldn't be accessed or modified outside of the class. We use the term non-public here because we are following the term that is used in the Python style guide. Usually you will not see the term private in Python because no attribute is ever really private in Python. And you will see why in just a moment in this section. So we will be commonly using this term, non-public. In Python, we have two ways of defining a non-public attribute: by naming convention or by activating a mechanism that changes the attribute's name and makes it more difficult to access, called name mangling. When we use the naming convention, which is what we typically do, we just add a leading underscore to the name of the attribute. And this will immediately tell other developers visually that the attribute should be treated as non-public, so it shouldn't be accessed or modified directly outside of the class. We can also trigger this process of name mangling, of changing the name, by adding two leading underscores, to the name of the attribute. This makes it more difficult for developers to access the name because we are actually changing the name during the process. You will learn how name mangling works in a specific lecture of this section. But you must know that the second alternative should only be used for special cases. So we typically work with and use the first alternative with one leading underscore. Let's see what the documentation has to say about non-public attributes in Python. If we go to the Python documentation, to the article that covers classes right here, we can click on this part, section 9.6, private variables, right here. It says private instance variables that cannot be accessed except from inside an object don't exist in Python. This is what we mentioned. They actually do not exist. However, there is a convention that is followed by most Python code. A name prefixed with an underscore, like this. You can see that we have the name, and right here we have a leading underscore. This should be treated as a non-public part of the application programming interface, whether it's a function, a method, or a data member. It should be considered an implementation detail and subject to change without notice. So that is basically the message that you are sending to other developers when you add a leading underscore. You're telling them that this is part of the implementation and it is subject to change without notice. So they should not use it because that could break their code if you make any changes to that attribute. So remember, one leading underscore is a naming convention, and two leading underscores triggers the process of name mangling and should only be used for special cases. Let's see an example. Right here we have the car class that we defined with the 3 public instance attributes. But we already saw the possible consequences of making an attribute public, and something that is so important as the year and so restricted in the range of values that it can contain should probably be a little bit more protected from direct change. So how can we change this? How can we protect this attribute even further? Well, we can make it non-public or protected. We can do that by just adding a leading underscore to its name. Let's see how this changes the functionality of our code. If we add a leading underscore right here, we can still create the instance the same way as we did. This value will be assigned to this parameter, and the value of this parameter will be assigned to the attribute year. But now the attribute year doesn't actually exist. We have a leading underscore before its name, so when we try to access it right here below, let's see what happens. We get a yellow warning that says, unresolved attribute reference year for class car. This is basically telling us, hey, this car, this object, doesn't have a year attribute. So why are you writing this in your code? Well, let's see what happens if we save the file and we run the code. Now we see this error that says attribute error, car object has no attribute year. So we know that the object doesn't have this attribute. Now it has a leading underscore. And this is like a red warning telling other developers that they shouldn't access this attribute outside of the class. I'm sure you must be asking yourself, why do we keep using the term non-public instead of private? If you've already learned how to work with other programming languages like Java, you will commonly see the term private, but right here we are using the term non-public. Well, according to the documentation, and I'm taking this literally from the documentation, the Python style guide, we don't use the term private here since no attribute is really private in Python. This is very important. No attribute is really private in Python. Technically, you can access them, but you shouldn't. In Java, we have something called access modifiers that help us hide or determine where the attributes can be accessed, like public, protected, and private. But in Python, we don't have any access modifiers. So we rely on naming conventions to tell other developers that a member of a class, like an attribute or a method, is intended to be non-public. Awesome! Now you know how public and non-public attributes work in Python. So please think for a moment how you could access those non-public attributes outside of the class. I'll give you a hint. It's basically the same syntax, but we add a leading underscore to the name. Try to do this in our example in our car class. Pause the video for a moment and then come back so we can start writing the code and working with these attributes. Technically, you can still access it if you add the leading underscore right here. But you will see a warning that says access to a protected member year of a class. PyCharm is reminding us that this shouldn't be accessed outside of the class. If we run the code, we will still see the value because we can technically access it, but we shouldn't according to the Python naming conventions. Welcome to this example. Now you will practice defining non-public attributes in a Python class. We will define a student class in this case. We have write the class header and then we have to write the init method. Like this. In this case, we are going to take 4 parameters. The student ID, the name, the age, and the GPA, or the grade point average. Let's define the instance attributes like we usually do. Self.the name of the attribute, and then we assign the value of the parameter that we have right here. But let's say that we analyzed the class and we determined that the age attribute is an attribute that shouldn't be accessed or modified directly outside of the class. So how can we tell other developers that this attribute should not be accessed? Well, by using the naming convention that you just learned. We add a leading underscore to the name of the attribute, and we can immediately see the visual change in this list of attributes. We see the leading underscore, and this is like a red warning saying, please don't use this attribute outside of the class. So let's see how this impacts the code that we have been writing so far. We're going to create an instance of student, and we're going to store it in the variable student Nora. Okay? The first argument has to be the student ID, so 245AFS. Let's say that that is the student ID. And then we have the student's name, NoraNav. For simplicity purposes, we're just writing it as a string, the full name. The age will be 15 and the GPA will be 3.96. Okay, so now we have our instance. Let's see if we can access the age attribute like we used to do in our previous examples. We used stop notation and right here we wrote the name of the attribute. But what do we see right here? We see a yellow warning that says unresolved attribute reference age for the class student. This is just saying that there isn't an age attribute in this class that is part of this object. So why are you writing this? Let's save the file and run the code to see the error that we get. We see this error. Attribute error, student object has no attribute age. And it points to this line. This line is the one that caused the error, where we try to access the age attribute. This attribute is not found, but what do we have to do to fix this? In theory, we shouldn't access this outside of the class. But to show you that in reality no attribute is ever really private in Python, we can just add the leading underscore to the name of the attribute. And that will give us access to the attribute, but it will also show us a warning. Let's see. Right here we see the value of the age, right? We have the value 15, which is exactly what we assigned as the age of this instance. But we also see a warning right here that says access to a protected member age of a class. We're receiving that warning because even though we are technically allowed to access that attribute, we shouldn't access it in our program. So PyCharm is reminding us of this rule. Awesome, now you know how to define non-public attributes with a leading underscore and how this impacts how you can access the attribute in the class. You know that you shouldn't access this attribute outside of the class. You will receive a warning. Technically you can do it, but you shouldn't. The developer is telling you that this is only meant to be used inside the class. Now let's see another example of how you can define non-public attributes in Python. In this case, we're going to continue working with our backpack class and we are going to define our init method with the initially empty list of items. But let's say that we want to protect this attribute. We don't want the list of items to be accessed or modified outside of the class directly. So what do? We just add a leading underscore right here. And we're already visually telling users of our class that they shouldn't access this attribute. How can we check that this attribute is actually protected? Well, we can create an instance like this of backpack. And let's see what happens if we try to access the attribute like we did, just by writing the name of the attribute. Well, we see that it turns yellow and we see the warning unresolved attribute reference items for class backpack. This is just telling us, hey, this object doesn't even have an items attribute, so why are you writing this in your code? Let's see the error that we get if we try to run the code. Right here we see attribute error, backpack object has no attribute items. It doesn't have this attribute, and if we add a leading underscore, we will be able to access it, but we shouldn't. Let's see if we can, technically. Yes, we can. We see the empty list right here, but we see a warning from PyCharm. Access to a protected member items of a class. This is warning us that we shouldn't access this element outside of the class. So now you know how to make this attribute protected or non-public in your class. Awesome, so let's see our next example. Now we will define a movie class just like we did in a previous example with an ID counter. We have a class attribute ID counter, and in it, we will assign a unique ID for each movie. We will have these 4 instance attributes. And now we are going to define a 5th instance attribute called ID. We are going to take that ID from the class attribute, just like you learned when we covered class attributes. And we will update that class attribute every time that we create an instance right here. But don't you think that the ID of a movie is a very important attribute that shouldn't be accessed or modified outside of the class? It should at least not directly, because this could cause unexpected changes and bugs in our program. So what can we do to protect this attribute even further? Well, we can add this leading underscore to the ID. And there we're telling other users that the ID should only be used within the class, and it shouldn't be changed, modified, or accessed directly. Let's see how this works by creating 2 movie instances. My movie, let's say Pride and Prejudice, in 2005, in English with a rating of 4.7. And then your movie, Sense and Sensibility, from 1995, in English, and let's say a rating of 4.6. This movie should have an ID of 1, and this movie should have an ID of 2. But let's see if we can access the ID. Let's see what we get. Now, in both of these cases, we see a yellow warning that says Unresolved Attribute Reference ID for class movie. This is because the objects do not have an ID attribute. What do they have? Well, they have this protected attribute right here, or non-public attribute. What we can do technically to access them is adding a leading underscore, but you shouldn't. I am just showing you that technically you can, but you shouldn't, and even PyCharm is warning you, access to a protected member ID of a class. If we run the code, we see their IDs, 1 and 2. And we are adding that extra layer of protection by adding this leading underscore. We're telling other users that this attribute should not be used outside of the class. Great, so now you know how to define non-public attributes with a leading underscore. Great work so far! When you're ready, go to the next video so you can continue learning more about these principles. Welcome back! Do you remember that we mentioned the term name mangling just a few lectures ago? Well, now you're going to learn what this is all about. When we add 2 leading underscores, right here we have 2 underscores, to the name of an attribute or a member of a class, then the process of name mangling is triggered. It starts. This is a process by which the name of the attribute or of the member of the class is modified. What happens behind the scenes is this right here. The name of the attribute, which we have right here with the 2 leading underscores, is transformed through the process of name mangling into this. A combination of an underscore, the name of the class, 2 underscores, and then the name of the attribute. This is the basic format of the name of the attribute after the process of name mangling. So we're sort of like hiding the attribute even further. By convention, we just add one leading underscore, but when we add two leading underscores, we transform that name into this, which makes it even more difficult to access it. But it should only be used for special cases. Let's see what we can learn about this in the documentation. If we go to the Python documentation to the classes article and we click right here on private variables, we can learn more about name mangling. Particularly, we have to focus on this paragraph right here, since there is a valid use case for class private members, namely to avoid name clashes of names with names defined by subclasses. This refers to something called inheritance, which you will learn more about in a coming section. But for now, just focus on the fact that we are creating class private members. There is limited support for a mechanism called name mangling. Any identifier of the form, this form right here, which is the name of the attribute, and two leading underscores with at least two leading underscores and at most one trailing underscore, is textually replaced with this that we have right here. What you just learned, the name, the original name, is transformed into this. A name that contains a leading underscore, the name of the class, and two underscores followed by the name of the attribute, where class name is the current class name with the leading underscore stripped. This mangling is done without regard to the syntactic position of the identifier, as long as it occurs within the definition of a class. So if we have this attribute in a class engine serial number, and we add two leading underscores to its name, the process of name mangling is triggered to transform it into this right here. A leading underscore followed by the name of the class, two underscores, and then the name of the attribute. But it should only be used for special cases, okay? However, you can still access this attribute outside of the class, which is why the documentation says that no attribute is ever really private in Python. Please take a moment to think about how you can access this attribute. Remember that you shouldn't, but it is still possible technically with the new name. Pause the video and then come back so we can start writing the code. We're going to illustrate how the process of name mangling works with our backpack class. We define the class with the init method and our initial list of items. But now, instead of adding just one leading underscore, we are going to add two leading underscores to the name of the attribute. You can see that right here we have one and two leading underscores. After we have that, we know that it will not exist as an attribute with this name. It will exist with the new name that was assigned. We shouldn't access this attribute outside of the class, but I'm just going to show you this so you know that we can technically still access it, but we shouldn't. We're going to create an instance called myBackpack, and then we are going to try to print the value of the items attribute of the instance. You can see that there isn't an items attribute for this object. So if we run the code, we see that backpack object has no attribute items. How can we access this attribute then? If we add one leading underscore, we still see the error. If we add two leading underscores, we still see the error. So just by writing the same name that we wrote right here, we cannot access that attribute. If we run the code, we see that the backpack object has no attribute items. The name has been changed due to the process of name mangling. So how can we access that attribute? Well, we need to add one leading underscore and then write the name of the class. After we write the name of the class, we need to write two underscores and the name of the attribute. Now, if we save the file and we run the code, you can see this right here. You can see the empty list that is the value that we assigned to items. This name was changed to this name right here. Really awesome, right? So we can add some values right here to confirm that we are actually accessing this value in the output. We have a water bottle and a first aid kit. Let's run the code and we see this value, water bottle and first aid kit. We are accessing this value with a different name for the attribute. We add a leading underscore followed by the name of the class, 2 underscores, and then the name of the attribute. Awesome, right? You can technically access it, but you shouldn't. Remember that you shouldn't. When a developer adds 2 leading underscores or even 1 leading underscore, this is a red warning, a red sign that tells you please do not access or modify this attribute in your program. It is only meant to be used internally within the class. Finally, you have to know that name mangling is triggered when we add 2 leading underscores and a maximum of 1 trailing underscore after the name of the attribute. Adding 2 trailing underscores to the name of the attribute has a special meaning, so it doesn't actually trigger name mangling. This is reserved for something called magic methods or special methods, which you will learn more about in the coming sections. Great, so now you know how name mangling works behind the scenes, and that you should only use it for special cases. We usually rely on 1 leading underscore to define a non-public attribute. Welcome to this section. You will learn how to work with getters, setters, and properties. First, let's start with getters and setters. Getters and setters are members of a class. Particularly, they are methods. What are methods? Well, methods are like functions that are associated to a specific object or a class. They are like the functionality that the object can perform. In particular, getters and setters let us get and set the value of an instance attribute. They serve as intermediaries. Getters let us get the value of an attribute, like their name implies, and setters set the value of an attribute. Both of them help us protect the attributes by providing an indirect way to access them and modify them. So they serve as intermediaries. We are not accessing the data or the attributes directly, but indirectly through these methods. If we define getters and setters, we can make the attributes non-public by adding a leading underscore, and still we can provide a way to work with them indirectly. So from outside of the class, we cannot access them directly, but through the getters and the setters. Let's see how getters work in Python. Getters should be named with this format. This is the typical naming convention that we use. First, we write the word get, because we are going to get the value of an attribute. Then we write an underscore because we have to separate different words with an underscore, and then we just add the name of the attribute. And that is the basic format of the name of a getter. Right here we have some examples. Get name, get address, get color, get age, and get ID. These are all examples of getters for those specific attributes. Let's see an example in our code. Right here, we are going to define a movie class. And for that, we write the class header and the init method. In this class, we are going to add 2 instance attributes, title and rating. And they can be customized when you create the instance. But now, let's see how this is going to change when we write a getter for the class. Let's say that we want the title of the movie to be non-public. We just add a leading underscore to its name and we add a getter. How do we add a getter? Well, we just write the def keyword right here below init, indented, of course, so it belongs to the class, and we write the name of the getter, like for example, get title. Remember the format, the word get followed by an underscore and then the name of the attribute, title. Right here, within parentheses, we always have to write self, just like we wrote self right here as the first parameter in init. Then what are we going to get from the method? We are going to return the value of the title instance attribute. So as you can see, we're basically doing the same thing but through an intermediary. We are getting the value of this attribute and returning it when this method is called. Just like when we get a value from calling a function. Now, how can we get the attribute when we need to use it in our program? Well, to get the attribute, we just need to call the getter. And for that, we use dot notation again. Calling a method is very similar to calling a function, because we are executing or running its functionality. In this case, we will get the value of the attribute when we call the getter, and this is the basic syntax. First, we write the name of the variable that holds or references the object. Then we write a dot, followed by the name of the getter, which is get, an underscore, and the name of the attribute. And finally, we write an empty pair of parentheses, because getters do not take any arguments. Let's see how we can do this in our movie class to access the attribute. Great, so we've defined our getter in the class. It's time to create a movie instance. Let's call this my movie. We're going to create this instance, and the title is going to be, let's say, The Godfather. Rating 4.8. After we have our instance, let's see what changes when we have to access that attribute, when we need to access the attribute in our program. We can use the instance, right? But now if we try to access the attribute directly, you will see this error. Unresolved attribute reference title for class movie. This means that the instance or the object doesn't have a title attribute. If we run the code, we see this error. Attribute error, movie object has no attribute title. This is because right now we are defining a getter for that attribute. So instead of writing the name of the attribute, we need to call the getter to get that value. We say my movie dot get title, and we write an empty pair of parentheses to tell the program that we want to run this functionality. We want to call this method, and getters don't take any arguments. They just return a value. Now, if we save the file and we run the code, we see the value right here, The Godfather. This is the output from this line that calls the getter for the title. We can use this anywhere we need to in our program. For example, we could write my favorite movie is right here, and we are using that call as an argument to the print function. You can replace this, of course, with your favorite movie and try to experiment with this example. You can see this. My favorite movie is The Godfather. We see this value right here, the value that was returned by calling the getter. Awesome, now you know how to work with getters. So let's start diving into setters, and we will do this in the next video. Now that you know how to work with getters, let's see how you can define and call setters in Python. Setters are basically methods that we can call to set the value of an instance attribute. And what is the advantage of defining setters and using them instead of just changing the value directly? Well, that with setters, we can validate the new value before actually assigning it to the attribute. So we can check if the value is appropriate for the attribute before we actually make the update, and we can avoid making invalid updates. This is a huge advantage of using setters in your class. Basically, setters follow this naming convention. We write the word set to specify that this is a setter, followed by an underscore and then the name of the attribute. For example, set name, set address, set color, set age, and set ID. Now take a moment to think about how you would define a setter in a dog class to set the name of a dog. Let's say that you want to be able to change the name of your pet. Try to do this, pause the video, and then come back so we can start writing the code. Welcome back. Let's start writing our dog class. We write the header and then we are going to write our init method. Great, so let's say that after a careful analysis, we considered that the name of a dog should be a non-public attribute. So we add a leading underscore to its name. First, we are going to define a getter. Let's have some additional practice defining getters right here. We see getName, self is the only parameter, and we return the attribute self.name with the underscore. Now we have our getter. But now we have to define our setter. As you can see, the syntax is very similar to the syntax that we use to define a getter. We use the def keyword followed by the name of the setter, which follows this format, set followed by an underscore, and then the name of the attribute. Now, within parentheses, we still have to include self, but we are going to add a new parameter, new name. Why? Because we need to know what name will be replacing the old name. We have to take an argument to know what name we are going to set. Great! In the body of the method, we can make all the validations that we need before actually setting the name. Let's say that we want to check if the new name is a string. Well, we can use this function right here, isInstance. This checks if the name is an instance of the class string, of the type string. And we can also check if the name is alphabetical, like this. We are using the string method isAlpha. Only if these two conditions are true, we are going to replace the old name. If that is the case, we assign this new value to the attribute. But if this is not the case, then we are not going to update the value, and we are going to print this message. Please enter a valid name. You could handle this alternative scenario any way you like. You could print a message, you could do something with the attribute, you could assign a default value, anything that you like. Okay? It's up to you to choose how to handle if the name is not valid or if the attribute is not valid. Great, in our class now we have our getter and our setter. So let's define a dog instance. We say my dog. This is going to be, my dog will be named Nora. We have the instance. So first we are going to confirm that my dog's name is Nora. So let's write my dog is, and we're going to write the name of the instance followed by a dot, and then we are going to call the getter. Why are we calling the getter? Well, because we need to get the name of this dog instance. And then let's say that we need to update the value of the name. We want to change the dog's name. We just call the setter, like this. We write the name of the instance, the variable, then a dot, then the name of the setter, which is setName, and finally parentheses. But now we do have to pass a value right here. You can see that this part of the code turns yellow because it says parameter new name unfilled. We have to pass a value for this parameter in the setter, the new name. So we're going to change this from Nora to Norita. And after that, after we make that change, we can print the name of the dog again. But now let's customize the message. We say her new name is, and we call the getter again. Okay, so let's save the file and run our code to see what we get. We see this as the output. This is the output from this line of code. My dog is, at this point in the program, the dog's name was Nora, like we defined initially right here when we created the instance. On this line, we updated the name for the dog instance, and on this line, her new name is Norita. As you can see, the attribute was successfully changed. Awesome! But let's see what happens if this condition is not true. If the name is not valid and we do not update the attribute. Let's say that the name is not alphabetical. So for example, let's add this right here, a few numbers. If we save the file and we run the code, initially the dog's name was Nora, and we see a message that says, please enter a valid name. Then we see this message, her new name is Nora. The name was not updated, so the value of the attribute was protected by the intermediary, by the setter. We could also try to assign a value that is not a string and see what happens. Remember that we are also checking if the new name is a string. So let's see what we get. We save the file and we run the code, and right here we see this. My dog is Nora, please enter a valid name because the name was not valid, and the new name was Nora. It was not updated because this value was not valid. So you can see the amazing power of setters. They help us protect the attributes by providing an indirect way to change or update their values and access their values. Awesome! Now you know how to work with getters and setters. Welcome to this practical coding session. Now we will start diving into two examples of classes where we will define getters and setters. Let's start with our backpack class, and let's define our init method. We will have our initially empty list of items. In this case, we're going to make the items attribute non-public, or sort of like protected. And for that, to provide access to that value and to be able to update the value, we will have to define a getter and a setter. To define a getter, we first write the def keyword indented. Remember that this should be indented at the same level for them to belong to the class definition. Then we write the name of the getter, get, followed by an underscore, and then items, which is the name of the attribute. And within parentheses, we write self. What are we going to do? We are going to return the value of the items attribute. We write self, dot, and items with a leading underscore, like we have right here. This way, we are providing an indirect way to access the attribute. And we also want to be able to update the attribute. So we are going to define a setter, set underscore items. This is the basic format of a setter, but we also need to add something right here. We need to define a second parameter because we need to know or get the new value that will be assigned to the attribute. And we take that usually as an argument. So we have the new list of items. And what are we going to check? The items attribute is a list, so that should be preserved. We're going to check if the new items value that was passed as an argument is of type list. If that is the case, then we are going to assume that it is valid in this case, so we can replace the old value of the attribute. But if that is not the case, we will tell the user, please enter a valid list of items. And there you go. We have our getter and our setter defined for the items attribute. Great, so let's see how this works by creating a backpack instance. We say backpack, we create the backpack, and what are we going to do? Well, we are going to print the initial list of items through the getter. We are going to call the getter to get the list of items when we create that instance. Let's save the file and run the code. We see an empty list, which is exactly what we expected, the initial value. After we have that, let's call the setter. Let's update the value of the items list to a new list. Let's say that we have, for example, we want to have a water bottle, a sleeping bag, and a first aid kit. This will be our new list of items. So let's use a print statement right here and the getter again to print the list of items after this update. Right here we can see this. Initially we have an empty list, and after the change, the items attribute is updated to this new list, the argument that we passed to the setter. Great! Now let's see what happens if the argument is not valid. For example, if we write right here instead of a list, a string or something like that, a value of a different data type. Let's see this. First, we have an empty list. We see the message, please enter a valid list of items, and then we see the empty list again right here. The value was not updated. So we protected the integrity of the data, of the state of the object. And that is one of the main advantages of using getters and setters as intermediaries to update and get a value. Great, so now let's go to our second example. We're going to define a circle class. And in that class, we're going to define our init method. This time, we're going to take the radius of the circle as an argument when we create the instances, and we are going to make this attribute non-public. For this attribute, we're also going to define a getter and a setter. Try to do this. Try to define the getter and the setter for the radius attribute. In the setter, you need to check if the radius is of type float. Let's say that we want to represent the radius as a float, so we want to check if it is a float and if it is greater than 0. These are the validations that you need to implement in your setter. Think about this for a moment, pause the video, try to write the code, and then come back to complete our class. Welcome back. First, we need to define the getter. We write def, getRadius, self, and we are going to return the value of the radius attribute with a leading underscore right here. Now we have our getter. Our setter has a few more details that we need to implement. First, we need to get the new radius as an argument when we call the setter. And we need to check if the new radius is an instance of float, if it is of type float, and if it is greater than 0. Remember that we are not going to take values equal to 0 or negative. If that is the case, if all these conditions are true, then we can update the value of the radius. But if that is not the case, we can say, please enter a valid value for the radius. You can customize this message to your liking. Great, so now we have our circle class with a getter and a setter. Great work! Let's see how this works by creating an instance. Try to do this yourself. Create an instance, then call the getter, call the setter to update the value, and then check if the value was updated. Pause the video for a moment, try to write this in your code, and then come back so we can do this together. Welcome back. Now we're going to create a circle instance. So in this case, since we're expecting a float for the radius, I am going to pass the value 5.0. Okay? So we can confirm if the value of the radius is actually 5.0 by calling the getRadius getter. And we can see 5.0 right here as the output, so it is. After this, we can change the value of the radius by calling setRadius. In this case, we are going to change the value of the radius to 10.5. And then we are going to call the getter again to confirm that this change was successful. Now, if we save the file and we run the code, we see this. Previously, the radius was 5.0 and now it is 10.5. Awesome! But what happens if we pass a value that is not valid? For example, the radius has to be greater than 0. If we pass a radius that is equal to 0, we will see this message. Previously, it was 5.0 right here, and then we see this warning message. Please enter a valid value for the radius. And after that, we see that the radius was not updated because this condition was false. The radius was not greater than 0. And we could also try to update the radius with an invalid value like this one with a string. What do we see? Well, we see that the attribute is not updated, exactly what we needed. We see please enter a valid value for the radius. This time, this part of the condition was false. The radius was not a float. Great, so now you know how getters and setters work, and you had some practice with these examples, defining them and calling them in your programs. When you're ready, go to the next video so you can start learning the Pythonic way of working with getters and setters. You will commonly see getters and setters in programming languages like Java, but in Python we use something called properties. You will learn more about them in the coming video, so I'll see you there. Now that you know how to work with getters and setters, let's start diving into properties in Python. Getters and setters are very commonly used in object-oriented programming because they help us follow and implement the principle of encapsulation, showing only the attributes that we want to show to the outside world. But in Python, we typically don't work with getters and setters, at least not directly, because we have a better alternative. Let's see why. If we have a very simple dog class with an age attribute that we have used in many different parts of our program or project, and then, after writing the program, we are asked to validate the age before assigning it to the attribute, then based on what you have learned so far, we would have to make the attribute non-public by adding a leading underscore and then define a getter and a setter for that attribute, right? This is what you have been learning so far. In that case, the class would be similar to this that we have right here. We have the init method, we have the getter, and we have the setter that checks if the age is an integer and if it's greater than 0 and less than 30. The problem is that we already use the traditional syntax to access and update the attributes in our program. Like this, we are accessing the attribute with dot notation and we are updating the attribute using a typical assignment statement with the dot notation right here. So this will throw an error everywhere that we use this syntax. If we do this, if we change this to non-public and we add getters and setters, we would need to replace all of these lines of code in our program by calls to the getter and to the setter. And that would not be practical or realistic if we are working with a large and more complex project. We have a better alternative. First, let's start by writing the class and seeing the effect that this change has in our code. Let's define our dog class right here with an init method and the age attribute. We have our class and now we are going to create our dog instance. We have to specify the age of the dog. So we're going to use some attributes of the dog in our program and we are also going to update its value. We say my dog is, we are going to access the age of the dog directly using dot notation, years old. And 1 year later, we are going to update the age by incrementing it by 1 directly. And then we say, my dog is now years old. Okay? We are accessing this value twice using dot notation and we are also updating the value. But what happens if we are suddenly asked to validate the age? In that case, according to what you have learned so far, we should add a leading underscore and define a getter and a setter. So let's do that. Get age, return self.age, and then set age. And we write here new age, self.age equals new age, but now we have to validate the age. Let's check if the new age is an instance of int, if it is an integer, and if the age is between 0 and 30. Let's say that this is a criteria that we were asked to implement in our code. If this is the case, then we update the attribute. If this is not the case, then we have to print a descriptive message. Please enter a valid age, like this. So now we have our getter and our setter and our non-public attribute. Awesome. So initially you might think that this solves the problem. Now we are validating the age. But the problem is what happens with the code that we already wrote in our project. Right here, the code that is not part of the class. The class was modified. But right here, we are using the age attribute in several places in our code. And right here, we are seeing them in yellow, highlighted in yellow, because now the dog object doesn't have an age attribute. Remember that we made this attribute non-public, and now we can only access it by calling the getter. We would have to replace right here, everywhere where we access the age attribute, we would have to replace this by a call to the getter. And where we update the attribute, we would have to replace it by a call to the setter. In this case, it might seem simple enough because we only have to make 3 small changes, but imagine if this happens in a large project with thousands of lines of code. We will have to change this in every single place in our code where we access or modify the attribute, and that is simply not practical. But before you panic, let me tell you that we have a really awesome solution for this in Python. They are called properties. We can define a property in the class using the property function. We just need to specify the getter and the setter that we want to assign for that particular property, and assign the result or the object returned to a particular variable right here, which will be the property name, this right here. Let's do that in our code so we can add this property and see the effect that it has in our code. To solve this problem, we just need to create a property in the class. Let's see how you can do that. We have our class with a getter and a setter. So right here, after the getter and the setter, we can define the actual property that we want to create. We want to be able to access this attribute with the same name, age. So we're going to define the age property right here. And as arguments, we need to pass the name of the getter and the name of the setter. We write getAge and setAge. Now we are connecting this property to these two methods, the getter and the setter. We have to specify them in this order, okay? Now, if we see the code that we wrote previously before we added the getters and the setters, we can see that the yellow warnings disappeared, because now the dog object has an age property right here. If we hover over the name, we can see this. Property age of main dog. Okay? We can access and modify the attribute with the same syntax, but now we have the getter and the setter acting as intermediaries. Now everything is working correctly. When we define a property in Python, we can use the same syntax to access and modify the attributes, just as if they were public, but we are still using the intermediaries, the getters and the setters. The getter and the setter will be called behind the scenes for the corresponding operation. For example, when we try to access the attribute using dot notation, the getter will be called. And when we try to update the value of the attribute, the setter will be called. Let's see this in our code, and let's use print statements to confirm that they are actually called behind the scenes. And we say, calling the getter, and then we can say right here, calling the setter. And these print statements will run whenever we call these methods. Let's save the file and run our code and see the output. Let's analyze the output line by line. We say calling the getter because right here we have to access the age attribute of the dog instance before we actually print this message. My dog is 8 years old. This value has to be retrieved or known before printing the message. Then we print 1 year later, and we are calling right here the getter again and the setter and the getter. Why? Right here, we have to get the value of the object, so we can update it. Right here, remember that this is equivalent to doing this. My dog.age plus 1. So first, we have to get the attribute, the value of the attribute by calling the getter. Then, since we are updating it with this assignment statement, we have to call the setter. And then right here, for this message, we have to call the getter again to print the final message. My dog is now 9 years old. You can see that the value was successfully updated. This is just a more concise syntax. So this confirms that we are actually calling the getter and the setter behind the scenes, when we use the same syntax that we used when the attribute was public. Awesome! Now you know how to work with properties in Python, using the property function. Welcome to this practical coding session where we will define properties in our circle class, so let's get started. First, we have to define our circle class, and now we are going to define two instance attributes, radius and color. But in this case, these two instance attributes will be non-public, so we are going to add a leading underscore. First, let's start with the radius. We are going to create a property for the radius. So for that, we need to define a getter and a setter for that particular attribute. We say getRadius with only self as the argument, and for that we have to return the radius. So we have the getter. Now let's define the setter. We're going to take the new radius as an argument, and we are going to check if the new radius is greater than 0, then we are going to accept it. Okay? Alrighty, let's say that we're only going to take integer values for the radius. So we could assume that it is an integer, or we could check if it is an integer in our condition as well, okay? If that is not the case, then we just print the message, please enter a valid radius. Awesome, so now we have our getter and our setter for the radius. How do we define the property? Try to define the property right here. The property's name will be radius. Try to complete this line of code with the property. Pause the video for a moment, write this line, and then come back. To write this line of code, we just need to call the property function, passing the name of the getter as the first argument and then the name of the setter, like this. And voila! Right here we will have a property named radius. So we can use the same syntax that we used before to access the radius attribute. And we will have the benefits of these two intermediaries to protect the data and the value of the attribute. All of this code was written to protect the radius attribute. But now we also want to create a property for the color. And how can we do that? Well, right here below this property, we will have to define a getter for the color, like this. And then we have to define the setter for the color. And we take the new color as the argument. But in this case, we're going to do something a little bit different to check if the color is valid. We want to check if the new color is in a list of valid colors. And where can we find that list? Well, we're going to define a class constant. A class constant is just like a class attribute, but we use a naming convention of writing the name in uppercase letters to specify that we don't want to change that value, that the value should be treated as a constant, because Python doesn't really implement constants. We use this naming convention of writing the name in uppercase letters to tell other developers that this should be treated as a constant. So we're defining this constant as a tuple to protect these values even further. Tuples are immutable, so they cannot be changed. And we specify the 3 valid colors for the circle: red, blue, and green. What are we going to do right here in the setter? We're going to check if the new color that was passed as the argument is in the list of valid colors. So we write circle.validColors. This is a class constant, a class attribute, a class member, so we can use the name of the class dot the name of the attribute. If that is true, if that is the case, then we are going to update the color with the new color. But if that is not the case, then we just print, please enter a valid color. And we don't update the color. Awesome, so now we have our getter and our setter, and it's time to define the property. The property will be named color. Just like the attribute, this is very common, and you should usually name your property the same as the attribute that you're trying to protect or shield from the outside world. Try to complete this line right here. Define the property with the getter and the setter. Pause the video and then come back. Welcome back. To define the property, we use the property function and we pass the name of the getter and the name of the setter right here. And we will have our color property defined. Awesome, now we have our class with 2 properties, a radius property with the getter and the setter, and a color property with the getter and the setter. So let's go to our main program, and we say, my circle, we're going to create a circle instance with a radius of 10 and color blue. Right here, okay, radius and color. And blue is one of the valid colors. So let's see what happens with the radius. We're going to first print the radius to check if it was assigned correctly. Let's save the file and run the code. And we see the value 10 right here for the radius, which is correct. After that, let's say that we want to update the value of radius to 16. Right here, we are calling the getter, and right here on this line, we will be calling the setter. If the setter was called appropriately, then the radius should be updated correctly. We save the file and we run the code and we see that the value was updated. From 10 right here, it is 16 right here. And if we try to update it to an invalid value, we just see this message, please enter a valid radius, and the attribute is not updated, so it is being protected by the setter. Great, so now let's test this with the color. So we say myCircle.color, and then let's say that we want to update the color to red. Previously it was blue, we want to change it to red, which is one of the valid colors. And then let's check the color after this change. First, let's comment these lines of code. Let's comment them out so we can see just the output for these 3 lines of code. And we see blue and red. The color was updated successfully. Previously, it was blue, and now it is red. If we try to assign a color that is not in the list of valid colors, like for example white, then let's see what happens. We see blue, please enter a valid color, and then blue. The color was not updated because this was not a valid color. It was not in the list that we defined right here as a class constant. The add property decorator is really amazing. We get the same functionality that we got when we used the property function, but with a much more concise syntax. We just need to write add property, and a special process will start behind the scenes. Let's see this in detail. First of all, what is a decorator? A decorator is basically a function that takes a function as an argument and extends its behavior without explicitly modifying it. That is why we call it decorator. It is sort of like decorating another function by extending its behavior. But it doesn't explicitly modify the function, it just adds some extra flavor or functionality to the function. The new syntax that you are going to learn right now using the add property decorator is cleaner and it is more compact. So we typically use it in Python. We avoid working with getters, setters, and with the property function whenever possible. We use this syntax that you're going to learn. It is also easier to read and understand, and it avoids calling the property function directly. We will also reuse the name of the property if we use the add property decorator. So we avoid adding new names like the name of the getter and the name of the setter to our list of valid names in the class. This is basically how you can define a getter using add property. You can see add property right here at the top. First, you write add property, and then you basically use the same syntax that you would use to define a getter. We have the def keyword followed by the name of the property that you want to create. Right here, instead of writing get and the name of the attribute, we are just writing directly the name of the property. If we have, for example, an age property, this would be age. If we have price, this would be price, and so on. Then we have self as the only parameter, because this is a getter. And in the body of the method, we have a return statement that returns the actual attribute. Usually that attribute will have the same name as the property that we write right here, just with a leading underscore, because it is non-public. Let's see this with an example. Right here, we are going to define a movie class, and we are going to define right here the init method with two instance attributes, title and rating. We're going to keep this class simple so we can focus on the syntax of add property. We define these two instance attributes, title and rating. And let's say that we want to make the rating be a non-public attribute, like this. So how can we use the add property decorator to define a getter and a setter for the rating? We just write add property right here, and then we start writing our getter. Instead of writing get rating, we will just write rating, the name of the property that we want to create. And in the body of the getter, we will just write what we usually write in a getter, return the attribute. The main changes are this right here that we have to add before the first line of the getter, and that the name of the getter is the name of the property, not a name that we create like getRating. Okay, so now we have our getter. Let's test that the getter actually works like we expected by creating an instance right here. Let's say favorite movie, and the title will be Titanic with a rating of 4.3. To test if the getter is working correctly behind the scenes for the rating property, we just need to access the rating of the favorite movie instance. To check that this is actually being called behind the scenes, we can also add a print statement and print calling the getter. So let's save the file and run the code. And right here we see exactly that. We see the message that we print right here, calling the getter. So in this line, when we try to access the rating, we are actually calling this behind the scenes. We see this message calling the getter, and we get the rating and print it on this line right here. We can also define a setter with the add property decorator, like this. We just need to write add, followed by the name of the property that we use, the property that we created with a getter. Remember that previously we were writing a getter. That is the name of the property that we created. Then we use that name, we write a dot, and then the word setter. This tells the program that this is the setter for this particular property. And then we use the same syntax that we would typically use to write a setter. The def keyword followed by the name of the property. Right here, instead of writing set and the name of the attribute, we are just writing the name of the property directly. And in the list of parameters, we have self and the new value that we are going to take as argument. In the body of the method, we see the same assignment statement that we would typically see in a setter. And we could also implement code to validate the value before assigning it, to check if it's valid, and to handle cases where it is not valid. Let's see this and how we can write a setter using this syntax with an example in our code. Our getter is working correctly, so now let's define a setter for the rating. How can we do that? We usually write the setter below the getter, so let's do that. Let me zoom in so you can see all the details, because setters do have some small changes. We have to write an add symbol and then the name of the property for which we are creating the setter. In this case, the property is named rating. So we write rating right here, followed by a dot, and then the word setter. Great. After that, we just write what we would usually write for a setter. The only change is that instead of writing set rating, we just write the name of the property for both the getter and the setter. These decorators are telling the program which one is the getter and which one is the setter. And right here, since this is a setter, we need to take a value, the new rating, that we are going to set. And what are we going to do right here? We are going to check if the new rating is greater than or equal to 1.0 and less than or equal to 5.0. If this is the case, then we can update the rating with the new rating. But if this is not the case, then we can print the message. Please enter a valid rating. We could also check if the new rating, is an instance of float. So we're basically implementing the functionality that we implemented in a setter, but we are using right here a different syntax to define the header. Let's see how this works, and let's check that this is actually being called behind the scenes with a print statement. We say calling the setter, and let's try to update this right here. We say favorite movie dot rating, and let's change this to 4.5. After that, we are going to check if the rating was updated successfully. Let's save the file and run the code. And right here we see this. We are calling the getter, and then we print the rating, 4.3. After that, we have to update the value. We call the setter because we are updating the value to 4.5. This assignment or update of the value is calling this method behind the scenes. And right here, finally, we are calling the getter again, and we are printing the rating, 4.5, which was updated correctly. Now let's say that we want to change the rating to an invalid value. We have a bug or something that is not correct in our program, and it tries to update the rating to a negative value. Let's see what happens. You can see that the rating is not valid. We say calling the getter, 4.3, calling the setter, please enter a valid rating because this one is not valid. And then when we call the getter again, we see 4.3. So the rating was not updated. It was protected by the setter that we have right here. Awesome, now you know how to define a getter and a setter using the syntax add property and then add the name of the property dot setter. Remember that you don't use the names getRating and setRating. You just use the name of the property that you want to create, and you will be able to use the same syntax that you use outside of the class. Awesome work! When you're ready, go to the next video. I will see you there. Welcome to this coding session. In this example, you're going to practice how to define a getter and a setter with the add property syntax. Let's start by defining our backpack class. And right here we have our init method and our initially empty list of items. Now, based on what you've learned, try to write a getter and a setter using add property for the items attribute. Pause the video for a moment, try to write this yourself in the code, and then come back. Remember that you have to check if the list of items is actually a list in the setter. Welcome back. First, let's start writing the getter. And for that, we need to write add property before the header. Then we have to start writing the method. We use the def keyword and then the name of the actual property that we want to create. This is the same name as the non-public attribute, usually. And then we are going to write the same line of code that we would write for a getter, which is returning the value of the attribute. Now we have our getter. Great work. So let's start writing our setter. For the setter, you have to write the name of the property, which is items. And then you have to write the word setter. The name of the property, dot setter. After that, you write the first line of the setter. But the name is the name of the property. You reuse the name of the property for both the getter and the setter. Okay? We also have to take the new list of items as an argument. And we check. If new items is a list, then we can make the update. Awesome. If it's not a list, then we just print, please enter a valid list of items. Great, so now we have our getter and our setter. And notice how this syntax is much more concise than when we use the property function. Let's create a backpack instance right here below. And let's check that they're actually working like getters and setters. We say my backpack.items. Remember that we can use the same syntax that we used before. Dot the name of the property. And the getter and the setter will act behind the scenes. We're going to get the value of the items, and then we are going to update that list. We're going to include a water bottle and a sleeping bag, like this. And then we are going to print the list of items to check if it was updated successfully. But before we do that, before we actually run the code, let's add print statements to confirm if the getter and the setter are being called. We say calling the getter, and right here we write calling the setter. Okay? We save the file, we run the code, and right here we see this. Calling the getter, we see the empty list of items right here. We call the getter because right here we are getting the value of the items property. Then we are calling the setter because we are updating that value with the setter. And then we are calling the getter again to print the updated value. This one right here, water bottle and sleeping bag, are the two items that are now in our list of items in the backpack. Great, so let's see what happens if we try to assign an invalid value for the list of items. We see that the value is not updated. We just see a warning. Please enter a valid list of items, and the value is protected. Great, now you know how to work with add property in Python. And you can define a getter and a setter for your property and use the same syntax that you use outside of the class. Great work so far during the course! Welcome to this section. Now we will cover methods. Methods are fundamental building blocks of the classes that we write in object-oriented programming. Do you remember that a few sections ago we mentioned that a class defines the state and the behavior of an object? Well, in this section, by covering methods, you will be learning how to define the behavior of the object, because so far we have been focusing on the state, the attributes of an object. We can define a method as a function that is associated to an object of the class or to the class itself. The methods defined in a class will determine the behavior of the objects that are created from the class and how they can interact with their state and with other objects. So we're basically defining all the actions that the object can take. There are three main types of methods: instance methods, class methods, and static methods. In this section, you will learn how to work with instance methods. Instance methods, in particular, are methods that belong to a specific object because they have access. They have access to the state of the object that is calling them. And how do these methods get access to the internal state of the object? Well, through self. Through this parameter that we have been writing so far as the first parameter in every single method that we've defined in our class, like init, like getters, and setters. Remember that in a previous section we said that self refers to the object or the instance. Well, in the case of a method, it refers to the instance that is calling the method, that is asking to execute its functionality. Calling a method is very similar to calling a function, because we are asking the program to run its functionality or to execute its lines of code. But this time, it is a specific object that will be calling the method. Let's see what we can learn about methods in the documentation. Right here, we can go to the official documentation where it says classes. We go to the article that covers classes, and we click right here in section 9.3.3 Instance Objects. We click on it, and right here we can see a short description of the instance objects that an object can contain. In this paragraph, we see a short description of what a method is. So let's read it. The other kind of instance attribute reference is a method. A method is a function that belongs to an object, just like you learned in the definition right now. In Python, the term method is not unique to class instances. Other object types can have methods as well. For example, list objects have methods called append, insert, remove, sort, and so on. And I'm sure that you've used these methods before. However, in the following discussion, we will use the term method exclusively to mean methods of class instance objects, unless explicitly stated otherwise. So the key takeaway from this article is that a method is a function that belongs to an object. You will learn how to define these functions, how to call them, and how to work with them in your code. In a general overview of the class structure, this is a typical class in Python, methods are defined below the init method, after the init method in the class. So right here, we would have our first method and then as many methods as needed for the class. And they also have to be indented to the same level as the init method and the class attributes so they can belong to the class. If a method is not indented, then it's not considered part of the class anymore and it is considered a regular function from the main program. This is the basic syntax that we need to use to define a method. First, we have the def keyword followed by the name of the method. And right here we have the list of parameters, including self and as many parameters as needed. Just like when we define a function, we can define as many parameters as we need. Of course, they have to be separated by a comma, and it is recommended to add a space after the comma. This is recommended in the Python style guide. You shouldn't need to add many parameters to this list of parameters, and if you do need to, there is usually a way to redesign your code to reduce the number of parameters in this list. Method names usually include verbs, since they represent the actions of an object. When we identified classes in a problem statement, remember that we identified the nouns. Well, now methods will be identified through the verbs, because they represent the actions that an object can take. For example, a calculator class may have these methods: add, subtract, multiply, divide, and other operations. A deck class, like in a deck of cards for blackjack or for war, will have methods like this ones: build the deck, show the deck, shuffle the deck, draw a card, and other operations that are important for that particular object. Let's see the naming conventions for these methods. How should we write their names? Let's see this in the Python style guide. Let's see what it recommends. If we go to PEP 8, the style guide for Python code, we can learn more about how we should name methods in a class. We just need to go right here to naming conventions and method names and instance variables. Let's see what it says. Use the function naming rules for methods and instance variables. write them in lowercase with words separated by underscores as necessary to improve readability. And we should use one leading underscore only for non-public methods and instance variables. So you can see that this naming convention of adding one leading underscore for non-public members still applies for methods as well, not just for attributes. So if you want to make a method non-public, you should add one leading underscore to its name. So, based on what you just read, this is the typical format for a method name. We write it in all lowercase letters with the words separated by an underscore. This naming convention is called a snake case. And it is the same naming convention that we use for function names and for variable names. Now let's see an example of how you can define a method in Python. We will define a method in our circle class. First, we write the class header and then we write the init method. In this case, so we can focus on the methods, we're just going to add one instance attribute, the attribute that we need to implement our method, which is the radius. Our method is going to find the diameter of the circle, which is twice the value of the radius. We're going to take this attribute and we're going to use it to find another value. It will be a function associated to a circle object. And how can we do this? First, we use the def keyword, just like we did when we defined getters and setters and when we define init. Now we write the name of the method. In this case, we call it find diameter. We could also name this calculate diameter or get diameter or print diameter, anything that describes the functionality and the effect of our method. Of course, for instance methods, we always have to add self as the first parameter. And then right here, with one level of indentation to the right, we write the actual code that we want to run when this method is called. So let's say that we want, in this case, to print the value. And we say diameter. We have an f string, so we can write this right here, self.radius times 2. And what will this do? Well, this will print this message. This message is an f string, so this will be replaced by the actual numerical value. The radius will be replaced right here, it will be multiplied by 2, and then that value will appear right here after the word diameter. This line of code will run whenever we call this method with a circle instance. Another alternative could be returning a value. You can return a value from a method just like you return a value from a function. Using the return statement, and you just write the value that you want to return. In this case, it would be the radius of the instance multiplied by 2. Awesome, so let's go back to our initial version where we print this value. And this is how you can define a method in a Python class. Awesome, you know the basic syntax now. If you need to add a parameter for this method, you would just add it like we added the second parameter in the setter. We would do something like this. We write a comma, a space after the comma, and then the name of the parameter. And as many as we need to. Welcome to this coding session and this practical example. In this case, we're going to work with our backpack class, but now we're going to add some functionality to our class. So we will be able to add items, remove items, and check if an item is in the backpack. Well, so let's get started. First of all, we have to define init to assign an initially empty list of items to the backpack. We will also provide a getter like we have right here, like you learned in the section where we covered properties. We want to create a read-only attribute, a read-only property with only a getter. We want to be able to add an item to the backpack. So for that, we just need to write or create or define a method called addItem in our class. It has to take self as the first parameter, and then the second parameter can be, for example, item, the item that we want to add. What do we want to do with that item? Well, first of all, we want to check if the item is a string. So we can check this with the isInstance function. We say item and then string. If the item is a string, then what do we want to do? Well, we want to append or add that item to the list of items in the backpack. This one right here. When we create the backpack, that list is initially empty. But if we want to add an item, we will have to append it to this list. Okay? So that is the power of self right here, that we are taking it as a parameter. Just like we use self right here to create an attribute, we use self as well to work with those attributes in our methods. If this is not the case and the item is not a string, then we could, for example, write this message. Please provide a valid item, or please enter a valid item. Great, we have our add item method. Now take a moment to think about how you would implement the remove item method. You know the basic syntax? This line right here, you just have to adapt the name to remove item and then try to implement the body of the method. What do we have to do to remove an item from the backpack? Think about this for a moment, pause the video, and then come back. Welcome back. So to define this method, we have to write the def keyword and then the name of the method, remove item. We also have to add a second parameter because we want to be able to specify what item we have to remove. If the item is in the backpack, so if it is in the list of items of the backpack instance, then we have to remove it from that list. We take the list and then we call remove. And what are we going to remove? That item that we received from the method call. Now, what happens if the item is not in the backpack? Well, we have nothing to remove. We can, and it is very common, to return a particular value that indicates the user or the object that called the method whether the operation was successful or not. For example, if the item was in the backpack and it was successfully removed, then we can return the value 1, for example. And if this is not the case, if the item was not in the backpack, then we could return 0. And this is an example of a method that actually returns a value. You will see how this works when we start calling methods, and you will see how you can store this value and use it in your program. Great, so we have our 2 method definitions. We only have to implement our third method right here. In this case, this will be a short method, hasItem. It will return true if the backpack has the item and false otherwise. What do we want to return in this case? We want to return true if the item is in the list of items, like this. This expression will be true if the item is in this list, and it will be false if the item is not in the list. So we can just return this value directly. And we have a method with just 1 line. That is really awesome, right? We added functionality to our backpack. And we will use that functionality when we reach the part of the section where we start calling methods and using them in our program. Once we have our method defined in our class, we will need to actually call the method to tell the program that we want to execute it or run its functionality and its lines of code. Previously we said that calling a method was very similar to calling a function, but there is a small change in the syntax because instance methods now belong to the actual objects that we create from the class. So since they belong to the objects, we need to specify the object before the dot. Right here, we are using dot notation. As you can see right here, we have the dot. After the object, we write the dot and the name of the method. Then after the name of the method, we write within parentheses the list of arguments or values separated by a comma and by a space after the comma. Let's see these examples. I'm sure that now with these examples you will realize that you've actually been working with object-oriented programming since you started learning how to code in Python. Let's say that I defined right here a list, 4, 5, 6, 7, and 8. This is an instance of the list data type, of the list class, and basically everything is an object in Python, so this is an object as well. I'm sure that you must have written this like 1,000 times. This is just a line where we add an element, the element 14, to the end of this list. Well, let me tell you something. This is an example of calling a method. Yes, that's right. We are writing a list object right here, the variable that references that object in memory, followed by a dot, then the name of the method, which is append, and then we pass one argument, which is required by the method, 14, because we need to specify what element we want to add. Similarly, there are other methods that do not require any arguments, like for example, sort. If we call the sort method on the list object, we just need to write empty parentheses because we don't have to pass any arguments. This method will just sort the list in ascending order. In this case, it's already sorted, but it would sort it in ascending order. Then append takes one argument, and there are other methods that require other data types as arguments. For example, the extend method to add those elements to the original list, to this list object that we have right here. So as you can see, methods are very versatile. They can take as many arguments as we need, and these arguments can be of any data type that we need. Let's add some print statements to see the effect of these methods on the list object. Right here, we can see the 3 different stages of the evolution of the list in the program. We have the original list, and after that we sort it, which in this case leaves the list intact. Then we append the value 14, and then we extend the list with the values 1, 2, and 3. When we return a value from a method, we can assign it to a variable. In this case, we are calling the pop method of the list object. This method doesn't take any arguments, and it returns the last value in the list. Since the value is returned from the method, it is not printed, it is returned, we can assign it to a variable. In this case, we are naming this variable number, so we can print that value. Now if we run the code, we see this value right here, the value 3. The last value in the list was returned by the method, and it was at the same time removed from the list. If we print the list right here, we can see that it doesn't have that element after it is popped. This is an example with a list, but I'm sure that you've also worked with string methods and dictionary methods and tuple methods and all types of methods for the built-in data types. In this section, we will focus on writing methods for our custom classes that we define in our code. For example, right here, if we are working with a class that we defined, a circle class, and we have a circle instance, let's say that we want to call the find diameter method, then we would just write the name of the variable that holds or references the circle instance, followed by a dot, and then the name of the method. After the name of the method, we would write empty parentheses, because in this case, no arguments are needed. Let's try this in our code with a circle class. Right here, we have our circle class with the init method, and we have the find diameter method. Now you're going to learn how to call methods from classes that you have defined. Let's create an instance, my circle, like this, and its initial radius will be 5. How can we call a method from the class? How can we, for example, find the diameter of a circle? The basic syntax is this one right here. We write the name of the variable followed by a dot, and then we call the method like this. We write the name of the method and parentheses. If the method takes any arguments, then we pass those arguments. But if it only takes self, then we don't have to pass any arguments. Self is like skipped from the list of arguments, just like we skip self from the list of arguments when we create the instance right here. The same happens with the method, because actually behind the scenes, this instance is assigned as the value of self, a reference to this instance in memory. So we don't have to specify it ourselves within parentheses. Great, so now we see in the method definition that the value is returned by the method. So for us to use it, we will need to assign it to a variable. We say, for example, diameter. And if we print that variable, we will have access to the value, and we can use it anywhere in our program. Let's save the file and run the code. We see this right here, the value 10. The radius was 5 and the diameter is twice the radius. So the value is correct. We called the method right here from myCircle instance. The value of the radius of this instance was used for the calculations, and we got the value that was returned by the method, so we could use it in our program. And this is how you can call methods defined in your classes. Welcome to this example. Now you will practice how you can call a method of a class by working with the backpack class. Remember that in a previous video we defined these three methods: add item, remove item, and has item. So we will see how they work and how you can call them and use them in your program. First of all, we have to define a backpack instance, like this. After we have our instance, we are going to print the initial state of the items attribute or property. We want to confirm that the items list is initially empty, like we have right here. So we've confirmed it. So far, so good. Now, what do we want to do? Let's say that we are preparing for a camping trip. The first thing that we want to add to the backpack is a water bottle. We take the backpack instance, and then we have to add an item to the backpack. We use dot notation for this purpose. We write the name of the variable that references the object, then we write a dot and the method, the name of the method, and any arguments that it requires, of course. This one requires the item that we want to add to the backpack, right here. So after we add the item, we want to print the state of the list again. We want to see how many items are in our backpack. We see that before it was empty, and now we have one item, which is a water bottle. After that, let's say that we want to add another item. Try to do this yourself. Add the item a sleeping bag to the backpack. Pause the video, write this line in your code, and then come back. Remember, a sleeping bag. Welcome back. So let's add this item. And after that, we are going to print the state of the list again. We want to see how it is working. Well, we have an empty list, and then we have a water bottle and a sleeping bag. So our backpack is actually looking like a backpack for someone that is going camping. And that is really cool. Let's say that a friend is asking us if we have the water bottle in our backpack. How can we check this? Well, by calling the method hasItem that we defined right here. With this method, we can check if a particular item is in the backpack or not. So let's do that. My backpack.hasItem and water bottle. Let's save the file and run the code, and you will see something very peculiar right here, very interesting. We see the list of items in 3 different states, but right here we don't see any output coming from this line. We don't see true or false, and why is that? Well, because if we go to the method definition, we actually have a return statement right here. We are not printing true or false. We are returning the value. So, since we are returning the value, we have to assign the value to a variable to be able to work with it in our program, or use it directly. But in this case, we're going to assign it to a variable. The variable will be hasWater. Okay, this will be true or false. And now we do see the value true right here. We see the 3 states of the backpack, and then right here we see true, printed as the output. This method call returned the value true. We assign the value to the variable, and then we print it. After our camping trip, we will want to remove the items from the backpack. And how can we do that? By calling the removeItem method. What do we want to remove first? Our famous water bottle. So after we remove that water bottle, we are going to check if it was removed. Right here, we can see that it was removed successfully. Previously, we had a water bottle and a sleeping bag, and now we have a sleeping bag in our backpack. So that is the only thing left to remove. Sleeping bag right here. And then we are back to an empty backpack, like we had when we started. We removed the 2 items. Let's also see what happens if we try to remove an item that is not in the backpack. For example, candy. And we print it. Let's go to our method definition to see what could happen right here. We say if the item is in the backpack, if it is in the list of items, we remove it. In this case, if it's not in the backpack, we return the value 0. We could potentially also display a message saying this item is not in the backpack. Okay, and return the value 0 in case we need to use that value for some operation. If we save the file and we run the code, we see that the item is not in the backpack, and we still have an empty backpack after we call this method. Great, I hope you liked this example and that you found it helpful to practice calling methods of your class. You can see how your classes are starting to grow in complexity and functionality, and they are becoming more powerful. Great work so far during the course. If you need to, you can also assign default arguments to the parameters of a method. These act like default values that we assign in case we omit the arguments. Let's see them in detail. You just need to add an equal sign and then the value that you want to assign by default to the corresponding parameter. Right here, we would write the name of the parameter, and right here, the value. Like this. The parameter or parameters with default arguments have to be at the end of the list. They must always be at the end of the list, okay? Otherwise, you will get an error. Let's see what the Python style guide recommends for writing or defining default arguments for our parameters. We can find more information about how we should assign default values to the arguments by going to PEP 8, the style guide for Python code. Right here in the table of contents, we just go right here to white space in expressions and statements, and we click on other recommendations. If we scroll down, we will quickly find this part of the documentation where it says, don't use spaces around the equal sign when used to indicate a keyword argument or when used to indicate a default value for an unannotated function parameter. That is exactly what we have right here. Annotations in Python are a completely different topic, but what we are using right here is an unannotated function parameter. When we indicate a default value for that type of parameter, we shouldn't add spaces around the equal sign. Now think about a player class with 4 methods: move up, move down, move left, and move right. Each one of those methods should have 5 as the default value for the increment in their x or y coordinate, increment or decrement depending on where you are moving, okay? Try to implement this in your code, in your class. Pause the video for a moment, try to write the code, and then come back. Let's write our player class. We're going to do this real quick, the init method, and we're going to define the x and the y instance attributes for each player. Let's say that we are representing a player for a video game where we have a coordinate system. Let's start defining our methods: move up, move down, move left, and move right. We're going to start with move up. By default, instance attributes should always have self as the first parameter. But now, for a second parameter, we will have to specify how much we want to change the position of the player. If we assume that moving up means incrementing the value of y, then we would just increment that value by the value of change. Then we pass this argument. But let's say that we want to assign a default value for change. In that case, we would just write right here an equal sign and the default value. This way, if the user calls the method moveUp without passing this argument explicitly, then this value will be assigned by default. Great, let's see another example with the next method, moveDown. We will do exactly the same. We want to change this by a value of 5. So we want to move up or down by the same amount by default. Instead of adding the change, now we are subtracting it. Now let's go to the move right method. This is similar to move up and move down, but instead of updating the y coordinate, we will update the x coordinate. And now we will assign the value 2 as the default change horizontally. Move right will be incrementing the value of x, and move left will be another method that will change the value of the x coordinate. It will reduce it by the default value 2 if we don't specify a value for the change. Of course, we are always assuming that change will be a positive value. Great, so now we have our player class with these 4 methods that will let us move our characters in the x and y plane. So let's create our player instance. My player, player. And what do we have to specify for the player? Well, the initial x and y coordinates. Let's say that initially we want the player to be at 5, 10 at this location. Let's call the method moveUp. We want the player to move up initially. And you can see that since the only parameter that we've defined right here besides self has a default value, we can call the method without passing any arguments. We don't see any errors right here. Let's call the method, and after we call the method, let's print the value of y. Let's print it before and after we call the method so we can see the update. Right here we see the initial value 10, which we assigned right here, and then we see 15 because we moved up by the default change, which we defined to be the value 5. Previously we had 10 and we incremented that value to 15. Great, so let's see what happens if instead of using the default value, now we pass a specific value for the change. Let's say 8. You can see that now the value went from 10 to 18. So the change was 8 instead of 5. This argument that we specified replaced the default value that we assigned. When you do this, you are giving the user the opportunity to customize this value. But if the user chooses to omit it, then the default value is assigned to that parameter. Now let's see what happens if we write move down. Right here, if we call move down and instead of passing a custom argument, we just use empty parentheses. Now the value of y went from 10 to 5 because we decremented the value of y by 5, the default value. Let's say that we pass a custom value like, for example, 3. Now we go from 10 to 7. We are decrementing the value of y by 3, which is exactly what we expect from this method. And let's see what happens if we try to move horizontally. Move right. Now we will be updating the x coordinates, so let's update these print statements right here. Initially, our x coordinate is 5. That is correct. And when we move to the right using the default value, which we set to be 2 right here, now the value of x is 7. We go from 5 to 7, which is correct. Let's customize this value to be 1 instead of 2. Now we go from 5 to 6. Now you try to call move left, use the default argument, and pass a custom argument. Pause the video for a moment and try to do this. Call move left. Welcome back. Now let's see what move left does to the x coordinate. We had 5, and now we are decrementing it by 2, so we reach the value 3. And if we customize this value, for example, let's say that we want to move 10 units to the left, we are decrementing the value from 5 to -5. Awesome! Now you know how to assign default arguments for the parameters of your methods. Great work so far. When you're ready, go to the next video to continue practicing your skills. Welcome to this practical coding session, where we will continue working with our backpack class. Now we will add another method that will show all the items or print all the items that are currently stored or contained in the backpack. This method will have a default argument. The default argument will determine if the list is printed alphabetically or not, if the items are sorted in alphabetical order or not. So let's implement this right here. We go to the bottom of the class after the last method and we add the method show items. We could also say print items or display items. You can choose the name that you like the most. Show items. This argument will determine if we print the items sorted in alphabetical order. By default, this will be false. So we will present them in the order that they were added to the list. But if we choose to make this true, we have to pass an argument, the value for it, and that will present the items in alphabetical order. So we say, if sorted list is true, we don't have to compare this to the truth value because this is already true or false. Then what are we going to do? Well, we are going to print a sorted version of the list of items. And this is how we can do that. With the sorted function, we get a copy of this list sorted in alphabetical order since we are storing strings. We're getting a copy. We're not modifying the list at all. This function is different from the sort method, which does mutate the list. So you might want to read more about the differences between the function and the method. Else, if the user is not asking us to sort the list, we use the default argument, which is false. And we just print the list of items like they are stored in the backpack in the order that they were added. Let's see how this works. We have our method defined, so now we can create our instance of backpack. And we're going to add some items to the backpack. We're going to add a water bottle, we are going to add a sleeping bag, and we are going to add some candy. Now the backpack has these items. Let's say that we want to show the items that are in the backpack, like we have x-rays or something. We can see everything that is in the backpack. First of all, we are going to see what happens if we don't ask the method to print the items sorted alphabetically. We write the instance and then we call the method show items. But we are not going to customize the argument. We are going to use the default argument that we assigned right here, which is false. This will print the items in the order that they were added to the backpack. And now we want to print the items sorted, like this. And for that, we have to pass an argument true right here. To replace the value false that would have been assigned by default, we pass the value true. Great, so let's save the file and run the code. And we see this right here as the output. When the list is not sorted, we see this output: water bottle, sleeping bag, and candy, the order in which we added the items to the backpack. But if we do ask the method to sort the items, then they will be sorted in alphabetical order: candy, sleeping bag, and water bottle. So this is an example of how you can assign default arguments for the parameters of your method, and how they can impact the output and the behavior of the methods. Another very helpful tool that we can use in Python is calling methods from other methods. This way, you can reuse the functionality that you already implemented in the class. If you already wrote some code to do something in your class, then you can reuse that code by calling the method in your class, in another method. If you're calling, for example, method B from method A, so you're making the call right here, and you're calling this method, this would be the basic syntax. In the body of method A, this box, this blue box, represents the body of method A. You would write self dot method B, the name of the method that you want to call. And then within parentheses, you pass the necessary arguments. It's just like calling a method, like we have been doing so far. But now we are replacing the object or instance that used to be a variable with the word self, because now we are working inside the class, and we need that class to work for every single instance. So instead of just specifying a specific instance, we use self to refer to them in a general way. In this practical coding session, we will see an example with our backpack class of how you can call a method from another method. For example, let's say that we want to implement some functionality in our class that will let us add multiple items at once. Instead of just calling the addItem method and passing one item, we want to define a method that will let us add multiple items at once by just passing a list of items. We can do this by defining a new method. Let's say, for example, add multiple items. You can customize the name of this method, add multiple items. And we will assign the name items to this parameter in plural because this will be a list of items. What do we want to do in this method? For each item in the list of items, we want to add that item to the backpack. So how can we do that? Well, we have a method for that precisely. We are taking a list of items and we are iterating over all the elements in that list. And then for each one of those items, we can add the item like we do right here. We are going to reuse the code that we already wrote by using self.addItem. And what item are we going to add? The item of the current iteration. This is really nice, right? For every item in the list of items, we are going to add that item. Self is the instance of backpack, okay? Self is the instance of backpack and this is a list of items. We can call the addItem method right here and reuse its code. We use what we wrote within the class already in another method to add an item. Let's test this new method right here by creating a backpack instance. Backpack, and what are we going to do? We're going to call the method add multiple items and we are going to pass a list. Let's add a water bottle and candy. We're going to add these two items. And remember that right here we are passing a list as an argument because we want to add multiple items to our backpack. To check if the items were successfully added to the backpack, we are going to print the list of items before we call this method, and then we're going to check this value again after we call this method. So let's save the file and run the code. Right here we have to add another line, and you can see the output. We see an empty list right here because the list of items is initially empty. And then after calling the method add multiple items, we see the list with the two items that were added by the method. This argument was a list. All the items of the list were added individually by calling the addItem method. The code ran, and within the code we were calling another method of the class, addItem. So we reuse this code and we avoid writing it again right here. This is really essential to make your classes more concise and to avoid code repetition, which is always recommended in software development. Great, so now you know how to call a method from another method of the class. You just write self dot the name of the method and you pass the necessary arguments, omitting the value of self. Whenever you call a method, even within the class, you have to omit self in the list of arguments. Right here we have self, but we just pass the item, and that is very important. Welcome to our first project. We're going to apply everything you've been learning so far to create a dice game. We will create all the functionality of the game with object-oriented programming, and we will write the code together step by step. We will start by analyzing the game description and the logic, and then we will dive into the code. This will be the final result. You will see a game where we have very descriptive messages in the terminal for the user, and we ask the user to press any key to roll the dice. Then the player and the computer will roll the dice and then the game will continue. We will see the specific rules in the next video. This will be a really fun game and you will apply many of the concepts that you have been learning so far. So if you're ready, let's begin. Let's talk a little bit about the general idea of the game that we will create. It's going to be a dice game. We're going to have 2 dice. And we're going to have 2 players. One of the players will represent the human player. In that case, if you are the one playing the game, then it's you. And the other player will be a computer player that you will play against. Both players will challenge each other to win the game. And they will both start with a counter of 10. The counter will determine who wins the game. In the game, we will have 2 dice. Each player will have a particular die associated with it. In terms of object-oriented programming, this will be an instance of die, and this will be another instance, and we will associate each player to each instance. We will have several rounds of rolling the dice until someone wins the game. For each round, each one of the players will roll the die, and the score or the value of the die will be recorded. Let's say 3 and 2, for example. The dice can take random integers from 1 to 6. So let's say, for example, that we got 3 and 2. After we roll the dice, for that round, we will compare the values. Is the value greater than the other one, less than another one, or are they equal? The player with the greatest value of the die, in this case, in our example, that would be 3, wins the round. And we will decrement the counter by 1 for the player who wins the round. And the player who loses will have the counter incremented by 1. Okay, so it's like the opposite of what you would initially think. You would think that if you win the round, you would increment the counter. But in this case, we are decrementing it. And you will see why in just a second. Remember, we subtract 1. If the values are equal, then there is a tie and the counters are not changed. We just go to the next round. And we continue like this in an endless process until one of the counters reaches 0. The player whose counter reaches 0 first wins the game. And we're all happy. Okay, so hopefully that will be you. If not, it will be the computer player and you will have to challenge the computer again if you want to win. After that, the game will be over and you can start playing again. Awesome, right? So that's basically the logic of the game. We will see this in much more detail in the next video when we actually start talking about the requirements for the game. I will see you in the next video. Before we start diving into the specific details of the game, there is a very important concept that I think you should definitely know about, because we will use it throughout this project, and that is aggregation. It is a concept in object-oriented programming that describes the relationship between two classes. Two or more classes. We're basically going to have a relationship between these classes. In aggregation, we're going to build complex objects that are composed of other objects. We're going to take simpler objects of simpler classes and we're going to combine them or use them to create more complex objects. Let me illustrate this with a more concrete example. Let's say we have two classes, class A and class B, and we need to reference class A inside class B. What we're doing here is we're basically using the functionality of the class A inside class B. Inside the actual classes, their definitions, okay? We're not talking about instances here yet or objects, we're talking about their definitions. We're kind of like creating a relationship or a connection between these classes. Class B uses the functionality or some of the functionality defined in class A. This is a relationship between the classes. Let's say that we create instances of these classes in our code. Instance of A and instance of B. When we create those instances, since B needs some instances of A to work completely because we're using the functionality of A inside B, we will need to provide an instance of A to create the instance of B. Like this. The instance of B will somehow store and contain the instance of A inside its definition. So we will be able to access the information and the methods of the instance of A inside the instance of B. We're basically storing instances of the simpler objects in the more complex objects. That's what we're doing right here. Let's say that A is a simpler object and B needs that object. B has an object of A. So we're going to store it inside B so we can use it. It is a has A relationship between the classes. An object of class B has an object of class A. We're using the functionality of A inside B. Let's see a more concrete example. I know this will help to illustrate this concept. Employee and vehicle. An employee has a vehicle. This vehicle could be assigned by the company to perform the work or something related to that. But let's say that in our program, an employee has a vehicle. So that has a relationship defines the concept of aggregation. We will store the information of the vehicle inside the employee, but they will be two separate objects in our code. We will just connect them or associate them in our program, like this. We will have the vehicle class and the employee class, so they will be separate objects. But since employee needs the information of the vehicle, we will work with the vehicle inside the employee class. Remember, they are still separate classes. We're going to define them separately. We're not writing the information of the vehicle directly within the employee. We're keeping them separate, but we are using a vehicle and storing it inside the employee. When we create instances of each one of these classes, vehicle and employee, the employee instance will store and contain an instance of vehicle. They're going to be separate objects, but when we create the employee, we're going to pass the vehicle, the instance, as an argument. And we're going to store it so we can use it inside the employee class. It's really awesome. Let's see an example in code. I know you will understand it more concretely once you see the code. Right now, I am creating a new project. It's creating the virtual environment, and we're going to have it ready in just a few seconds. And let's zoom in so we can write our code. Let's define our vehicle class. Remember that an employee has a vehicle. So first, we're going to define the vehicle that we need to create the employee. Class vehicle. Our vehicle is going to have three attributes: color, license plate, and a Boolean value to determine if the vehicle is electric or not. We're going to create those instance attributes using self, and we assign the value of the corresponding parameter. Then license plate. And finally, if the car is electric or not. Is electric. Awesome. So we have this ready, and just to add some functionality to make this example more realistic, we're going to define two methods. The license plate is something that we are going to be using constantly. We're going to check that license plate in our system. For example, let's say that this is something that we've determined. So I'm going to define this method, and what I'm going to do is I'm going to print the license plate when I call this method. And finally, my last method will be show info, show information. Okay? Let's print my vehicle you could also write vehicle or customize this message to your liking. To replace the value of the attributes more easily and more concisely, I'm going to add an F here, so we can use an F string. F strings, if you haven't heard of them, are a really cool and concise way to create strings and replace the values of variables inside our strings. We just need to add curly braces, and inside the curly braces we write the name of the variable. Or, in this case, we're going to write the name of the attribute, self.color. And when we see the string in the output, we will see it with the value replaced. Again, let's print the license plate and self.license plate. And finally, if the car is electric or not. Like this. Awesome. We have our vehicle class ready. We have init, the constructor, we have our 3 parameters, we define our instance attributes, and we have our 2 methods. So far, so good, right? Until this moment, we haven't started using the concept of aggregation, but we will in just a moment, right here below, when we start defining our employee class. We're going to have 2 blank lines here to separate the classes, and then we're going to start defining our employee class. Our employee is going to have an init method to our constructor, but here we're going to do something new. An employee is going to have a name, a string, but it's also going to have a vehicle. A vehicle right here. Vehicle is going to be an instance of the class vehicle. And that is where the concept of aggregation starts to become relevant. This is not going to be a primitive value like we have been using so far, a number or a string or another predefined or built-in Python data type. It's going to be an instance of a class that we just defined. So let's see this in practice. Now for the vehicle, we will write the same thing, but you have to keep in mind that we are not working with primitive values. This will be an instance of the vehicle class, and we will store that instance as an attribute of the employee. Notice what we're doing right here. It's like in our diagram. We have an instance of vehicle right here. We are taking that instance to create an instance of employee. And the employee will have a vehicle attribute that will refer to that vehicle instance that we are associating it with. A particular employee will have a particular vehicle. And that is the relationship that we are creating through aggregation. To illustrate this, let's use the vehicle in a method inside the employee class. Let's say that I want to define a method for the employee. I want the employee to be able to show me the vehicle information. That should be something that the employee should be able to do. If I ask the employee, hey, what is your vehicle? The employee should be able to give me that information. But how will it do that? It will do that through the instance of vehicle that we associated to that employee. Like you can see right here. This is something new. We haven't done this before during the course. So let's see this in detail for a few minutes. We're defining a method in the employee class, and we're naming that method show vehicle information. So the employee will be able to give me the vehicle information. But since we are not storing the actual vehicle information inside the employee, because they should be separate objects, remember that a class should represent a particular object, and an employee doesn't have a license plate. That wouldn't be logical at all. So to store that information in its own separate object, a vehicle, it does make sense to add the license plate to a vehicle. Then we just associate the objects, and then we can access that information through the vehicle. Right here, when we write self.vehicle, we are accessing that vehicle instance. And then, once we have that instance, we can write another dot to call a method or to access an attribute. In this case, we are calling the method showInfo, the method that we defined right here for the vehicle. I hope this is making sense, okay? Feel free to review the code as we move forward to make sure that you understand how this works, because we will use this in our game, and it's very important that you understand the concept. We are associating the two instances. I think this will be more concrete when we start creating the instances. So let's do that. Again, we have 2 blank lines, and then we're going to define our instances. First, we're going to create our instance of vehicle. We create that instance like you learned in the previous sections, vehicle. First, let's check our init method. We have color, license plate, and if the vehicle is electric or not. So let's pass those values. We're going to say that the vehicle is black. The license plate is AXY245. Let's say that this is the format of the license plate where the employee is working. And then we're going to specify that the vehicle is not electric. In Python, if you're curious about this, you can specify the name of the parameter just to make it extra explicit in your code, but it has to be at the end of the list of arguments, okay? I think this is much more readable than just writing false, so that is why I am including it here. Okay, so we have our vehicle instance. That's great. Now let's create an instance of employee. Employee. Let's check the init method for employee. Employee takes a name and a vehicle. So that is when we start actually using the concept of aggregation with the instances. The employee has a name, so let's say Gino. But it also has a vehicle, and that vehicle is an instance of the class vehicle, the instance that we created right here on this line. So we're going to take that instance and we are going to pass it to the employee as an argument. We're going to create the employee with the vehicle. The vehicle will be stored inside that particular instance of employee. So we're creating that relationship. An employee, a particular employee with the name Gino, has that particular vehicle, which is black, with this license plate, and it's not electric. So I hope this illustrates the concept of aggregation a little bit better. We are creating that relationship and working with the objects, and we are storing this instance inside the instance of employee. And since we are working with the vehicle instance inside the employee class, we will be able to use the information from the vehicle instance inside our employee instance. Okay? Now we have our instances. Let's see how they work, how you can use them and access their values in the code outside their classes. Let's remove this line and first let's print employee and let's run our code. You can see the output, this one right here, okay? We do have an employee object. Now, what if we want to access the vehicle associated to that particular instance of employee? Remember that we stored the vehicle as an instance attribute of the employee. Just like any other attribute, just like the name attribute. Usually when we access an instance attribute, we use dot notation. Like this, employee.name. If we run the code, we see the value Gino, the value of the name attribute. The same principle applies to the vehicle, but instead of being a string, we will just have an instance of vehicle. Like this, employee.vehicle. This is the output. We have a vehicle object stored at a particular memory location. So we are confirming that we actually have a vehicle instance inside our employee instance. Really awesome, right? We are using aggregation to create more complex objects from simpler objects. Now that we confirm that we have a vehicle instance inside employee, let's check that you can actually access the attributes of the vehicle and call its methods inside your class, because right here we have a method, show vehicle information. This is a method defined in employee, but the method is calling a method from the vehicle. Notice that right here we are referring to self.vehicle, and everywhere where we use that, we will be referring to the vehicle instance that we associated to our employee. After we have that instance, we can call the method because the instance has that method defined, because we defined it right here in the vehicle class. So if we call this method, we should be calling this method indirectly. Let's see. We can write employee show vehicle information. Let's see the output. We see the output right here, which is awesome, right? Because we're getting the information of the vehicle associated to the particular employee, Gino. Notice that we are calling the method on the employee. We are not actually doing anything with the vehicle on this line. But through this method and the class definition, we are calling the method of the vehicle instance indirectly. And through the employee Gino, we are getting the data or the information, the attributes of the vehicle instance associated to that particular employee. And that is super helpful because we can create those more complex objects and still keep the information separate in different classes with different objects that can be reused. Great, so now we call the method, and another cool thing that you can do outside the class, of course if you're working with public attributes, is accessing the attributes of the vehicle directly using dot notation like this. Remember that when we wrote employee.vehicle, we had a vehicle object. Well, after we have that vehicle object, we can use dot notation again on the same line, like in a chain, to get a particular attribute of that vehicle. Color, we could also get the license plate, and we can get if the car is electric or not. And we're getting all of that information indirectly through the employee. Then we are accessing the vehicle instance with dot notation, because vehicle is an attribute of employee. We are storing a reference to that instance inside the employee. And then once we have that reference to the vehicle, this will be converted behind the scenes to a vehicle instance. We will be able to use dot notation again to get these particular attributes of the vehicle. And we're doing all of that outside the class. Let's run the code and see the output. We get the values right here. Remember that our vehicle was black. We see it right here. It had this license plate, and we see it right here, and it wasn't electric, so we see false right here. So we are able to get those attributes indirectly through the employee instance. And that is the best way to access them, because if we need the vehicle that corresponds to a particular employee, we use this, and then we can access the attributes of that particular vehicle instance. Great! Notice that this is very similar to what we did right here in the method. Inside the method show vehicle information, we wrote self.vehicle to get the instance of vehicle, and then we call the method. Right here, we are just writing the name of the variable that holds the instance instead of self, and then we're writing the vehicle, and then show info. Right here, we're getting a message that says that this parameter shadows the name vehicle from the outer scope. In this case, in this simple example, this wouldn't affect any of the functionality of the class. But if we want to prevent this, just say black vehicle or something like that, and you would just update this name and the warning would disappear. Okay? Black vehicle, or you can assign any name you like to this variable. Awesome. And finally, let's see that you can also call methods of the vehicle instance through the employee. Let's say that I want to show the license plate of the vehicle associated to this employee. I write employee, then vehicle, because I want to get that particular vehicle instance associated to my employee, and then I call the method show license plate. Employee.vehicle show license plate. With this part of the line, we are getting the vehicle instance, and then we are calling the method show license plate. If we run the code, we see the license plate right here of the vehicle associated to that particular employee instance. Awesome. So this is a brief overview of how you can use aggregation in your code, and we will use aggregation during our project for the dice game. How will we use it in our project? Well, let's see. For our project, we will be using aggregation between the die and the player. And then we will also use it for the game. Initially, we will have a die class and then a player class. The player class will have functionality of the die inside it. The player class will reference the die inside the class. We will work with the die, that particular instance, inside the player class, so the player can roll the corresponding die. We will have these two classes, die and player, and then we will create two instances, just like we did right here with vehicle and employee. Die instance and player instance. And then the player instance will store an instance of die inside it, so we can roll that particular die and get our final result for the round. Awesome, right? I hope this concept of aggregation is a lot clearer to you now. It's very important in object-oriented programming, and we will use it throughout this project. So, if you're ready, let's continue. Feel free to review this code and the vehicle and employee example. I will see you in the next video. Now let's dive into the requirements of the game. Let's say that you met with a potential client or with a friend, or you're just analyzing what project you want to create. The first thing that I would recommend is writing the requirements of the project like this, in detail with bullet points or in any format that you feel comfortable with. But I personally like to write them like this. We have the general requirements, we have specific requirements, and then we have requirements for each one of the elements in our game. Let's dive into this analysis and see how we can derive the structure of our code from an initial description. What are the general requirements? We know that the game should have 2 players. Players is an important concept for this game. That will definitely be a class in our game. We have a human player and a computer player, and both of them should have exactly the same functionality. So if we know that they will both have the same functionality, we can define both of them with the same class. We can just add something to distinguish between the different players, like an attribute. Okay, so we have a player that determines that we will have a player class. Then we know that both players will start with a counter of 10. So counter is another important attribute here. It will be an attribute of the player class. Each player will have a particular die during the entire game. So die will be another important concept, and actually we will represent it as a class. In our game we will have 3 main classes: player, die, and we will get to the next one in just a few lines. Both players will roll their corresponding die once per round. That is just a general description of the game. So far we are not identifying another element. We could highlight roll right here because it is a verb, and that is a potential method for the players. Then the value of the dice will be compared to determine who wins the round. The player with the highest value wins the round, or with the greatest value. So this is just telling us about the logic of how we should implement the round. Right now we're trying to get a general sense of the structure of our project and classes and methods, so this particular description will be helpful when we start implementing that. But right now, we don't have any new objects or classes to add. If the two values are equal, then there is a tie and there is no winner for that particular round. The counters are not modified. The counter of the player who wins a round will be decremented by 1, and the counter of the player who loses a round will be incremented by 1. I think we should highlight this in our description. The counter of the player who wins a round will be decremented by 1, and the counter of the player who loses a round will be incremented by 1. So we're not actually like rewarding by incrementing the counter. Incrementing the counter means like a punishment or the result of losing. Great, so now we're back to the final bullet point of our general requirements. The counter will determine who wins the game. The player whose counter reaches the value 0 first wins the game. So far, we have identified these important elements. We need a player class and we need a die class. The players will have a counter attribute because both players will keep track of a counter, and that will be an instance attribute because the counter of each one of the players can have a different value. And we know that players should be able to roll the die. Okay, so that is a potential method. Great, so we're done with the general requirements. You have a general idea of the game. Now we have some specific requirements that I wrote right here for interactivity, how to roll the dice, and how to present different messages for the user. For interactivity, before the human player rolls the die, he or she should be prompted to press any key to start the round. Because otherwise we will just be generating random numbers until the game ends and there will be no interactivity. We need to have a moment in the game where we're going to stop and ask the user to perform an action to start the round. I think that will make the game a lot more engaging. After that, we find rolling the dice. When a player rolls the dice, the result should be a random integer between 1 and 6 inclusive. Okay, this is something important. The result should be a random integer between 1 and 6 inclusive. We're going to play with a die that has 6 faces with the numbers 1 through 6 inclusive, the integers. That is important because we have to know the characteristics of the die to implement the functionality of rolling the die. After that, we're going to go to the messages. Let's go to the messages. The game should show a descriptive message when the game starts, when a new round starts, when the game ends, and this message should mention who won the game. Of course, we congratulate the winner. If the human player loses, then we should say like, sorry, play again, or try again. And the game should also display messages to show the value of each die after the players roll the dice, mention the winner of the round, or mention if there was a tie, and to show both counters when a round ends. So we have to keep these messages in mind. This will give the user a more interactive and engaging experience. That is important, and that is something that you should always keep in mind when you are writing the requirements of your project or game. What should be there? What should the user see? Now, okay, so we identified the two main classes from the general requirements, die and player. But we should also add a third class called dice game. Since we want to make this project purely object-oriented, we will also represent the game as a class. This will be a class and it will have its own attributes and methods. Okay, so we will have three main classes: player, die, and dice game. We will also use the concept of composition throughout the project. So let's go back to the first two classes, die and player. We have more details here. We are told that each die should have a value. So this is an attribute of die. This value should be either none if the die has not been rolled yet, or a random integer between 1 and 6 inclusive. This attribute should not be changed outside the class. The change should be handled internally. So that gives us a clue that this value should be non-public. We don't want to change the value outside the class. We only want to change the value when the player rolls the die. So that should be handled internally inside the class. Each die should also be able to roll. So that is a method that we should implement for the die. The die should be able to roll, and rolling in this case technically will mean generating a random integer between 1 and 6 inclusive and assigning it to the value attribute. That is our definition of what it means to roll a die. Great! So that is the basic definition of our die class. Now let's go to our player class. Each player should have the following attributes. These are instance attributes. A die instance. Remember aggregation? Well, right here we can see it in action in our game. We're going to create a player, and for each player we're going to have a die instance. Each instance of the player class will have a particular die instance associated with it, so we can roll that particular die through the player. Each player should also have a Boolean value, true or false, to indicate if the player is a human or the computer. Okay, so this attribute, we could determine how to call it, but in our implementation, I will call this isComputer. Usually when we write Boolean attributes that are true or false, we try to write them or name them as if they were a question. isComputer, or has that particular attribute. That is the format of Boolean attributes, usually to be more explicit in our code. And finally, each player should have a counter attribute, and that initial value should be 10. Remember that the counter will determine if the player wins or loses the game. That covers the attributes of the player, but we should also talk about the methods. What should the player be able to do during the game? Each player should be able to increment the value of the counter by 1. So we could name this method like increment counter. It should also be able to decrement the counter by 1. So we could call this method decrement counter. And it should also be able to roll the die instance associated to that particular player instance. We will tell the player to roll the die, and then inside that method, we will be rolling the die instance through its own method. We will get to those details when we actually implement the code, but I just wanted to give you a brief overview of what we're going to do. Great, so now we have our two classes, and we're going to start talking about our third class, Dice Game. This class will have a few more details. It will represent a dice game. So we're making our project purely object-oriented. Everything will be a class. Each instance of the game should have the following attributes. Since this is an attribute, let me change this to light blue. It will have a human player instance. It will have a computer player instance. And those are the two instances that will be associated to that particular game. So again, we will be using the concept of aggregation. We will store the instances of the player class. In this case, we have two instances inside the dice game. Awesome, right? This will create a relationship between these classes. So a dice game instance has a human player and a computer player. Again, we find this relationship has a human player and has a computer player. So we know that we are working with composition. Each instance of the game should be able to. Okay, so now we start diving into the methods. Because should be able to. So now we're starting to talk about verbs, actions. What should the game be able to do? So those are the methods. Let's change this to yellow. And we know that it should start the game. We will name this method play. This method will start the game logic. It should show a welcome message to the user. and it should create the endless loop, the infinite loop, that will continue the game until a counter has reached the value 0. The game should also be able to start a round. We're going to have two separate methods to handle the entire logic of the game. Play will start the game logic, and then we're going to have a method to handle the logic of a particular round. Otherwise, if we don't separate this into two methods or more, the method will be really complex, and we usually want to write our code in a modular way, in a way that is easy to maintain and easy to debug. So we try to write more compact methods instead of writing hundreds of lines in the same method. Okay, so start a round should handle the main round logic. It should welcome the player to the round, roll the dice, and determine the winner and loser of the round. After it determines the winner and the loser, it should update the counters accordingly and show the values of the counters. So that is basically what we talked about, the logic of the game for a particular round. And then this method will continue that endless loop or infinite loop going until a counter reaches a value 0. At that point, the game should be able to determine when the game is over and stop the game. Okay? It should be able to detect when we should stop the game logic and interrupt that endless loop or infinite loop. The game should end when the counter of either one of the players has reached the value 0. And in that case, a descriptive message should be printed before the game ends. Awesome, we've covered most of the details of the game that we're going to implement. In this dice game class, we're actually going to implement a few more methods than this, but these are the main ones, and the other ones will be smaller methods that will help us to implement this in a more modular and maintainable way. Based on the description that we just saw, this will be the basic structure of our code. We're going to have three main classes: player, die, and dice game. These three classes will work together to create the main game logic. For the die, we're going to have one attribute, value, and we're going to have one method, roll. We're also going to work with properties in our code, but right now I'm just mentioning the actual attributes that we're going to define in init, okay? In our code, we're going to write the properties. Then for the player, we're going to have these three attributes: die, is computer, and counter. The player will have a die instance associated with it through composition, a Boolean value to determine if the player is the computer player or not, and then the counter. Remember that the counter will determine who wins the game. Then we're going to implement some functionality for the players: increment counter, decrement counter, and roll die. This functionality will be essential for the game logic. And finally, we go to the dice game class. This class will have two main attributes: player and computer. Remember, we're going to use aggregation. So right here, we're going to associate two instances of the player class. Each dice game will have a particular player, a human player, and a particular computer player. In the class, I will assign the name player to the attribute that will store the human player, and computer to the attribute that will store the computer player. Okay, they are actually both instances of player, but I think this naming style will help us to write more readable code. And the dice game will have a few methods as well: play, to handle the main game logic; play round, to handle the logic of a particular round; check game over, to check if the game is over and when to end that endless process, that infinite loop; and a few more methods that we will implement as helper methods, methods that will help us to write more concise methods for this functionality. Great, so this is the final structure, and I also wanted to give you an overview of how we're going to work with our instances, because right now, so far, we have only talked about classes. We have the player class, the die class, and the dice game class. These are our blueprints, but what about our instances? Remember that in aggregation, instances were essential because an instance stored another instance. So let's see the relationship between the instances in our game. We're going to have two instances of die. Remember that each one of the players has its own particular die, and we will represent that with different instances. We will have a player die and a computer die. We will also have two players, my player and computer player. This will be the human player and this will be the computer player. And we will also have an instance of the game called game. If we have a bird's eye view of the structure of the logic of our program, this is what will happen. This is a general overview of the structure. We have our two player instances, my player and computer player, and each player will have an instance of a die, player die and computer die. Notice that the die corresponds to that particular player. We will use composition for this to store the instance of die inside the instance of player. We will pass them as arguments to create the instances like we did with vehicle and employee. And then once we have that structure ready, we will create the game. And the game will have a human player and a computer player. It will have references to these two instances, and the players themselves will have references to the dice, to the corresponding die. So this is like a general overview of what will happen during the game and how we can access the attributes. The game will be able to access the attributes and methods of the players, and the players will be able to access the attributes and methods of their corresponding die. I'm very excited to show you this code. I'm very excited to start diving into the actual project. I will give you this PDF file so you can download it and review it while we're implementing the project. So when you're ready, go to the next video and we will start writing our code. I will see you there. Awesome! Are you ready to start implementing our dice game? Well, first, let's start by implementing our die class. First of all, you need to create a new project. I named the project Dice Game and I created it in a folder in my documents. I also have my virtual environment here and I have main.py. To create the project, remember you go to File, New Project, and then you choose the location of your project. I usually like to use a folder in my documents. Then you can just leave the default settings and that will create a main Python welcome script. And you can delete the starter code from this file. You click on create and that will create the project for you. Great! So now let's start implementing our die class. Let's close the project structure and let's start implementing die. Remember, we write class die, and then we have our init method. Remember that in our initial planning, we said that the die class would have a value attribute. You could also call this score or result or any other name that you think could be more descriptive for this attribute. I will write it as value. Okay? And I will assign it as an instance attribute, value. This value should be non-public because we don't want the value of the die to change outside the class. So we're going to choose to make this attribute non-public. And we're going to create a property for that value, like this. Remember from the section where we covered properties, we use the add-property decorator, then we write def, the name of the attribute or the property that we are creating, and then we're going to return the non-public attribute. Remember, it's non-public because we have an underscore before the name. Awesome, we have our attribute and we have our property. In the description, we also saw that the value of the die should be none by default if we haven't rolled the die. Since we are defining this as a parameter, we can also assign a default value for that parameter, a default argument or default parameter. That is what we will do right here, value, and we assign the default value none. That will be assigned to value if we don't provide a value for it, and it will be assigned to the value attribute. Why are we writing this as a parameter? Actually, we have two choices to write the value. We can write it as a parameter like this for init if we want to give the user of the class the option to customize the initial value of the attribute. Or we could delete this and just write none here as the initial value for this attribute. I personally think that it is always better to include the attribute here with the explicit value none to make the code more readable. We could create it to make the code more readable. Okay, so we have those two options. You can choose the option that you want depending on the implementation that you are envisioning for the game. In our case, I will choose this option. I won't give the user the option to set the value for the die when the die has just been created. We're going to assign the value none until we roll the die for the first time. Okay. So after we have that, now we have to implement our method for the die class. The die has to roll, and rolling in our context means assigning a random integer between 1 and 6 inclusive to this value attribute. So let's do that. Right here we're defining the method roll, and then inside the method we're going to assign the random integer. We're going to store it in the variable new value. Okay, and to generate that random value we will need a module called random. It is a built-in module that is installed automatically when you install Python. You just write import random right here, and you will have access to that functionality, to the functions defined in this method. Right now we see a warning because we haven't used that module yet in our code, but we will use it in just a few seconds when we write this random.randint. This function randint generates a random integer between a lower bound and an upper bound. The lower bound will be 1 and the upper bound will be 6, both of them inclusive. Okay, so we will assign that random integer to the variable new value. And then once we have that new value, we should assign it to the attribute value right here. Self.value equals new value. We assign the new value to self.value. And finally, we are going to return the new value. Trust me, that will be helpful when we start writing the actual logic of the game and working with the dice. So we're updating the attribute and we are returning that new value. This is our die class. We should add 2 blank lines here to follow PEP 8, the style guide for Python code. An important thing to notice here in our class is that we are only writing a getter for the value attribute. We're only writing the getter and not the setter because we only want to present or to share the value of this attribute outside the class. We don't want to change it outside the class by any means. We just want to change it when we roll the die. Okay, so we don't want any unexpected or direct changes. That is why we make this attribute non-public and we only give the users the option to read or to access that value, not to change it. Okay, so that is why we don't define a setter here. And that is part of the decision-making process and analysis that you should do when you're writing your code and your classes. Awesome. We have our die. Now let's test our class by creating an instance. This will just be like an experimental code that we're going to write to test how our class works. Testing the class. This will not be a test in the formal sense of the word. We're just going to check how the functionality is working right here. Die will be an instance of die. Remember that in init we don't have any parameters, so the value of this attribute will be none initially. Let's check this. Die dot value the result should be none right here for this line. And like we predicted, the value is none. Then let's say that I want to roll the die, and I call the roll method. After rolling the die, let's check the value and see what we get. Let's run the file, and like you can see right here, we have the values none and 5. Initially, the value was none, and then it was replaced with the number 5, that random integer that was generated right here with random.randint. This updated the attribute, and it should also return the new value. So let's test that. Let's remove this print statement, and now, since we are returning the value from this method, we should be able to assign it to a variable and see that new value. So if we assign it to the variable and then we print that variable, we should see the new value if we run the code. Now we see the value 4 because it is random, and we will get a different value every time we roll the die. They can be the same, but the process will be random. And we could get a different value every time we roll the die. Great, so now we tested the class and you know how the die works. And now we are ready to start writing our player class, the next class that we will need to implement our game. Like you can see, so far we haven't actually used the concept of aggregation. We will start using that when we start writing the player class in the next video. We will have a particular die associated to a particular instance of player. I will see you in the next video. Awesome! Now we have our die class defined with its attribute and the roll method. So now let's start implementing the player class. We're going to have 2 blank lines right here between one class and the next. That is recommended by PEP 8, and you will see a warning if you only leave one blank line between the classes or between the import statement and the first class. Like you can see right here, it says that PEP 8 expects 2 blank lines but only found 1, so if we add 1, the warning disappears. We will do the same for the next class, and we will start defining player. Class player. We write our init method, and in our init method, we will start using the actual concept of composition. We will have a die parameter. This will be an instance of die of the die class that we defined right here above, before, and then we will have another parameter called isComputer. By default, the player that we are going to create will not be the computer player, so its default value will be false. We are assigning that. But we are giving the user the option to customize this because we're defining it right here as a parameter in init. So if the user wants to pass the value true for this parameter as an argument, he or she can do so. It is possible. We have our 3 attributes right here. Let's see them one by one. First, we have our die, which is the die instance that will be associated to that particular player. Just like we associated the vehicle instance to the employee, we will have a die for a particular player. Then we have the attribute isComputer. This is a Boolean value, true or false, that indicates whether the player is the computer player or not. And finally, we have the counter. The counter is initially 10. This is the initial value of the counter. You can also customize this to your liking. When the counter reaches 0, then the player wins. Great! Since these attributes should not be changed or modified outside the class, directly we only want them to change internally like we define, we can make those attributes non-public. According to the PEP 8, the style guide for Python code, if you're not sure about whether you should make an attribute public or non-public, you should choose non-public, because it is easier to make that attribute public later on, because no one will be using it outside the class. But if you change it from public to non-public, that is when you can have issues, because other developers or even yourself might already be using that attribute outside the class, and the access will be changed, modified, or restricted. But we do want to give access to these attributes. And how can we do that? Well, through properties. We will only define getters for these particular attributes. We will define a property for die. We don't want to change the die property in any way. So we will be returning die. We also want to create or define a property for isComputer. And finally, a property for counter. Remember that the counter starts at 10. But we don't want to modify it outside the class directly. We don't want to jump from 10 to 3, for example. That could cause issues or unexpected results in our game. We want to increment it or decrement it ourselves inside the class in a controlled way. So that is why we're only providing a getter for this attribute, no setter. So we have 3 attributes and they will all be read-only. We will only be able to access their values. Then we have our methods. Let's define our increment counter method. This method will increment the counter by 1. So how do we do that? We use dot notation, we access that attribute, and then we increment it by 1. Simple, just one line of code. And then we decrement the counter. We have another method to decrement the counter. Awesome, right? And one last method is where aggregation comes into play in this code. We want the player to be able to roll the corresponding die, right? That is an action that the player can take. But we also defined a roll method for the die, because rolling is actually an action performed by the actual die. The die rolls. But we also want the player to be able to roll the die through a particular method. We want to say, hey, player 1, roll the die. So we want to define a method directly in the player class. But we want to use this method to call the roll method of the die that is associated to this particular player. Remember that we are associating the die to a particular player. This is a die instance. Since this is a die instance, it will have its own set of attributes and methods. So we will be able to call those methods inside the player class. And that is what we will do right here. We will call self.die.roll. Right here, we are first getting the die instance associated to that particular player, because this is an attribute. Remember that we created it right here, and we assigned the die instance. And then we are getting that instance and calling the roll method. This is the method defined for the die, right here in the die class. Just like remember when we wrote the vehicle and employee example, we called the method from the vehicle inside the employee class. That is exactly what we are doing right here. We're rolling the die through its own method, but we will call a method defined in the player class. Awesome, right? And finally, we also need to return this value. Because remember that in roll, right here, above, we are returning the new value of the die. we want this value to be returned to anyone who calls this method. When we call the method right here, the value will be returned. But if we don't add another return statement right here, the value will not be returned from this particular method if we call this method. We would have the value none even if we returned it right here. We need to add another return statement. That is important, very important, to return the actual value from calling this method. Great! That is our player class. We are applying everything that you have been learning so far in player and die. Let's test our player class. Let's create the instance. Let's just define my player. This is just code to test the player class right now, okay? This is not code that we will be keeping later on when we write our next class. This is just right now for testing purposes. We're going to create a player instance. How do we create a player instance? Well, remember that we defined this init method, and it takes a die, and it takes a Boolean value, which is optional. It can be true or false, and by default, it will be false if we don't pass a value for it. So, the first thing that we notice here is that we need a die instance. So let's create it. We need to have that instance before we can actually create a player. My die. Okay? I have the die instance, and then I can pass that instance to player. This is my die instance. This instance will be associated to the instance my player. So each player, that player will have its own particular die to roll. And then we can pass the Boolean value, or we can just omit it. Let's say that this is the computer player. So we pass the value true. Let's check the attributes. First, let's check the type, the data type of my player. Right here we see the player object. So it is an object of type player. Great, this is working like we expected. Now, we created this instance with the instance of die. So let's access the die attribute of the player instance. Remember that this is the property that we defined right here, the property die. So we can use dot notation to access that particular instance of die associated to the player. This instance that we pass right here. It doesn't matter that the names do not match, okay? This is the name of the variable that we used right here to create the instance of die. And this is the name of the attribute internally, like we defined it in the class. They are totally independent, okay? But they represent or store the same value. Now we see that we do have a die object. By using the dot notation, we are accessing the die instance associated to that particular player. And that is how we're using aggregation in this case. We can also check if the player is the computer player. It should be true. And it is. We see the value true right here. If we omit this value, we will see the value false. Because by default, we are assigning the value false right here in init. This is a default argument or a default parameter. Awesome! Another cool thing is that in Python you can specify the name of the parameter if you want to make this more explicit, because true or false doesn't really give us much information of what that value means. If we want to know what this value represents when we create the instance, we can use keyword arguments. We write the name of the parameter, followed by an equal sign, and then the value of that parameter. In this case, it's true, but it could be false as well. Okay, the effect will be the same in the program. We will see the value true if this value is true, and false if we pass that value. And we can also omit it. and use the default value, false. Okay? Let's also check the counter attribute. If we run our program, we see the value 10, which is the initial value that we assigned right here for the counter. So that is correct. Let's print the counter. Then let's call the method increment counter. And then let's print the counter again. Let's see what we get. Initially here, this should be 10, then we are incrementing it, and then this should be 11. And that is exactly what we see. We see the value 10 followed by the value 11 because we incremented the counter. That is great. And then decrement counter should decrement it by 1. Perfect. Initially it was 10 and now it's 9. Awesome, we tested these two methods. We also tested all the different properties. And now we only have to test roll die. Let's call this method through my player. Roll die. This method will call the roll method of that particular die associated to the player. Initially, let's check. Since we're going to roll the die, we're going to change the value of the die. My die.value, we're going to print it before we roll it. And then we're going to print it after we roll the die to see the difference, to see the change. Right here you can see the difference. Initially, before we roll the die through the roll die method of the player, we see the value none for that attribute. The die associated to that player didn't have a value because the player had not rolled the die before. But after we call the method roll die, now we do see a value for that particular die, 4. It's amazing. We're calling the roll method of the die inside the player class. And this magic can occur just because we are using aggregation. We have a particular die instance associated to the player instance. That is very powerful. We have access to the methods and attributes of the die inside the player class. And finally, just to check, we can access the attributes of that particular die associated to the player instance using dot notation like we did before. Like this. My player, then we access the die. Right here we have the die instance associated to that player. This is the name of the attribute, die, of the property in this case, since we have a getter for that. And then we have the attribute of that instance, value. We see the value none right here because the die has not been rolled. If we roll the die, we see that the value is updated. Okay, the value of the die associated to that particular player. Awesome. Now we should delete this code for testing the player class. We're not going to need it anymore. We know that it's working. And now we have our die class and our player class. Awesome. In the next video, we will start implementing our dice game class. That is the class that we will use to represent the actual logic of the game. I will see you in the next video. Great, now that we have our die class and our player class defined, we will start defining the dice game class, the class that will represent our actual game. Since we are using object-oriented programming completely during this project, we will represent the game with a class. So let's start writing it. Remember that PEP 8, the style guide for Python code, recommends leaving 2 blank lines between the classes. So we will do that. And we will start defining the class, dice game. The dice game will have two instances of player associated with it. Init. And then we have player and computer. This will be the two player instances that will be associated to that particular game. Player will refer to the human player and computer to the computer player, because I think that this will be a simpler notation than writing human player and computer player. We write the two attributes right here, player and computer, and we will make them non-public. But in this case, we're not going to write any getters or setters or properties for those attributes. They will be completely non-public and they shouldn't be used or accessed outside the class. So we have our init method. Now let's start actually implementing the logic of our game. We're going to do that in the play method. Remember that all the methods take self as the first parameter. First of all, when we start playing the game, we want to show a nice and welcoming message for the user. So let's do that with print statements, because the game will be based on the terminal, so we can use print statements. I personally like to use like a row of equal signs. I think that is a nice visual separator for the different parts of the message, but you can choose to format it any way you like. Right here we can also copy and paste emojis. So I will use a die emoji. The emoji that you see right here will be different based on your IDE or code editor. In Visual Studio Code you will see an emoji with colors, and right here you see a different version of the die. Welcome to Roll the Dice. We can add a few more and then we can adjust it if we don't like the number of equal signs. And we have another one below. Awesome. Roll the dice is one alternative for the name. We can also write welcome to my dice game. We can write it in lowercase. You can choose the message that you would like to write here. I'm going to say welcome to Roll the Dice. Then, since we don't know how many rounds we're going to need to end the game, because we don't know how many rounds it will take for either one of the counters to reach the value 0, we're going to have an infinite loop. Well, it's not actually going to be an infinite loop, but we're going to stop it when the condition for game over is true. So we're going to use while true. A while true loop runs until it finds a break statement. That is exactly what we are going to do. Okay? We're going to implement this functionality in parts. We're going to implement it and then we're going to separate it into different methods, because the actual functionality is going to be a little bit more complex. An indefinite number of times we're going to play the round. Remember that we're going to have another method called play round. We're going to define it right here below. And then we're going to check if the game is over, and then we're going to stop the process. But that is something that we still have to add later on in our code. So we're going to write it right here like a to-do in a comment. To-do. Implement game over. Great, so let's start implementing play round. The implementation of this loop will take many different steps. So we're going to break this process into multiple lectures or videos until we have the entire functionality. We're going to implement the basic functionality in this video. Let's define the play round method, self. First, we want to welcome the player to the round. How can we do that? Well, we can write print, and then let's write a few dashes or hyphens, new round. Let me copy paste this so we have the same number of dashes on both sides. And then remember a key requirement of interactivity that we mentioned in the game description. We should ask the player to press any key to roll the dice. And if the player presses any key, then we roll the dice. So how can we do that? In Python, a really cool way is using the input function. We call input and we write the message, the descriptive message. Let me copy paste this emoji right here. Press any key to roll the dice. Right here. We can add a space or omit it. We can adjust that later. Since we are calling input, the program execution will stop. It will be paused until we enter something here. We ask the user to press any key, and we're not actually doing anything with that input. We're just calling input to stop the process. The user presses any key, and then we continue. But I think this adds more interactivity and it makes the game a little bit more engaging than just an endless sequence of random numbers being generated. Okay, so that is how we print a welcome for the user. Let's write comments here. Welcome the user, welcome the player. After that, what do we want to do during the round? We want to roll the dice. Remember that each one of the players will roll the die once, and we will keep track of those values. So, the player will roll the die first. How do we get the player to roll the die? Self.player and then roll die. This is how we can roll the die. Let's understand how this is working, because right here we are applying the concept of aggregation that we saw in the previous videos. Remember that we have an instance of the human player and an instance of the computer player right here. We pass them as arguments and we assign them to instance attributes, attributes of the dice game. If we write self.player with the underscore right here, we will be able to access that player instance through aggregation. And then, once we have the player instance, if we write another dot, we can call the method of the player, roll die. This is the method that we defined right here in the player class. This method, roll die. That will roll that particular die that has been associated to the player. So we do that for the human player and we do the same for the computer player. Self.computer.roll die. Awesome, right? Player value, computer value. And this is where you can see how helpful it is to return the value of rolling the die, the result. Remember that when we defined this method, we returned the value returned by rolling the die. By returning the value and returning the value from this method, we can assign that value, that result, to a variable. After that, we want to show the values. Let me add a comment here, roll the dice. Show the values, okay, of the dice. How can we show the values of the dice? We will print the values. Your die, we are using an F string right here. And we're going to print player value, the value of rolling the die associated to the human player. And then we are printing the computer die. Computer value. Show the values. Awesome. In an upcoming lecture, we will define methods for all of this functionality. We show the values, and then we want to determine the winner and the loser of the round. Determine winner and loser of the round. How do we determine the winner and the loser? Well, when we saw the rules, we saw that we were going to compare the values of the dice. the player with the highest or greatest value won the round. So we're going to compare player value and computer value. If player value is greater than computer value, is strictly greater than, then the player wins the round, and we print, "You won the round." A confetti emoji right here. And then we want to update the counter. But first, let's print the messages. Else, if the computer had the highest value, then we want to print a message. The computer won this round. Try again. And we can have a sweet emoji, sad or crying. Else, the third option would be that the two values are equal, because if the player value is not greater than the computer value and the computer value is not greater than the player value, then they're both equal. And in that case, we have a tie. We can add a little emoji with sunglasses because it's a tie. Great! After that, we can show the counters of the players. Your counter, and we're going to use f-strings. Self.player.counter. The computer counter is self.computer.counter. Self.player.counter and self.computer.counter. We're accessing the counter attributes of the human player and the computer player. So let's add a comment right here, show counters. But there is something very important that we haven't implemented yet. How are we updating those counters? Remember that we should decrement the counter of the winner and increment the counter of the loser. We're not doing that anywhere in our code yet, so let's do that. In this case, the player wins the round. So, remember that in the player class we have a method called increment counter that increments the counter of the player by 1. And we also have another one called decrement counter. For the winner, we have to decrement the counter. And for the computer, we have to increment the counter. In this case, the player won, so we are decrementing the counter of the player who won, and we are incrementing the counter of the computer who lost. Okay, the winner and the loser. So let's add these comments right here, winner and loser of the round. We will do the same in this case, but invert it. Instead of decrementing the player's counter, we will decrement the computer's counter because the computer won. So we can just copy paste this. You should be really careful when copy pasting. Make sure that you make the necessary changes. Right here, we are just inverting computer and player. Okay, make sure that they are inverted. And that is how we update the counters. Awesome, right? We're implementing that entire functionality in just one method. And that is not really recommended because, as you can see, this method has several different lines. And it has more complex functionality than we would like to for a particular method. So we can divide all of that functionality into multiple methods. But so far, let's see how it's working. Let's create an instance of dice game. We will name that instance game. But remember that to create a game, we need 2 instances of player. We need the player and the computer. So let's create those instances. My player will be a player and computer player will be a player. Now, what do we need to create a player? Let's go to the player class. Let's go to that definition. We need a die and we need a truth value to determine if the player is the computer player or not. So let's create the dice and create the players. Player die and computer die. Create instances. We have our two instances of die, the player die and the computer die, and we are going to associate them to the player instances, my player and computer player, through composition. We're going to have that relationship between the classes. Each player will have its own die, and this player is not a computer player, so we can pass the value false. Even if that is the default value, if you think that it's more readable to specify this, you can, if you think it will help you write better code. And right here, instead of false, we will be passing true, because this is the computer player. After we have our instances, we have our dice, we have our players, now we can create our game. For the game, we pass the two instances of player. This should be dice game, okay? The name of our class, dice game. So we're passing my player and computer player. And we are creating our game instance. And after that, we can start the game. How do we start the game? Well, remember that our dice game class that we defined has a play method. And this method is the method that we will call outside the class to start the game logic. So far we haven't implemented game over. We will do that before we complete the game, but right now we will have an infinite loop. We can stop that when we need to. Okay, so we're just going to run this to check how it's working so far and if we need to change anything. Game.play. We are using the instance game to call the method play. If we run this code, we will see this right here. Let me expand this and we see welcome to roll the dice. I think the number of equal signs right here is okay. You can adapt it to your liking. Then we see right here, new round. Press any key to roll the dice. Let's press enter. And we see the result of the round. Your die was 6, computer die was 2. So you won the round. You got the highest score, the highest value. Your counter is 9 and the computer counter is 11. We decremented the counter of the winner by 1 and we incremented the counter of the loser by 1. So far the entire functionality is working correctly. Let's see what happens if we lose. The computer won this round. Try again. Your die was 4 and the computer die was 6. So now the counters are equal again. Now let's press again and let's see if we can get a tie to see how this works. Right here we see it. It is a tie. Both of them got the number 5 as the value of the die and the counters were not changed. These were the previous values of the counters, 10 and 10, and they were kept exactly the same after the tie. Awesome! In the next video, we will define some new methods to make our functionality more modular, to define smaller and more easily maintainable methods than this one right here. We have a lot of things going on here. The same method is welcoming the user, it is rolling the dice, it is showing the values, determining the winner, and it is also showing the counters. So that's a lot of responsibility for one particular method. So we will do that in the next video. We will define those smaller methods. I will see you in the next video. Awesome, so now let's break this method into several smaller methods that we can work with more easily and reuse if we need to in our code. Let's see. First, we can define a method to welcome the user. To print this message and welcome the user in case we need to show this anywhere in our code. Welcome the user to the round. We will keep the main welcome message here in play. We can also define another method, but that is a challenge if you would like to define a method to print this message. Let's do that. We're going to cut this code and we're going to define a method right here below. The method will be called print welcome. We could also call it print round welcome. Let's call it print round welcome because we are specifically welcoming the user to the round. We add a new line here to preserve that rule of PEP 8, and we see a warning that tells us that this method may be static. Static methods are methods that are not related to any particular instance. They are actually like independent methods that do not need to work with any instances. In that case, we can convert the method to a static method. But for now, we're going to keep it, and we're going to keep that warning until we see a little bit more about those different types of methods, okay? It will not affect the functionality in any way. Okay, so we have that method, and we have to call that method where we used to have these lines of code. So we go right here where we had the comment, and we call the method. Remember how to call a method from the class. We write self and the name of the method. If the method doesn't take any other arguments, we just write empty parentheses like we would if we called a normal function that doesn't take any arguments. Great! Now we have that functionality, everything should be working correctly, and we can check that in our code. You can check that if you like. And then we are also going to show the dice in another method. Okay? We're going to cut these two lines, and we're going to define another method called showDice. This method will take two parameters, player value and computer value, and we will use them just like we used them in the main method, in play. Now we just need to call this method where we used to show the values. Self.showDice and empty parentheses. But right now, instead of empty parentheses, we need to pass the value of the player die and the computer die. It takes two arguments to print those values. We also see the same warning that says that this method may be static. You will see that warning for methods that don't use self in the body of the method. But this is another type of method that we haven't seen so far during the course. So for now, we're going to keep those warnings and it will not affect the functionality at all. Okay, these are just like suggestions. They're not errors per se. So we welcome the user, we roll the dice, we show the values. If you want, you can also define a method to roll the dice. That is another challenge that you can try when you create your project. For now, we're going to keep these two lines here. Then we're going to determine the winner and the loser of the round. One thing that I'm noticing that we can improve here is that we have functionality that is very similar here. The winner will have its counter decremented and the loser will have its counter incremented. So that is a repetitive concept that we can implement in a method. So let's do that. So we can remove these two lines and make them only one line. Right here below, we are going to define the method update counters. Self, winner, and loser. This method will take the winner and the loser and it will decrement the counter of the winner and increment the counter of the loser. Winner dot decrement counter and loser dot increment counter. We will tell the method who is the winner and who is the loser, and we will update the counters accordingly. So let's call this method to update the counters right here. Here we are updating the counters and here we are updating the counters. Now we are going to delete these two lines and instead we're going to call the update counters method. Remember, we use self because this is a method of the class. This is a method in the class that we are working with. We need to tell this method who was the winner and who was the loser. One way of doing that is passing a reference to that instance. In this case, the player is the winner and the computer is the loser. So we pass the player first and then the computer. But this is not very readable, right? You cannot determine immediately who is the winner and who is the loser. You would have to go and jump to this method definition to determine the order of the parameters, or you could just use this hint that PyCharm gives you, winner and loser. But if you want to make your code even more readable, you can specify the name of the parameter. And voila. I think this is much more readable, okay? Winner and loser. Whenever the argument is not self-explanatory, or whenever you think that this can improve the readability of your code, I recommend using keyword arguments. Okay, so now we're going to do exactly the same, but now the computer will be the winner and the human player will be the loser. Self.update counters. And now the winner will be self.computer. And then the loser will be self.player. Else we have a time. And like you can see, we have much more compact code right now for the play around method. And we have a lot of helper methods to perform those smaller tasks. And finally, we can define a method to show the counters. We cut this code and right here below we define a method called show counters. Like you can see right here, this method doesn't have that warning that we do have in other methods. Why? Because the difference is that right here we are using self. So we are using that particular instance, that reference to the instance that is calling the method. And right here we are not using self. So that is why we get the warning, but it will not affect the functionality. It's just a different type of method that you can create and work with. Okay, so in this case, we don't have to update anything. We just print the counter that corresponds to the human player and the counter that corresponds to the computer player. Now we do have to call this method where we use to show the counters, self.showCounters. This method doesn't take any arguments, so we can just write the parentheses right here empty. Awesome! We have a much more compact method right here, and the functionality should be exactly the same. Let's test this. We have the instances that we created in the previous lecture, in the previous part of the project, and we are still starting the game with the play method. So let's run this again. We say stop and rerun if the game was already running. And we see the game again. Welcome to roll the dice. New round, press any key to roll the dice. And again, we see the rounds, the computer, your die, the computer die, you won the round, your counter, and the computer counter. We have ties, the player can win the round, the computer can win the round. So everything is working like we expected. Awesome, right? The only thing that we still have left to implement is game over. When either one of the counters is 0, the game should stop immediately and it should say who won. So that is exactly what we will be working with in the next part of the project, in the next video. So we can stop main with this little red square, and in the next video we will implement game over. I will see you there. Great, so now that we have our class almost implemented completely, let's implement game over. This is a to-do that we had right here pending and waiting for us to implement it. So let's do that to complete our dice game. Remember that play was our main method. It was like the entry point to our game. When we call this, the entire game logic starts. And the process was almost like infinite. It would run an infinite number of times until we stop it. But according to the requirements, the game should stop when either one of the counters reaches the value 0. And that player will be the winner. So let's implement that. Here in play, we are going to call a method called checkGameOver. This method will check if the game is over or not, and it will handle it appropriately. It will return a Boolean value, true or false. This Boolean value will tell the program if the game should be over or not. If that value is true, then we will stop the infinite loop and the game will end. Okay? So let's define this method below. We go right here below show counters and we start defining the method. The method is checkGameOver. The first thing that we should check is if the counter of the human player is equal to 0. If that is true, then we should handle game over. Okay? Let's write this as a to-do. Else, if we see an error right here because to write an empty conditional, we should use the pass statement. This acts like a placeholder for you to write the basic structure of your conditional or function or class and then go back to implementing it. Game over, the player won. Okay, this is a to-do. Else, if the computer player is the one whose counter reached the value 0, then the computer won. So we have exactly the same right here. We're going to implement it in just a moment. And in this case, the computer won. Else, no one has won yet, and we should return the value false because the game is not over yet. Remember that checkGameOver is going to return a Boolean value. Then that Boolean value will be assigned to game over, and then if that value is true, we're going to break out of the loop. The program will stop, the game will stop. So we have to return either true or false from all of these conditions. We're going to return true in these two cases because in both cases, if either one of them won the game, then the game is over. So we return true, and if neither one of them has won yet, then we return false. Now is the time to start implementing these to-dos. What happens when the player wins or what happens when the computer wins? For that, we're going to define another method, showGameOver. That method will show a descriptive message, showGameOver, self is the first parameter, and then we will need to take the winner. We're going to take the winner to know how to customize the message that will be displayed at the end of the game. You have to congratulate the winner if that was the human player, or you have to tell the user that the computer won. So let's do that. If the winner is the computer player, then we will print a message saying that the computer won the game. Sorry. Right here I have this message. You can write it any way you like, but right here I am writing a sequence of equal signs, game over, and then an emoji with stars, with sparkles. The computer won the game. Sorry. And right here I really like to add a lot of these rows. I think it gives it like a classic game feeling. Else, if the winner is not the computer player, then it is the human player. In that case, you have to congratulate the user. You won the game. Congratulations. Add a dot right here. And that is the message that the user will see. Notice that right here we are using the isComputer property of the player class. We are checking if the winner is the computer player or not. If this is true, then the winner is the computer player. If it's false, then it is the human player and we congratulate the player. You won the game, congratulations. We defined the method, but we haven't actually called this method yet. This is part of the to-dos that we have right here. Instead of pass, now we are going to call this method show game over. Show game over. And we need to specify the winner. Who won the game? The player. The human player. Else, if the computer won, then we call the method show game over. And we pass the computer player. Okay? The computer player. Since we are passing a reference to the player or the computer player as the winner, right here we can access its property, its attribute, isComputer. We know that this value, winner, will be an instance of player. All of that would be documented in your documentation strings, something that you will learn how to write during the course, one of the final sections of the course. That is part of the documentation. You would tell your users that winner is an instance of player and that you will be working with properties or attributes of those instances. There are many ways to implement this functionality. You can also just choose to return a Boolean value from this method and call this method from the main play method, show game over. You could also return the winner from this method and then call this method from play. Those are all different decisions, different ways to implement the same functionality. So I encourage you to start experimenting with that and to try other alternatives. Now let's add these two lines below the class where we create the instances. Remember that right here below we still have our instances there and we are starting the game. So if we want, we can start playing. Now we have our entire functionality implemented. We can check game over right here in the main loop of the game in play. So we are calling this method, then we are returning a Boolean value that determines if the game is over, and then we break out of the loop. So let's see how this works. Let's run our code. Welcome to Roll the Dice. New round, press any key to roll the dice. I press enter, your die, computer die, you won the round, your counter, computer counter, and so on. Then we press another key again. We see how the counters are updated and how the dice are rolled. We see ties, you won the round, the computer won this round, and we can continue the process until one of the counters reaches the value 0. This can take a while because it's completely random, so let's continue for a few minutes or until the counter reaches the value 0. And right here we see it. We have a new round, we press the key. Now your die was 3 and the computer die was 6. The computer won this round, try again. Now, your counter is 20 and the computer counter is 0. So since the computer counter is 0, we see game over. The computer won the game. Sorry. Awesome, now we have the functionality of the game implemented and we even check if the game is over. So that's really, really awesome. Congratulations for completing the game. In the next lecture, we will make some small modifications to the strings to present in a nicer format. So I will see you there. Welcome back. Now we have the entire functionality of the game implemented. The only thing that's left is just a few characters here and there to make our output more readable. I personally think that they help you to create a better game. Like right here, we should add a new line character, a backslash followed by an N, to add a blank line before we start each round. Then we should also add another new line before we show the counters. And that's basically all the changes we need to make, these two small changes. But you will notice that they make a huge difference in the output. Let's run our code. And you can see that now we have the output. Welcome to Roll the Dice. New round. We see that we have a blank line between the welcome message and the round. We press any key, and now we see the result of rolling the die, and we see a blank line before the counters. We can also add a blank line right here before this result to highlight it even more. Let's do that. These messages are printed when we determine the winner and the loser. So instead of adding a new line before each one of these messages, let's just print a new line after showing the dice. We go to Show Dice, and after the last line, we write / followed by an N, a new line character. We stop the game, and then we start the game again, and now we see this. Really nice. Now we see a blank line after the results of rolling the dice. We see the result, and we see a blank line before the counters and before starting another round. So now we do have our full game functionality and presentation completed. Great work so far. Think about how far you've come since you started learning object-oriented programming. Now you're able to create a game with these principles, understand them, and analyze a project description to a point where you can translate that description into code. So, congratulations! You've come a long way, and we still have a lot to learn during the course, but you're already mastering the basic principles of object-oriented programming, and you can create really powerful programs with these concepts. Take a moment to experiment with this project. If you want, you can save a copy of the original code and then start experimenting. Try out different variations, define different methods, modify this code and make it your own. And then if you want, you can share it in the Q&A, or you can share it with me through a message. I'm always happy to see what you create. We're done with the project. I will see you in the next section. Great work during the first part of the course. Now in this section, we will start covering how objects are stored in memory and how this is related to your Python code. You might have heard this phrase before. In Python, everything is an object. And this is actually true. Let's see why. Let's see some examples. Let's confirm that basically everything that we have been working with so far is an object. Let's first write a print statement, and let's print the word object. You can see that this word changes color because this is a special word. Right here we can see the output, class object. Object is the base class from which all classes in Python inherit. This defines all the basic attributes and functionality of any object that any object should have. Let's start testing whether values that we have been using so far are instances of this class. So we will print isInstance. Let's check if an integer is an instance of object. Initially, we might not think that this is an object, right? But let's see what we get. Right here, we see the value true. 5 is an instance of object, so integers are objects as well. Let's comment these lines out, and now let's print if, for example, a list is an instance of object. This makes more sense, right? Because lists have methods that we can access. So right here we see true. Now if we test this with, for example, a tuple, we can see that this is true as well. Let's also test strings. Hello world. Let's see if this is an instance of object. Right here we see the value true. If we make a very simple dictionary, like this one for example, let's test if dictionaries are objects as well. And that is true. We see right here in the output. Something that you might find surprising is that truth values are objects as well. The value false is an instance of object. You can see true right here. And if we pass the value true right here, we also see the output true. So truth values are objects as well. And last but not least, we will test if functions are objects. So right here, we have a function definition, a very simple function, and we're going to test if this function is an object. We just pass the name of the function right here. We're assigning a generic name, f, which is really not very descriptive, but we're just using this for the example. And object, if we run the code, we can see that this is true. Functions are objects as well. And finally, if we define a generic class, let's say movie, and we just assign a basic init method, like for example title, if we check if this class, the movie class, is an instance of object, we can confirm that classes are objects themselves. The movie class itself is an object. So basically, everything that we have been working with so far is an object, and you can confirm that basically everything in Python is an object. So as you saw in the previous examples, basically everything in Python is an object, including integers, floats, booleans, functions, lists, tuples, dictionaries, strings, exceptions, and any other element that you can use in your code is an object. So let's see how they work. An object is stored in memory when it is created after running the program. The particular place in memory where that object is stored can be identified by its ID, which is the memory location where it is being stored in the computer's memory. For example, when we create a list object in our program, that object is stored in memory. Let's say that this box represents that place in memory, and that place in memory is referenced by the variable that we assign it to, if we assign it to a variable. In this case, we are assigning it to a variable, so this memory location is referenced by that name. That object is assigned a unique ID, that particular memory location while it exists in the program. The ID represents the memory location of the object. If we create another object, like for example right here we have two list objects assigned to different variables, the second object will be stored in memory as well in its own memory location, and it will have its own unique ID while the program is running. This principle can also be applied to other types of objects, including strings, tuples, dictionaries, and even objects from classes that you have defined. Where we create instances, for example, of the dog class that we've defined previously in our code, we create objects that contain attributes and data, and these objects are stored in memory. When we assign them to variables, we are just assigning a reference to that memory location to the variable. And each one will have their own unique ID while the program is running, or while they exist in the program. Every object that you create in the program is stored in memory while the program is running and while the program is able to access that object. Programs keep track of how many references to the object exist. And what is a reference? Well, a reference is just a name that refers to the location in memory of an object, so we can access it and work with it in our code. Examples of references include variables, attributes, and any other item in our code that somehow references the object and keeps it alive and accessible for us in the program. We use a variable to access an object. We use an attribute to access an object. And we can also use other types of items. For example, if the object is part of a list or if it's part of a data structure, that will keep the object alive and referenced in our program. Variables in Python store references to the objects in memory. This is very important because sometimes we might think that when we assign a value or an object to a variable, that variable holds the object. And this is not the case in Python. In Python, variables store references to the objects. The object is stored somewhere in memory, and the variable knows where to get that object from memory because it has a reference to that object. We have like an intermediary. The variable knows where to look for the object in memory. And that is basically what happens behind the scenes. So when we assign a value to a variable, we're actually assigning a reference to the memory location where this object is stored. Somewhere in memory, Right here we have the object 5. The variable knows where to look for that particular object in memory. When there are no references left to the object in the program, then the object is deleted automatically from memory. This occurs when the object is no longer accessible by the program. We have an object right here that we created and we stored in memory. But in the program, we have no way to access the object because there are no references, variables, or items that we can use to work with the object. In that case, the object is just deleted automatically from memory by Python. This process is called garbage collection, and it is done automatically to improve memory usage, to optimize the efficiency of Python programs. Great! Now take a moment to think about the importance of garbage collection. Why is it important that objects that are not used or cannot be used anymore are deleted from memory? Think about this and then go to the next video. I will see you there. Now you will learn about the ID function in Python and how it is related to the objects in your program. This is the ID function. ID followed by parentheses, and in those parentheses we will write the name or the variable that references the object in memory for which we want to find the ID. This function basically returns the address of the object in memory. Remember that we said that when we create an object, that object is stored somewhere in memory at a specific memory location. This function helps us know the address of the object in memory. This is the ID that we mentioned in the previous video. Let's see what we can learn about it in the documentation. If we go to the Python documentation to the article on built-in functions, right here, if we go to the third column, we can find the ID function. If we click on it, right here we see that the function ID takes an object as argument, so we will need to specify an object when we call ID. The function returns the identity of an object. This is an integer which is guaranteed to be unique and constant for this object during its lifetime. This is really important, during its lifetime. Two objects with non-overlapping lifetimes may have the same ID value. This last line is very important because if an object doesn't exist anymore, the same ID can be assigned to a different object. So it is guaranteed to be unique and constant for an object only during its lifetime. In CPython, the version of Python that you download from the official website, the ID is the address of the object in memory. Okay, so that is the meaning of the integer that we will get, the address of the object in memory. So now you know the purpose of the ID function, and that the ID is unique for each object while the object exists in the program. Let's see some examples of the use of the ID function. If we create an object in our program, we can use the ID function to find that unique integer that identifies the object and its location in memory. For example, if we want to print the ID of an integer, 15, we can do so. We save the file, we run the code, and right here we see the memory address for that object. This is a unique integer that will identify this object while it exists in the program. Then, for example, we can check this, hello world. If we comment out this line and we run the code again, we will see this number, which is different from the previous ID for the integer. You can see both of them right here. They are not the same object in memory. Also, each time we run the program, you will notice that the numbers are different because the objects are stored in different places in memory each time we run the program. They are not kept at the same memory location after the program completes its execution. We can also find an ID for a list that we create in our program, right here. Let's also see what happens if we have two lists with the same value, like 1, 2, 3, 4, 5. What will we get right here if we print the ID of A and the ID of B? We can also pass right here within parentheses as argument the name of the variable that references the object. In this case, we are finding the ID for A and the ID for B. We run the code, and right here we can see that these values are different. So these numbers are indeed unique. And what is this telling us about the objects? Well, that they are stored in different locations in memory. So these two lists are separate objects. Each one of them is stored at a different memory location. Try this yourself. Create some objects in Python and check their ID. Welcome to this example. Now we will apply the ID function to instances of the backpack class that we create. Right here we have our class with the init method and an initially empty list of items. To complete the class and to make it a little bit more realistic, let's add a getter for the items attribute, like this. Okay, so now let's define our two instances, my backpack and then your backpack. We will check that they are indeed different objects because they will be stored at different memory locations. How can we do this? Well, we are going to print the ID of my backpack. That will give us the memory location of this object. And then we are going to print the ID of your backpack. We will see where these two objects are stored. And if they are different, we can confirm that they are different objects in memory. Let's save the file and run the code and see what we get. Right here we see that the numbers are indeed different. These digits are basically the same, but these last 4 digits are different. So we know that these two objects are not the same object in memory. They are stored at different locations in memory. And this is how you can use the ID function to confirm that your objects are different objects in memory. This will be very helpful when we start talking about aliasing, mutation, and cloning. In Python, we have an operator called is that is very closely related to object-oriented programming. Let's see what it is and how we can use it in our programs. This is the basic syntax of the is operator. We write two objects as the operands, one to the left and one to the right of the operator, and we ask if object 1 is object 2. When we write this, we're actually asking if these two variables reference the same object in memory. Right here I'm writing object 1 and object 2, but really they will be variables referencing objects. If the variables reference the same object in memory, this will be true. If not, this will be false. Let's see what we can learn about this operator in the Python documentation. In the expressions article of the documentation, right here we can click on the table of contents where it says identity comparisons. If we click on it, we will reach the part of the documentation that explains more about the is operator. We see identity comparisons. The operators is and is not test for an object's identity. An object has a value, an identity, and a type. The is operator tests the identity. So x is y is true if and only if, so this means that the comparison should work both ways, x is y and y is x, only if x and y are the same object. An object's identity right here is determined using the ID function. So you can see that they are closely related. When the IDs are the same, is will be true. When the IDs are different, they are different objects in memory, so comparing them with is will be false. We can also use the combination is not to test if an object is not another object. This yields the inverse truth value. If we apply the ID function to two variables and their IDs are different, then that means that they do not reference the same object. And that will be very helpful to determine the result of the is operator. For example, right here we have two lists with the same value. But since we are defining them like this, they represent different objects in memory. In memory, they are kept or stored at different memory locations, and they are independent. So their IDs will be different. In contrast, if two variables do reference the same object in memory, then when we apply the ID function, they will have the same ID. For example, right here we have two variables that reference the same object in memory. This object right here, the list. Right here we are creating the list and we are assigning it to the variable a. We are assigning a reference to this object in memory that points right here to this location. And right here below, when we assign a to b, we are actually assigning the same reference to this variable b. Therefore, right here we have the is operator, which is a very helpful tool. The is operator returns true if both operands reference the same object. If the two variables or references reference the same object, the result will be true. Else, it will return false. I'm sure that you must be asking yourself right now about the difference between is and the equal to operator. How can we use them and how are they different? Well, they are actually quite different in their functionality. Let's see why. The is operator checks the objects that we are comparing, checks if the references or the variables actually point or refer to the same object. But the equal to operator checks the values of the objects. And you can customize how this works behind the scenes. You will learn how to do this when we reach special methods. But for now, we are just confirming that this checks the values of the objects. It returns true if they both have the same value and false otherwise. So two objects may have the same value like you saw in a previous example, and they can still be different objects in memory. Because they will be stored at different memory locations, they will be independent, and changing one of them will not affect the other one. Right here we have an example. We will see an example of how two objects can have the same value and still represent different objects in memory. If we define these two lists, A and B, with the same value because they contain the same elements, then let's see what we get from the is operator compared to the equal to operator. If I write A is B, that is not precisely the same as writing A equals B. This will be true if A and B are the same object in memory, but this will be true if they have the same value, and that is very different. An object has an identity, this one, a type, and a value. And they are not necessarily the same. Let's save the file and run the code, and right here you can see that these values are different. A is B was false, because these objects are not the same object in memory. Their identities are not the same. And A equals B was true, because they do have the same value. We can also test that the is operator is closely related to the ID of an object. Because right here, if we print the result of calling the ID function for each one of the objects, we will see that their IDs are different. So that is why this result is false. They are different objects in memory. And this is an example of the difference between is and equal to. Awesome! Think about this difference and when you should use the is operator versus the equal to operator. Think about this and then move on to the next video to continue learning more about objects in memory. Welcome back and welcome to this example where we will test how the is operator works with different data types and different objects that we create in our program. First of all, let's start by writing two lists. But these lists will not have the same value. So let's see how this works. Right here, we have the two lists and we are going to check if A is B. In this case, that is false because these are not the same object in memory. But what happens if, right here, I choose to assign A to B? We might initially think that we are just creating a copy of this list and assigning it to B, right? But that is not the case. We are not creating an independent copy. If we run the file, we see that this is true. So these two variables are now referencing the same object in memory. And if we modify the list through any one of these variables, the other one will also be affected, because they are both referencing the same object that we are modifying. Okay? We can also check this with tuples, A, B, and C, and we have another tuple with E and F. Now let's print if C is D. And this is not true. They are not the same object in memory. But this comparison should also work the other way around. It should work if we check if D is C. That is why we saw in the documentation that this is if and only if. It works both ways. If we run the file, we see false for both of these lines. So the comparison is working as we expected. It is equivalent to compare C and D or D and C. Now let's test this with some strings. For example, hello world, and then hello world. Right here, we are comparing two strings that do have the same value. So let's see what we get. Right here we have to delete this. E is F, F is E. We save the file, we run the code, and we see true as the output. And this is something that you will learn more about in the coming video. Why, if we are defining them separately, we're creating two separate strings right here like we did with the lists, and we are also assigning them to different variables. So why are they the same object in memory? You will learn more about these unexpected results in a coming video in this section. And let me tell you that it is very interesting. It has to do with something that Python does to optimize memory usage. Great work so far. Now you know what the ID of an object is, how to use the ID function, and how this function is related to the is operator. When you're ready, go to the next video, and I will see you there. When you work with the is operator in Python, there might be some unexpected results. For certain values, the result might not be what we initially expect. And these variations come from implementation details of Python that are used to optimize memory usage. This can vary a lot depending on your programming environment and your Python version. For example, let's see one of the unexpected results that you might get. If we assign the value 5 to these two variables A and B, and then we print the result of A is B, to check if these two values represent the same value in memory or not, we run the code, we will see that this is actually true. These two variables reference the same object in memory. But we didn't do this explicitly. We didn't write something like this, like we used to do before, right? So what is happening right here? Let's see more about this. Small integers are one of these cases. Specifically, small integers ranging from -5 to 256. If we go to the documentation, we can learn more about why this happens. We can go to the article Integer Objects, and right here you will see below a very small paragraph that explains what is happening behind the scenes. We see that the current implementation keeps an array of integer objects for all integers between -5 and 256. When you create an int, an integer, in that range, you actually just get back a reference to the existing object. So when we access one of these integers from -5 to 256, we're actually reusing existing objects. The integers with the same value will be the same object in memory. We are reusing an object that already exists in memory. And we can confirm this in our code. Let's do that. Let's try this again with a number in the range that we saw, -5 and 256. If we check if A is the same object as B, and we run the code, we see this value, true. We are getting a reference to the existing object that represents the value 3. But now let's use a number, let's assign a number that doesn't fall in that range. We said 256. 256 was the upper bound of the range. So let's use 257. Now, if we check if these two variables reference the same object, we also see true. These two values reference the same object in memory. This is a memory optimization done by PyCharm. Because, for example, if we write the number 15,000, and then we check if these two objects are the same, then we get true. PyCharm is optimizing this for any number that we can write in our code. Like, for example, 15,345. But let's see the difference with another programming environment, like idle. And I am defining these two variables, a and b, with the number 257. A is b, now evaluates to false. Previously, it was true when we worked in PyCharm. Now let's write 256. And now we see that this is true. Now let's test this with the lower bound of the interval. This is true, -5 is being optimized. We are using the existing object in memory. But now let's write -6, and let's see what we get. Now we are not optimizing this in memory. We are not reusing an object. This is not being reused. But in PyCharm, we are reusing this object. If we write -6, this is true, because these numbers are referencing the same object in memory. The environment in PyCharm is sort of optimizing memory usage. Strings also have certain memory optimizations, like in the example that you saw in the previous video. We defined two separate strings, but they were actually the same object in memory. And this is done through a process called string interning. Let's see what it is with an example. Let's see what happens if we try to determine if these two variables reference the same object in memory. Right here we have a string of length 1, the same string. If we save the file and we run the code, we see the value true. These two strings represent the same object in memory, so these two variables reference the same object in memory. And how is this possible? Well, strings are immutable, so they cannot be changed after they are created in the program. If we try to update the value of a string of a character in a string, we will get this error. Type error, string object does not support item assignment. This tells us that strings are immutable and they cannot be changed. So that is why we have the process of string interning. This is the process of keeping only one distinct copy of the string in memory, and then reusing that copy when we need to in our program. We're only going to create one object. Let's think about this for a moment. Strings are immutable, right? So they cannot be changed. So it really doesn't make sense to create a separate object in memory for each one of these strings since they are all the same. Sometimes what Python will do is optimize memory usage by just creating one object for that string and then reusing the object throughout the program. So when we try to use the string again, we will get a reference to the same string that we created before. And this will not cause any problems because the string is immutable. It cannot change. Let's see some examples of this, and now we will use the id function. Let's see what happens with a very simple string, like for example, hi. We will check this with the id of the string. Let's see if the ids are all the same. If we assign the same string to multiple variables like a, b, c, and d, like this. If we assign the same string to these four variables, what will we get? As you can see, we get the same ID for all of them. So they are all represented by the same object in memory. This object was created in memory, and all of these objects, the subsequent strings that we use that are equal to it, are sort of like recycled. They use the same object that we initially created because strings are immutable. And this is a memory optimization that Python can make behind the scenes. So if we check if A is B and B is C and C is D, we see true, because all of these variables reference the same object in memory. Now in this short lecture, we will see some of the internal details of what actually happens when we pass objects as arguments to functions in our code. In a programming language, usually objects can be passed by either value or reference. Passing an object by value just means that we make an entirely new copy of the object when it is passed as an argument to the function. And passing the object as reference means that we take a reference to the object as argument, sort of like the flag of where that object is stored in memory. And if we make any modifications to the object while the function is running, those modifications will affect the object directly in memory, if the object is mutable. In Python, objects are passed by reference. So any changes that we make to the object in the function will affect the object permanently, if the object is mutable, like a list. We pass a reference to the object, so we don't pass a new copy. The original object can be modified. Let's see an example of this. For example, if we define a list, like this one right here, and then we define a function, print data, or print elements, for example. We're going to print the data stored or the value stored in the list. For every element in the sequence, what are we going to do? We are going to print that element. Let's call the function print data, and let's pass the sequence A. Let's rename this to my list to be more descriptive, like this. And then as the output, we see this right here. The function runs, and each one of the elements in the sequence is accessed. But right here, notice that we are passing an object. We are passing the list object that we defined right here. And this object is passed by reference. We get a reference to this object, and we see right here the parameter that will take that reference. We can confirm that we are actually working with the same object inside the function if we print its ID. We're going to print the ID of the parameter, let's say inside the function. And we are going to say, first, we're going to print outside the function. Let's see if the ID of the list and the sequence are equal. That way we can confirm that we're referring to the same object in memory even after we call the function and once we're inside the function. This is what passing by reference implies. We're not creating a copy of the list. We're working with the same list object within the function. We save the file and we run the code, and right here we see the output that we expected. We see outside the function, this is the ID of my list. This is the output that we get from this line of code. Outside the function, and we print the ID of my list object. And then once we call the function and we start running its code, we can print the ID of the sequence that we are getting inside the function. And that ID is the same ID of the list. We are not creating a new object when the function starts running. We are referring to the same object in memory, the same list. When we pass the list as argument right here, we are actually passing a reference to the object. We are passing sort of like its ID, a flag that tells the program where that object is stored, so it can be modified and accessed. Now we will work with the same list that we just defined in our previous example, my list, but we will define a function that will change the sequence, change the list. We will say for I in the range, for the length of the sequence, for each one of the elements in the sequence, what do we want to do? We want to multiply each element by 2. Okay, so we can call this function passing my list like this. In our previous example, we didn't modify the sequence. We just confirmed that this sequence that we're passing right here as an argument is the same object, the same sequence that we are working with inside the function. We are passing that object by reference. But right now, we will see how we can modify the sequence inside the function because we are passing it by reference. Let's write the print statement that we wrote before, outside the function, and then the ID of my list. And then we're going to copy this when the function starts, but now we will say inside the function. This will modify the list, the original list in memory. Okay, so after we modify the list, we want to check its new value. It will mutate the list object that we have right here. So after we call the function, this will be different. Let's save the file and run the code. We see the output. Outside the function, we have this ID for the list. And we can see that this is the same ID that we get inside the function. We are passing a reference to this sequence, so we can modify the original object in memory and access its values. In the function, we are multiplying each one of the elements by 2, and then reassigning that result as the new element. All elements were multiplied by 2, but this modified the original object that we passed as an argument. We didn't make a new copy of the list. We modified the original object that we passed by reference. If we have a function findTotal that takes a list of sales objects, we can pass it as an argument. We can pass this list as an argument and operate with the individual values by reference. Like we do right here, we have an initial total which is equal to 0. We have a for loop. For each sale in the list of sales, this will be an object of type sale. And then we access the amount of the sale or the total of the sale, and we add that amount to the total sales. And then we return the total. In the list that we will pass as argument, we will hold the individual sale objects as elements. We will use them in the for loop. So when we iterate over the list of sales, we are actually assigning each one of the sales to this loop variable right here. First, it will be this sale object with an amount of 400, then the second sale object with an amount of 345, and finally the third sale object with an amount of 45. Let's see how this works if we have a list of objects. Right here, we will define the sale class. And what do we want to represent for each sale? Well, the total amount of the sale. We will make this class simple because we want to illustrate the principles of how we can operate with lists of objects in our program and combine object-oriented programming with imperative programming, writing our code line by line. We will define our class and we will also define a function. This function is not part of the class. The function just takes a list of sales and finds the total amount from all the sales. So we say, for every sale in the list of sales, we want to add the amount of the sale to the total, and then we will return the total, like this. We could also assign a more descriptive name, like this, sales list. This will be a sale object. We know that it will be a sale object, so we can access its attribute amount that we've defined right here in our class. After the function, we can make, for example, a list of sale instances. January sales. We create a sale instance with an amount of 400. Then we create another sale instance with an amount of 345. And then we create another sale with an amount of 45. Right here, we are creating a list that contains sale objects, and we are creating the objects directly right here. After we have our list of objects, we can just find the total of all the sales by calling this function, findTotal. January sales. We are passing the list of sale objects. We have it right here as the parameter, and we are passing it as an argument. So we call the function, and the function will return the total of all the sales in the list, and we will print that value. If we save the file and we run the code, we see the value 790. This is 745 plus 45 is 790. If we want to see how this process is evolving, we can add some print statements. New sale, and we can print the sale amount, like this. So we can see the process. New sale, 400, this instance that we have right here, then new sale, 345, the second instance, and finally new sale, 45, the third instance that we have right here. So you can see that we can use our objects in our code as well. We can combine different programming paradigms. Great work so far. Now you know how objects are stored in memory, what the ID of an object represents, how to use the ID function, the is operator, and how to work with objects in your program, combining different programming paradigms. Welcome to this section. Now that you know how objects are stored in memory, we will dive into 3 new concepts: aliasing, mutation, and cloning. You will commonly find them when you work with object-oriented programming. So let's begin. Think about this for a moment. In the real world, what is an alias? What do we use aliases for? Pause the video and then come back, because we will be covering aliasing first in the section. Welcome back. According to Merriam-Webster Online Dictionary, an alias is used to indicate an additional name that a person sometimes uses. In programming, having an alias is very similar to that, because an object has an alias if there are 2 or more references to the same memory address or to the same object in the program. This is an example. Right here we have 2 variables, A and B. We saw this example before in the previous section, but we were focusing on the fact that they both point or reference the same memory location. Right now, we are focusing on the fact that we have 2 different names referring to the same object, to the same memory address. And this is what an alias is in object-oriented programming: 2 names or more that refer to the same object. If we define, we create a list object right here, and then we assign the same reference to another variable, then we can access that list object with any one of these 2 variables. And we can modify it, we can access it, and we can use that object in our program with these 2 aliases that we are creating. We can confirm that they are aliases with the ID function, like this. Why? Because if the IDs are equal, then that means that the 2 variables are aliases for the same object. And we confirm that they are indeed aliases because they have the same ID. We can also check this with the is operator. If A is B, that means that both of these variables reference the same object in memory. So let's save the file and run the code, and we see that this is true. Both variables reference the same object in memory, so they are aliases. So basically, an alias is just a different name that is assigned to the same object. And these multiple names are active in the same program. We can access or refer to the same object with either one of those names. We can even have more than one alias in the same program. Let's see an example of this in our code. We can, in theory, create more than one alias in our program, although this would not be recommended. But in theory, we can do that. And we can reference the same object with any one of these aliases, A, B, C, or D. Notice that right here we are assigning the reference of A to B, then B to C, then C to D. If we check if they are all referencing the same object, then we see that this is true. We can check this with the ID function. We just need to write 4 print statements right here, A, B, C, and D. We run the code, and now we see that the 4 IDs are equal. So they are all referencing the same object. We could also assign the reference of A to each one of these variables, and it will work exactly the same. This is what is happening behind the scenes in this example. All of these variables that we have defined right here, A, B, C, and D, are referring to the same object in memory. And right here, this is just a sample ID, a sample number that could have been the ID for the object. They would all have the same ID, okay? Because they reference the same object in memory. And that is part of the importance of ID and the ID function that you learned about in the previous section. This way, by using the ID, we can identify if 2 or more references are aliases for the same object. Now think about the risks of aliasing. We will cover this in this section, but start thinking about what do you think could happen if two or more variables reference the same object in memory. Is this good? Is this bad? And what are the risks? Welcome to this example where we will dive into aliasing with classes that we define in our program. Let's start with our circle class. We start by defining the init method with just a radius to keep the class simple. First, we will define a myCircle instance. This instance will have a radius of 4. And then we are going to create yourCircle, another instance. But now we are going to assign the myCircle instance. Initially, you might think that you are creating another circle object, like a copy, and assigning it to your circle. But you're not. You're just creating another name for the same circle. These two names will be used to access the same circle right here. So, let's check if they reference the same object. If myCircle is your circle. That is true. MyCircle is your circle, so they are aliases. They have the same ID. What are the implications of creating aliases like this? Well, if you don't know that these two names reference the same object in memory, you might make some modifications to this, for example, to this instance, and then believe that that will not affect this instance. And this is a likely source of bugs in your code. For example, let's say that you don't know that they reference the same object. So you want to update the radius of your circle. What is going to happen? If now we print the radius of myCircle and we print the radius of your circle, let's print the radiuses before and after we make this change, and we save the file and we run the code, you can see that before we make the change right here, the radius was 4 for both instances, because they are both referencing this circle object with radius 4. Then we update the radius of your circle to 18. But this is surprising if you don't know what aliasing is in Python. We expected to change your circle's radius to 18, and right here we changed it. But we also changed this one to 18, the radius of myCircle. Why? Because they are the same object in memory. And that is a very likely source of bugs if you don't know the concept of aliasing and how to work with it and even avoid it in Python. Awesome! This was our first example with a circle class. Now let's go to another example of our backpack class. You will see how modifying one of the backpacks changes all the other aliases that we can use in a program. Let's start by defining our backpack class. In this case, we will just write the items attribute and add a getter so we can access the items attribute, like this. Okay, so we will create a backpack instance, like this. Then your backpack. We have another instance, and then we can say, for example, her backpack. In this case, we're creating 3 separate instances, but let's say that we don't do this. And instead of this, we just assign this, but like this, expecting that we will be creating sort of like copies of the backpack. If we are not aware of the consequences of creating aliases, we might end up with something like this, 3 aliases for the same backpack object. If we print the result of using the is operator on these 3 instances, we can see that the 3 references point to the same object. They are all referencing the same object in memory. So let's see the possible consequences of doing this in our program without knowing that we are doing it. If we define the method addItem that we had in some of our previous examples, self.items.append item, and we want to define this method removeItem, and we say if the item is in the list of items, Then we want to remove the item, else we print the message, this item is not in the backpack. Okay, so we've implemented these two methods, add item and remove item. Let's call these methods on one of the instances. For example, my backpack. We want to add a water bottle to the backpack, and we also want to add some candy. If we print the list of items in the backpack, in the instance that we have been using so far, my backpack, we see that the changes were applied correctly. The water bottle and the candy were added to the backpack's list of items. But something unexpected is also happening. If we check the list of items in your backpack and in her backpack, and we run the code, we see that now all three backpacks have the same list of items, water bottle and candy. Why? Because when we modified this object and we added these items to the list, we are actually modifying the object itself. And these three names are used to access the same object because they are aliases. As you can see, this is a potential source of bugs, so you have to be very, very careful when you create an alias in your program, and possibly try to avoid it as much as possible, because this can have unintended consequences in the program when you make changes. Awesome! Now you know how to identify aliasing in Python, how it works, and the possible consequences of creating aliases. Now let's see two very important concepts in object-oriented programming. You will see them in Python very commonly, even if you're not referring explicitly to object-oriented programming. These are the concepts of mutability and immutability. Let's see how they work. According to Merriam-Webster Online Dictionary, mutation means change. A change is a significant and basic alteration. And that is basically what mutation is in programming too. A change that we make to an object. An object can be classified as either mutable or immutable. It is mutable when it can be modified in the program after it has been defined, just like a list. And it is immutable when it can't be modified, like a tuple or a string. We can't change the characters of a string, just like we can't update the elements of a tuple. So they are immutable. Mutable data types in Python include lists, sets, and dictionaries. And the objects that we have been creating so far with our classes are mutable as well, because we can update their state. Let's see an example of something that you must have probably done like 100 times before watching this video. But this time you will see it from a different perspective, because you will actually be understanding why this is allowed in Python and what is happening behind the scenes. If we define a list with certain elements, they could be any elements in the program, and then we try to update the value at a particular index of the list. If we print the value of the list after making this modification, let's see what we get. We see the list updated. Now the element at the index that we specified was updated. Instead of 7, we have the value 5. Let's see what is happening behind the scenes when this occurs. What happens behind the scenes is that we are storing the list object in memory. But when we change it right here with the index and we update the element, we are changing the actual object in memory. We are mutating it. We are making the change directly to the object. So the variable a will now reference the updated object in memory. This is an example of a mutable object. In contrast, let's start diving into immutable objects. Immutable data types in Python include Boolean values, integers, floats, strings, and tuples. Previously, we were working with a list, so now let's change this to a tuple, which is an immutable data type. Right here, we immediately see a yellow warning provided by PyCharm that says tuples don't support item assignment. This message is telling us that tuples are immutable, so this line will throw an error. Let's save the file and run the code to see it. We see type error, tuple object does not support item assignment. And this is just because tuples are an immutable data type. We cannot update their values once they have been assigned. They're elements. Another example is a string. Right here, if we are trying to change a particular character at an index of the string to another character, we will see another warning. Because strings are immutable, we cannot change their values. Right here, we can see this. Type error, string object does not support item assignment. Right here, we are representing that we've created the tuple in memory and it has its own ID. When we try to update it, the object cannot be changed. It is like locked because it is immutable. The same happens with strings and with any other object from an immutable data type. They cannot be updated once they have been defined in the program. So remember, an object can be classified as either mutable or immutable. Mutable means that it can be modified, and immutable means that it cannot be modified. Please take a moment to think about the importance of choosing the correct data type for a value, mutable or immutable. Why is it important that we choose a mutable data type for certain situations and immutable data types for other situations? Also, think about the risks of choosing the wrong data type. Think about this, and when you're ready, go to the next video to learn more about these concepts. Welcome back. Now let's see the advantages and disadvantages of mutable and immutable objects, when they should be used, and the risk of aliasing. So let's begin. We will start with the advantages of mutable objects, objects that can be changed. This type of object tends to be more memory efficient because we can reuse existing objects and modify them instead of creating or making new copies for each small change that we have to make. We don't have to create a new copy, we can just reuse the object by modifying it in memory. They are also very helpful to represent real-world objects that are mutable by nature. However, they do have some disadvantages. For example, using mutable objects in a program might introduce bugs. Why? Because you might unintentionally mutate an object in the program. Of course, that is not enough reason to avoid using mutable objects because they are incredibly helpful. It's just that when you use them in your program, you have to be really careful about what you do with that object to avoid unintentionally mutating the object and causing unexpected behaviors in your program. Let's see an example in our code. In this example, we have a function called addAbsoluteValues. This function will take a sequence, in this case it will be a list, and it will take each one of these elements in the list. It will find the absolute value of the element, which is just its positive value, and then it will add all of those values and return the value, the total sum of the absolute values. So take a moment to analyze this function. Try to find the bug in this function. The intended purpose of this function is to keep the list intact. Analyze this line by line and see if you can determine why this is not working like we intended. Pause the video and then come back. Welcome back. The source of the bug right here is that we are replacing the value in the sequence right here. We are finding the absolute value of the element and then we are assigning that value to the list. Okay? So right here, we are actually mutating the list that we passed as argument. Remember that you learned that in Python, objects are passed by reference. So right here, when we assign a value to the list, we are mutating the list that we passed as argument. And that is not what we initially intended. Let's check this in our code. Values before, we say values before calling the function. And since the value is returned, we have to assign it to a variable. We pass the list values right here. Right here we need to add an S. And then we are going to print values after. If we save the file and we run the code, we see this. Before we call the function, the numbers are negative. Before we call the function at this point in the program. But after we call the function, the values are changed. Now they are their absolute values, which are positive. So we've mutated the list. And let's say that this was not our initial intention. This is not what we intended to do when we wrote the function. So this is an example of how mutable objects can be prone to unexpected changes. Great, now you know the advantages and the disadvantages of mutable objects. So let's check out the potential risks of aliasing, because they are closely related to mutable objects. One of the risks is mutating objects. We might mutate an object unintentionally through an alias. Remember that aliases are multiple names or references that we create for the same object in memory. When we create aliases, we might unintentionally mutate an object using one of those names and affect all the other names that reference the object in the program. So this is one of the possible risks. Like in this case, we have two variables, a and b, referencing the same list. If we change the list using the variable a, the variable b will be affected as well if we use it in the program. We will get or work with the modified object instead of the object that we believe we initially assigned to this variable. Let's see how we can mutate an object through an alias. If we define a list with the elements 1, 2, 3, 4, and then we create an alias for this list object right here, let's say that we don't know that this is actually creating an alias, and we just think that by assigning A to B, we are making a copy of the list. If we don't know this, then we might try to update a value in list B. We might write this somewhere in our program, and then if we check what happens to list B, and we run the code, we can see that list B is modified like we intended. The first value was updated to 15 at index 0. But what happens if we check the value of A? We might initially think that A is not affected because we are not writing A anywhere on this line. But if we run the code, you will see that both values are the same. A was also modified and the new value is 15 at index 0. So we're modifying the object unintentionally through an alias that could make the program work unexpectedly and provide the wrong output or results. This also takes us to the advantages of immutable objects. Since they can't be modified, they are less likely to introduce bugs in your program. So we can say that they are sort of like safer from bugs. They can also be easier to understand because we know their exact value without any hidden or unexpected changes like it might occur with mutable objects. So they are very helpful when we need to create values or objects that should never change in the program, like for example tuples. However, they do have certain disadvantages. They are less efficient in terms of memory usage if you want to modify them. Because to modify or to create a new object with some modifications, you would need to create a new copy of the object. You don't need to make an entirely new copy of the object to make any changes. And this can be costly depending on the complexity of the internal structure of the object. So in cases where the object would have to be modified, it is preferable to use mutable objects, like a list, for example, versus a tuple. Let's see an example of how we can create a new tuple based on the content of another tuple. Let's say that you've defined a tuple with the elements 1, 2, 3, and 4. You chose to use a tuple in your program, but then you realize that you have to add an element right here between the elements 2 and 3. We will add the number 7. But when we try to add an element, we realize that tuples are immutable. We cannot add an element to a tuple. So we might try to find a possible solution using tuple slicing. For that, we would have to take these two elements from index 0 to index 1 inclusive, so we write 2 right here. We might concatenate that tuple to a new tuple with just one element, the value 7, and then we might include all the elements from index 2 up to the end of the list. This would give us, let's see right here what we get. Right here we have a new tuple with the element 7 where we wanted it to be. Like this. If we print both of these tuples, we will see the change. Right here, now we have the value 7. So there is a way to add an element to a tuple, but let's see what happens behind the scenes. If we print the ID of the first tuple and we print the ID of the second tuple that we've created, right here from concatenating the previous tuples, we see that their IDs are different. And what does this mean? Well, that the two tuples are different objects. Right here, we created an object that we used initially, and then, right here, by concatenating several tuples, we're creating a new object in memory. And if this tuple is more complex, has more elements, or if the object is more complex instead of a tuple, then this would be really costly in terms of memory usage, because you are creating an entirely new object in memory. And you can confirm this with the ID. In this case, we're creating two separate objects with the same value. But the old object is no longer accessible after we update the variable. The variable A is now referring to the new tuple, the tuple that we created by concatenating other tuples. So this old object will be garbage collected automatically, since we updated the reference, and now this object, the old object, doesn't have any reference to it in the program. Great! Based on these advantages and disadvantages, think about when you should use mutable and immutable objects or data types in your program. For some scenarios, it will be very helpful to use mutable data types, and for other scenarios, it will be more helpful to use immutable data types. So think about this, and then move on to the next video. Welcome to this example, where we will see an example of what can happen if we try to work with a mutable object, like a dictionary in this case, and we perform some operations without knowing how they affect that object. This will result in a bug. We have a function called removeEvenValues that takes a dictionary as an argument. This function will iterate over all the key value pairs of the dictionary using a for loop. Like we can see right here, we have the key, we have the value, and right here we are iterating over the list of key value pairs of the dictionary. And we say, if the value of the pair is even, so it is divisible by 2, evenly divisible by 2, then what are we going to do? We are going to delete that key value pair. So far, so good, right? Initially, our logic seems to be correct. We are getting all the key value pairs, we are finding the pairs that meet our criteria, and then we are deleting the pairs. But let's see what happens behind the scenes, because I know that this might surprise you. If we have a dictionary called my dictionary with these key value pairs, A, B, C, and D, we will keep this dictionary simple to focus on the function, okay? If we call the function removeEvenValues, like this, and we run the code, we might assume that these key value pairs will be removed, B and D, right? Because we are finding even values in the key value pairs to delete those pairs. But if we run the code, we will see this. Runtime error. Dictionary changed size during iteration. Let's analyze this error in detail. This is a runtime error, so it is a type of exception thrown when the program is running. It says that the dictionary changed size during iteration. Why would it change size? Well, remember that right here we are deleting key value pairs, and this deletion occurs inside the for loop. That is why we see this line right here. When we delete a key value pair, we are mutating the dictionary. We are changing the number of key value pairs it contains. And that is essential for this value right here, because we're getting a list of items from the dictionary that are left to evaluate or to assign to these loop variables. So the loop doesn't know how many iterations are left because we changed the size of the dictionary during the iterations. So this is an example of the risks of mutation. and you have to be very careful when you work with mutable objects. But wouldn't it be really nice to be able to create sort of like a clone for this dictionary? A copy of this dictionary so we can iterate over all its elements and still modify the original dictionary. Well, we can do it through a process called cloning. You will learn more about cloning in the next video, so we'll see you there. Let's see what cloning is all about and how we can use it in Python to prevent bugs like the one that you saw in the previous example. Let's see what it is and how it works. Cloning is the process of creating an exact copy of the object, and this copy is completely independent from the original object. It is like the opposite of aliasing, because the new object that we create, the clone, is not connected to the previous object at all. It is completely independent from the original object. For example, right here we have an object and its clone. When we create the clone, they are initially exactly the same. They have all the same attributes, methods, and other properties. But if we modify the clone during the program, or if we modify the original object, then the other one will not be affected, because they are completely independent. So instead of having something like this, two references that point to the same object, so they are aliases, we will have something like this. Independent references to different objects in memory. They will be initially the same. They will have the same value initially. But we can modify them and the other one will not be affected. Previously, when we saw the risks of aliasing, we said that if we have a mutable object and we create an alias for that object, we can modify the object with any one of the aliases. We had this example, right? We said that we could modify list B, and that would also affect list A. If we print both lists, you can see that the change affects these two variables because they are pointing or referring to the same object. You can see that their first value is now 15 instead of 1. So how can we solve this? Well, we can use cloning, which is really nice. To clone a list, we can just write this. We write the syntax that we use for list slicing to get a slice of the list, and within the square brackets, we just write a colon. That indicates that we want to get a copy of the list from the first element up to the last element, including all the elements in between. So we're basically getting a clone. After adding this to our code, if we run the code, we can see that we modified list B right here. And this change was reflected for this list, list B. But now list A is not affected, and that is really awesome, right? We are no longer working with aliases. We are creating a clone of the list right here, and that clone is independent from the other object, so they are not affected. Awesome, now that you know more about cloning, let's go back to our example where we changed the size of the dictionary. Right here we have our example. The function remove even values dictionary. The dictionary is taken as an argument, and we have a for loop where we iterate over the key value pairs, and if the value is even, we remove that key value pair from the dictionary. Let's remember real quick the error that we got when we ran the code. Right here we can see it. It is a runtime error, dictionary change size during iteration. Okay, so how can we solve this? Well, we can create a clone of the dictionary right here. We just need to add one word. It is literally one word. We are calling the method copy right here on the dictionary. This creates a copy of the dictionary that we passed as an argument. It is an independent copy, like a clone. And after we have that copy, we can get all its key value pairs for the iterations. Then for each iteration, we are going to check if the value is even. And this is the key, We are going to remove the key value pair from the original dictionary that we got as an argument. We are using the copy only to iterate over the key value pairs, but we are not using that copy to mutate the object. When we delete the key value pair, we are deleting it from the original dictionary. So that way we can mutate the dictionary and still use it in the for loop. This is really, really awesome, right? Let's print the dictionary after calling the function so we can see the changes. Let's save the file and run the code. Now you can see that we don't have an error anymore. We only have A1 and C3, the key value pairs with odd values. And that is how you can solve this bug. You can just make a copy of the dictionary for the loop and then mutate the dictionary using those values. Awesome work! Now you know how cloning works and how you can use it. Most data types will have a way to create a clone. That is an independent copy of the original object. You can work with it and modify it, and the original object will not be affected. Great, so let's start writing our move class. This is going to be our first class for the tic-tac-toe project, and we are going to represent a move in the game. How are we going to do that? Let's start by defining our move class. With the class header, right here we have the class keyword, the name of the class, and the colon, just like you learned. Each move is going to have a particular value. Why? Each particular cell in the board has a number that identifies it from 1 to 9. So that is what we're going to call the value of the move. So to create a move, we are going to specify the value, and for that we need to define the init method. We add value as a parameter, so we can pass it as an argument when we create an instance of move. Great, so now we have to create the instance attribute, value. Right here we are using the parameter, and let's make this attribute non-public. We're going to make it non-public right here, but we are going to create a property for this attribute. Why? Because we want to make it read-only. We don't want to modify the value after the move has been created. Awesome, so now we can create move objects with a particular value. But a very helpful method that we should also implement is a method that will return true if the move is valid and false if the move is not valid. This will be very helpful when we take user input to check if the value that was entered by the user is within the valid range of values that we can accept. So right here, what are we going to do? We are going to return either true or false. But what are we going to check? We're going to check if the value is less than or equal to 9 and greater than or equal to 1. This is the condition that we are going to check. If this is true, then the value true will be returned. And if this is false, false will be returned. Great, we have our method right here implemented, and now we are going to implement two methods that will be extremely helpful for this project. There are several ways of implementing this particular functionality. We will see, I will mention some of these alternatives, but we will implement them in this case as methods. Remember that in our board we have 9 possible options, from 1 to 9. The user is going to enter a value from 1 to 9, but that value doesn't really tell us anything about the row and the column where the move is located. The row and the column that the user chose for the move. So we're going to have to calculate that somehow, and that is exactly what we are going to do in these methods, getRow and getColumn. Let's define them right here, and then we are going to implement them. GetRow and getColumn. We can use the pass statement to just fill the body of an empty method until we implement it, like we did right here. So let's start implementing getRow. We want to get the corresponding row of the move based on its value. So if we take a closer look at the board, we can see that the values 1, 2, and 3 all belong to row number 0. If we think of it like a list in Python that starts counting from 0 for the first item. If the value is either 1, 2, or 3, we could check this using the in operator and checking if the value is in this tuple that contains the values 1, 2, and 3. If that is true, if it's either one of those values, then we will return 0, because this represents the first row on the board, or the top row. Then if we go to the second row, we will see that the values 4, 5, and 6 belong to the second row. So we check if the value is either 4, 5, or 6. Then we return 1. This is the second row. If the value is in this sequence, so if it's either 4, 5, or 6, then this condition will be true and we will return this value. Great, so that is for the second row, and we have a third row, but for that we just need to return 2 because it is the only option left. If it's not 1, 2, or 3, it's not 4, 5, or 6, then it has to be either 7, 8, or 9. So that means that the move refers to the third row. Awesome! So now we have the basic structure of how we're going to get the row that corresponds to the move object that we are creating. We get the row, but we also need the column. So let's implement this method that we have right here. This time, the logic is exactly the same, but we are going to take the values per column. If you see right here the structure of the board, you can see that the numbers that belong to the first column are 1, 4, and 7. So let's say, if the value is in 1, 4, or 7, if it's in this tuple, if it's either one of these values, then we return 0, because this would be the first column. We should do the same for the second column. Now the values will be 2, 5, and 8. You can check the structure of the board again to confirm that these values are indeed present on the second column of the board. And by default, if these conditions are false, then that means that the value belongs to the third column. So we return the number 2. Remember that we are starting to count from 0 instead of 1, because this is going to be very helpful when we represent the board as a nested list. We're going to have an outer list, and each row is going to be a list. So we can use these indices to access the different rows and columns of the list. You will see how this works when we start implementing the board class. But trust me, this will be very helpful. PyCharm is letting us know that PEP8, the Python style guide, recommends adding 2 spaces before an inline comment. So this is a really nice tip that will help you keep your code clean and more readable. So now we have our move class implemented. Let's go over the code of this class quickly before we move on to our player class. We have the class header right here with the class keyword, the name of the class, move, and a colon. The colon is very important. We have a blank line, and after that we have the init method. We take value as an argument when we create an instance, and we assign that to an instance attribute that is non-public. We create a property for that attribute because we want it to be a read-only property. We can only access the value of the move, but we cannot change it because we are not creating a setter for this property. So we are sort of like protecting the value. Then we find the isValid method. This method is going to return true if the value of the move is valid, or if it's between 1 and 9 inclusive, if it's one of the cells on the board. And right here we have the 2 methods that are going to get us the row and the column of the move. Each time we call these methods, we're going to get the value that corresponds to the row and the column of the cell that the user selected for that move. Awesome! This is our move class. So take a look at this code carefully, go over it if you need to one more time. When you're ready, move on to the next video, and I will see you there. Great, now we have our move class. So before we start writing our player class, let's test how the move class works and that it works correctly. So let's start by creating a move instance. Right here, below the class definition, right here we are not indenting the code. This is right here at the same level as the class keyword because it is not part of the class. It's part of the main program, and we are creating a move instance. And right here we see a warning that is telling us that we need to pass something as an argument. Remember that. Let me draw a diagram right here real quick. This is our board, and these numbers represent the positions on the board. The user will enter a particular value that corresponds to this position from 1 to 9. We need to pass one of those values to create a move. So let's say that we pass a value from the first row. We need to test all the rows and all the columns, so let's test this with the number 1. We're going to create a move for position 1. Great, so after we have the move, we can check if the move has a particular value attribute, or in this case, a property. Okay, so we can print it, and if we run the code right here, we see the value 1, which is the value that we assigned for this move. Great. Now let's test if the isValid method works as we expected. It should return true if the value is between 1 and 9 inclusive. We have 5 different possibilities that we should test. We should test a number that is less than 1. We should test a number that is greater than 9. We should also test these boundaries of the interval, the bounds of the interval 1 and 9, and we can choose a value in that range. And that will basically test the method appropriately. So let's do that. Let me zoom in so you can see this better. We have the move, and then we are going to call the method isValid. Okay? This method doesn't take any arguments, it just takes self, so we just need to call it with empty parentheses. And we know that the value of the move is 1, so it should be valid, the value should be true. Right here we see true, which is what we expected. Now if we pass the value 2, for example, a value in the valid range, we also see true. Let's test another value in that range. This is true. Now if we test 9, which is a boundary case, for the interval, we also see true. That is what we expected. Now let's test this with a number that is less than 1. For example, 0. That is no longer a valid value, so we should get false right here. And this is false like we expected. And we should also test this with a number that is greater than 9, for example 10. And we see false. The move is no longer valid, so the method is working like we expected. Awesome. We tested this method, so now let's test getRow and getColumn. For getRow, we need to check if the correct value is returned for a number on the first row, on the second row, and on the third row. So let's do that. Let's change this to an actual valid value. And right here, we are going to get the row, okay, of this move. We know that the value is 2. So this value corresponds to this position right here. It is on the first row. Right here, let me add this row 1, row 2, and row 3. Okay? And right here, we can add this to the diagram, column 1, column 2, and column 3, right here. So we can have like a visual guide or representation of the board. Let's run the code. This is row 1, row 2, and row 3. But what is happening? Why are we getting the value 0? We set it up like this to return 0 for the first row, then return 1, and then return 2, because we are going to work with lists. And lists actually have indices. We're going to work with these indices in our code. So this is actually row 0. Then we go to row 1 and finally row 2. The same with columns. 0, 1, and 2. So intuitively we might think of them as the first row, second row, third row. But when we represent their indices, we will start to count from 0. Now that this is clear, let's test a position at a different row, at row 1, the second row. Let's say the number 6, which is this position right here. Let me run the code, and we see the value 1 now, which is correct, row 1, if we start to count from 0. And let's also test a different row, the third row, and we see the value 2, which is correct. So this method is working like we expected. Awesome. Now let's test getColumn. We should also test a number in each one of these columns, and we should get the numbers. For example, 4. Let's test number 4. This is on the row 1, but it is on column 0, on the first column, right here, this position. So we should get the number 0 because right here we are getting the column of the position, which is 0 in this case, and that is correct right here, column 0. Then let's see what happens if we try to get the column of the value 8. Right here, if we run the code, we see the value 1, and that is correct, column 1. And finally, let's check what happens with the value 3, which is 2 in this case, and that is correct. It is right here at column 2 if we start to count from 0. Awesome! We tested all the methods in the move class, and this is basically how you can test your classes quickly in your program. You can use different test cases. For example, when you have a range of values, you can test values that are not in the range, values that are in the range, and the boundaries of that range or of that interval. Those are typically the test cases that we use. And if you have a conditional, you should test all the branches at least once, okay? Awesome! So now let's move on to the player class. When you're ready, go to the next video. Welcome back. Now we're going to start writing our player class. We have the move class, and now we have to create a new file for the player class. We're going to keep our classes on separate files. So right here, you can see that I have a main file where I wrote the move class. What I'm going to do is I'm going to refactor that file, and I'm going to rename the file to move. And I say refactor, and you can see that the file was refactored correctly. Now we have a move file. So we're going to create a new Python file. And we're going to assign the name player. So we have a new blank file. Great, so let's start writing our player class. First of all, we write the class header, the class keyword, and the name of the class. In the game, we are going to have two types of players. A human player, which is going to be interacting with the game through user input, and a computer player that is going to select a random position in the board to make the move. So we have to define or create a way in our class to identify if the player is the human player or the computer player. So how are we going to do that? We are going to do that in init. When we create the instance, we're going to specify if the player is human or not. By default, the player will be a human player. That is why right here, I am assigning a default value for this parameter. So we are going to assign this to the instance attribute is human, right here. Each player will have an associated marker, a particular symbol that we're going to use during the game, like X and O, which is a traditional pair of symbols that we use for tic-tac-toe. How can we know which marker to assign? Well, we check if the player is the human player or not. And what do we say? We say, if the player is the human player, we are going to assign a particular value as the marker. We're going to assign the string X. So when the human player makes a move, we're going to have an X on the board. But if the player that we are creating is not the human player, if it is the computer player, then we are going to assign O as the marker. This is an O, this is not a 0. In PyCharm, O looks like this. Awesome, so we know what marker each type of player will have. But let's say that we want to use the symbol somewhere in our class, and we have to use it multiple times, which is something that could occur if we want to extend the functionality of our program. How can we make our code easier to maintain? Let's say that we want to change these values, and we've been using them at several different lines in our code. What are we going to do? We are going to create a class constant or a class attribute that will serve as a constant that we can refer to in our class. We say player marker and computer marker, which is O. We're kind of like creating a central point where we can update these values. And then we will refer to these attributes in our code. And if we make any updates, they will be updated automatically anywhere we use them. So right here, instead of writing X, like we have right here, we are referring to the player marker attribute of the player class. So if I update this, for example, to C, or to a different character, this will be updated automatically and anywhere in our code where I use it. Now let's say computer marker, And this will work exactly the same. We're just thinking ahead and thinking about how our program might grow in complexity and how we can make it easier to maintain. Awesome, now we have our init method, which runs when we create a player instance. We're going to define some properties. For example, we will need to access the isHuman attribute, but we don't want it to be modified. So we're going to make it read-only, and we're going to create a getter for this attribute using the add property decorator. We're going to do the same with marker, because these are attributes that exist, but we don't want them to be modified. We only want to access their values. Like this. The main functionality that we have to implement for a player is to make a move. So we're going to define a method that is going to return the move that the player selects. We're going to have like user interaction with the input function, depending on the type of player. Let's see. This method will be getMove. And what are we going to do in this method? We are going to check if the player is a human player. If the player is the human player, then we want to do something very specific, which is interacting with the user to get the input. We're going to use this method like the main central point that is going to decide what type of move we are going to get. If the player is the human player or if the player is the computer player, like this. Returns self.getComputerMove, like this. We haven't defined these methods yet, so this is why we are getting these warnings on resolved attribute reference. But we will do that in just a second, so don't worry. Notice that we are returning right here the values returned by these method calls. This is very important. If we don't write this return statement, then this method getMove will not return a value. If we just write this method will return none automatically. Because we are not returning a value explicitly, we have to write return. These methods will return the move, and this statement will return that move from the method. So let's start defining our getHumanMove method. This is the method that will be called if the player is a human player. So we need some user interaction, and let's start working with the input function. We're going to use an infinite loop right here, but it's not really going to be infinite. We say while true, so this will run indefinitely until something very specific happens. We're going to ask for user input, and we're going to store it in the variable user input. We're going to take an integer. We're going to ask for the number of the cell that the user wants to choose as the move, from 1 to 9. So right here we write the input function, and we're going to convert the input to an integer. Please enter your move. We can also add like a visual cue, like saying from 1 to 9, or you can customize this message to your liking. It's totally okay to customize this to make this game your own. Great. So now we have user input, and once we have the user input, we need to create a move object. Remember that we defined the move class right here in our previous video. So we're going to create right now a move object from that user input. The move class has an init method that takes a value. So when we create a move object, we need to take the value from 1 to 9 to create the move. And that is what we are passing right here. The value from 1 to 9 to create that move object. But right here we see a warning, unresolved reference move. And we can solve that very easily with an import statement. This file, the player file, doesn't have access to the move class because it is in another file. We can import the particular class. Instead of import right here, I'm going to write from move import move. So we can use the name of the class directly, like we do right here, move. Great. You can see that the warning has disappeared. Awesome, we have our move. After we have the move, it's very, very important to check if the move is valid, because we don't want to work with an invalid move. For example, if the user enters the number 15 or 25 or -5, We don't want to work with that move. That will generate a lot of errors in our code. So, first of all, we have to check if it's valid. And for that, we call the isValid method of the move object. This is a very nice example of how we can work with objects of different types and use their methods and use the structure that we have been defining in our classes. When we call this method, we will get true or false, depending on whether the move is valid or not. Remember this method in the move class. This is the method that we are calling isValid. This will return true if the value is between 1 and 9 inclusive. Okay, so now we get this value, and if that is true, then we break out of the loop. We got the user input, we created our move, and now it's time to move on and return that value. So we use break. Break is just like a stop sign that you see on the streets that immediately stops the while loop. You can think of it like a stop sign that immediately stops the loop. And it continues with the normal flow of execution of the program after the loop. But if this is not the case, if the move is not valid, if, for example, the user entered 15 and that is not a valid number, we should print a message. Please enter an integer between 1 and 9. Okay? Notice that right here in this else clause, we are not writing a break statement. So we're just going to print the message and the loop will continue. It will start again asking for user input. That is what we want. We want to ask for user input until the user enters a valid value. We will not accept the value until it is valid. Awesome, so after we break out of the loop, we will jump to this line, return move. We will return that move object that we created from the user input. And that is the implementation of getHumanMove. Now we are handling the case where the player is a human player. We will get the move through user input. So now we have to implement what happens when the player is actually the computer player. When we have the computer player, things are a little bit different because now we cannot have any user input. We have to select a number from 1 to 9 randomly. And that is exactly what we will do right here. getComputerMove. Awesome. What are we going to get? We are going to get a random choice for the computer. We are going to do that by using the choice function from the random module. And that's right, that is a module, so we have to import it. Otherwise, we will get this error, unresolved reference random. So we go to the very top of our file, and right here we import the random module. Usually, it is recommended in Python to first import the built-in modules, like random or any other type of built-in and more general module first, and then import more specific modules or modules that you have created for the project. Okay, so now the error is gone because now we've imported random and the program has access to these functions. Now we can use the choice function, we can call it, and what are we going to pass as the argument? We're going to select a random value, but we have to specify a particular interval or range of values to make that choice. And what is the valid range of values? Well, from 1 to 10. Okay, this is the valid range of values. We can convert this sequence to a list as well. We can take this sequence, we can also write just a list from 1 to 9 manually because we only have 9 values, but I think that this is a little bit more compact. So we're creating a sequence from 1 to 9 and then we are converting it to a list and we are selecting a value randomly from that list from 1 to 9. After we have that random value, we have to create the move. We're going to do exactly the same as we did for the human move right here. We create the move, we pass a particular value for the move, which is in this case the random choice, and we assign it to the move variable. After that, we just need to print a message to let the user know what value was selected randomly for the computer. We print computer move from 1 to 9, and we need to print the value of the move. Remember that right here, move is not an integer. It is an object that we created from the move class. We got the random choice, which was an integer, and we passed it as an argument to the move class to create an object. And now right here we have an object that we can use in our code. And that object has a value attribute. Okay, so we can use that and that will give us the value of the move. And finally, we have to return the move because we are going to work with it in our code later on. Great! Now we have implemented all the main functionality of the player class. Right here, PyCharm is asking us to add another blank line between the import statements that we have right here and the class definition. Great, so let's go through this code one more time quickly to go over the details before we move on to the board class. In the next video, we will start implementing the board class. So let's review our player class. Right here, we define the class with two class attributes. Okay, that is why we are writing them in uppercase letters. We want to tell other developers that these values should, in practice, be like constants. They should not be changed. So we have x and o, and right here we have the init method with an isHuman parameter, which by default is true. So right here, we are creating an instance attribute isHuman, and based on whether the player is human or not, we are also assigning a value for a marker attribute. These attributes are non-public, so we are creating properties for them so we can access their values, but we don't want to modify them, so we don't create setters. Right here, we are defining a getMove method. This method returns the move for that particular player. In this method in particular, we are handling the two different cases for the two types of players. We are saying if the player is a human player, then we are going to get a human move, which is going to be the result of user input. But if the player is a computer player, then we are going to get the computer move, which is going to be a random selection from 1 to 9. In the getHumanMove method, we have an infinite loop right here, which is going to stop when the player enters a valid move. So right here, we are asking the user to enter a value between 1 and 9, which is the cell that he or she wants to select for the move. We are converting that to an integer, and we are creating a move from that value. If the move is valid, we break out of the loop, and we return the move object. But if the move is not valid, we say please enter an integer between 1 and 9, and then we start again until the user enters a valid input. And finally, right here we have the getComputerMove method, which is going to select a random value in a range from 1 to 9 inclusive. This 10 right here, remember that range doesn't include this value, so we are getting a sequence that goes from 1 up to 9 inclusive. So that random choice is going to be used to create a move object. And we take that object and we get the value to present it to the user. And then we return that move. You could add the space right here, or you could omit it, because this, adding a comma, will already add a space between the string and the next one. So these are both valid alternatives. Great, so we have our player class. Take a few minutes to go over this code, make sure that you understand it, and then move on to the next video. I will see you there. Now we have our move class and our player class. That's great. But now we have to test our player class to make sure that it works like we expected. We're going to do something very similar to what we did with the move class. We're going to call the methods and test them with different inputs. Okay, so first of all, we need to create a player instance. We will do this right here below, player, and by default, since we assigned the value true to the parameter isHuman, the player will be a human player. So we can start by testing the functionality of the human player. We can add a comment right here, human player. Awesome, so once we have a human player, what can we do with it? Well, we can test if the instance has these two instance attributes, isHuman and marker, which we defined right here as properties, so we can get the values of these attributes. Let's print player.isHuman, this should be true, and player.marker. we should check that the marker is an X, which is the marker that we selected for human players. If we run the code right here, we see this as the output. We see exactly what we expected. Player is human, is true. The attribute is true because the player is a human player, and the marker is X, which is the marker that we wanted to assign to the player in the tic-tac-toe game. So these two properties are working correctly. So now let's move on to testing the methods of the class. First, we find the method getMove. Okay, getMove should return a move object for the human player. And this will indirectly test the getHumanMove method, which should ask the user to enter a move and continue asking while the input is invalid, and if it is valid, it should return that move object with the value that the user entered. So let's do that. We say player and we call getMove. This method doesn't take any arguments, so we just call it with empty parentheses. If we save the file and we run the code, we see this. Please enter your move from 1 to 9. Remember the structure of the board? Each number marks a particular position on the board from 1 to 9, so let's say that we choose the value 2. And we don't see any errors, everything ran correctly. But to be more specific in the output and to check if the move that we get was actually the move that we expected with the value 2, we can assign the value returned by this method call to a variable, and then print the value of the object, of the move object, like this. Let's run the file again, and we see the prompt. Please enter your move 1 through 9. Let's enter 2. And now we see the value 2, because we're printing that value, the value attribute of the object that we just created. In this case, the value is a property. So that is great. We are creating a move object with this method and we are returning it. And we are creating it by asking for user input. So the methods are working like we expected, at least the getHumanMove method and the getMove method. But there is also another case that we need to test for getMove for the human player. What happens if the player, the user, enters an invalid input? That is something that we should test as well to check if it works correctly. For example, let's say that I enter the value 0. This is not a valid value for the board, so let's click enter and see what happens. We see please enter an integer between 1 and 9. And then we see the prompt again, so we can enter a different value. Let's enter an invalid value again. And we see that the process continues. This is correct. Let's enter a bound of the interval, for example 1, and see how it works. And we see 1, which is correct. And that is awesome. If we enter invalid input, the program will handle it nicely and the process will not stop, but it will continue and it will tell the user what has to be done. Great. If we run the code again and we try the other bound of the interval 9, we see the value 9. So the code is working correctly, like we expected. Okay, so now what we have to do is to test the other branch of this conditional, the other part of this conditional, where we get the computer's move. But for that, we have to create a different type of player. We have to pass the value false right here to create a computer player. If we pass the value false for is human, we will have a different marker, the computer marker, which is an O. And we will assign it to the marker attribute. Great, so now we have our computer player, and we have to get a move, but to avoid any confusions, we can change the name of this variable to computer. And then we're going to call the getMove method. Okay, so we get the move, and then we're going to print the value. This value is a random value selected from the range of valid values. And we should also see the output of the computer move printed in the console. So this should not be necessary. Okay, so we can delete it, at least for the computer player. If we save the file and we run the code, we see this. Computer move from 1 to 9, it was 2. So that was the value that was randomly selected for the computer move. Now if we run the code again, we see a different value, 8. Then we see 5. So you can see that this is actually a value that we are selecting randomly. 1 is being included in the sequence because we got it right here randomly. And then 6, 5, and you can continue and you will get different random values. So this method is working correctly as well. We're getting values in that range, and we are also getting the move object right here. If we want to check if this is actually a move object, the type of the object, then we could try printing the object. And we can see the output. We can see that this is a move object. So this is an object of type move at this particular memory location. And this confirms that the method is returning a move object, like we expected with this return statement. Great, so now we tested all the methods in the player class. And we checked that they are working correctly. We also have the 2 instance attributes that we need. When you're ready, go to the next video where we will start implementing our board class. If you want, you can take a few minutes to go over this code again and make sure that you understand move and player, because we will need them when we start implementing board and the main game logic. So when you're ready, I'll see you there. Okay, so now we have our move class and our player class. So let's start writing our board class. To do that, we just create a new Python file right here. And we're going to name this board. Initially, it will be blank, and let me zoom in so you can see this better. So we're going to start defining our board class. For that, we need the class header first, of course. And we have our colon at the end of the header. That is very important. What do we need to have as our initial board? Well, we need to have an initially empty structure. When the game starts, the board is empty. So we need to reflect that in our representation of the board. How are we going to do this? Well, we are going to create an attribute called GameBoard. It's going to have nested lists. It's going to be a list that contains lists. Each one of these lists is going to represent a row on the board, a row. You will see what I mean in just a second. Just picture this as a board. And within each row, we're going to have 3 columns. So we're going to have 3 elements. And the elements are going to denote what type of value we have at that particular row and column. This is our first row, this is our second row, and this is our third row. But this is not really looking like a tic-tac-toe game board, right? How can we help ourselves visualize this even better? Well, we can just press enter right here. And you can see how this is starting to look like a tic-tac-toe board. We have our first row, our second row, and our third row. And right here we have the different columns of the game. But of course, we're not going to show this to the user. It's just like an internal representation that we will use. This will be our initial representation when we create a board instance. So that is why I'm writing this in the init method, because it will be created automatically when we create an instance. It will also be helpful to define a class attribute called empty cell. This is like a constant that we can use to add more context to our code, to make our code more readable, where we assign the value 0 as the value that we will use to denote an empty cell on the board. This denotes an empty cell. So we know that this is empty, and this is what we will use to check if a cell is empty or not. You could also write this right here instead of the 0. Okay, so in this video, we are also going to implement a method that is going to print the board. This is very, very important. We are going to print a board that shows the positions to the user first, so the user knows what value he or she has to enter from 1 to 9 and what position that value corresponds to. And we are also going to have a method that is going to print the current state of the board. If the cell is empty, it will be empty, but if the cell has an X or an O, that symbol will be printed as well. Okay, so let's start defining our print board method. This method will not take any arguments, so we just write self. The first thing that we will do when we print the board will be showing a board with the positions. So we could name this method, for example, print board with positions. You can customize the name of this method to what you think is more convenient. In this case, I am going to name it print board with positions. And trust me, this will be very helpful once we've implemented this. Right here we see positions, because this is a message that will help the user know what we are referring to with the board. And this character right here adds a new line, so we separate it from previous messages, and that will help with the presentation. We can start defining this method to remove this error or wording that we have right here. It is very quick, a very quick implementation. It's actually just one line, so we can implement it right now. What are we going to print? Well, we are going to print a board like the one that I showed you on a previous video with the numbers and the spaces and the bars and exactly what the board will look like when we print it in the game. Like this. We write the first row, then we write a new line character, so this will be separated from this part of the string by a new line, then we print another new line character and the third row right here. Awesome, so we have our initial board class. Let's start testing what this looks like, so you have a clearer view of what we're trying to accomplish with this code. We're creating right here a board instance to test this, so I'm going to call print board. Okay, so let's run this file, and right here we see this positions, and we see the board with the corresponding positions 1 through 9. So the user has a clear idea of what number he or she has to enter to put the marker at that particular position on the board. Awesome. Let's comment this out for a moment because we will continue testing our board, but we have to finish the implementation of print board. After we print the board with the positions, this is going to be like a fixed value, so that is why we are printing a string with fixed values. We don't have any variables right here. But what we do have to do is to print the current state of the board, like this. We are going to print the board row by row and column by column. Let's see how we can do this. For each row in the board representation, remember that right here we have 3 lists, and we have a main list right here, so we have nested lists. When we write this in a for loop, we're iterating over each element in the list, the main, the outer list. So we're going to have 3 iterations, 1 per row, 1 per element in the outer list, and the elements are the nested lists that we have right here. After we have that set up for the for loop, we can start printing the structure of the board. Every row starts with a vertical bar, so we should print that as the first character, and then, since we want to continue printing on the same row, on the same line, we write this as the second parameter for print. We pass this value as the second parameter and an empty string. We want to continue on the same line, but we don't want to separate the next character. After we have that initial character, we have to start printing the columns. Each one of these values represents either an empty cell or a cell that has an X or an O, and those values are the ones that we have to print, column by column. So we say, for each column in the row, we are writing nested loops right here. We are taking each row, each one of these lists, and then for each list, we are taking each one of its elements, right here with the nested loop. So we say, for each column in the row, if the column is empty, so if the value at the column is equal to 0, this right here represents the value 0, because we are writing this right here. If the value is 0 at that position, then what are we going to do? We just need to print an empty cell. And we can do this by writing 3 spaces, 1, 2, 3, followed by our vertical bar. And then we write end and an empty string. Why are we writing this right here instead of 0, you may ask? I'm sure this is a question that you must have on your mind. I think that adding this right here adds a little bit of context or meaning to our code to make it more readable. If instead of this we write 0, it doesn't really help you understand that we are trying to check if the column is empty, right? So by adding this, we're saying if the column matches the value that we assigned for an empty cell, then do this. So that is why I'm defining this constant in the class. Great, so we are handling empty cells. And now we have to do something if the cell is not empty. So what are we going to do? Well, we are going to work with an F string. F strings are really awesome because they help us replace the values of variables and expressions in our strings in a very compact way and very readable way. We just need to write curly braces right here. And within the curly braces, we write the name of the variable that we want to replace. And when we print the string, the value will be there. We also need to add a space before and a space after the character to make sure that the elements are aligned on the board. And right here after the space, we write the vertical bar. Remember that we're creating the structure for the board. And we also need to add end right here because we want to continue printing the remaining columns until we reach the end of the row. Great, so after we print the row, we want to start a new line. We can do this in Python by just writing print. That will add a new line character to the output and we will start a new line because we completed the row. And after we printed all the rows, we also want to print a new line. Trust me, I tested this and this will really help us present the output nicely to the user because we are creating like a division between the board and what comes next in the output. Awesome. Let's test how this works in the output. I'm sure that you must be really curious to see this in action and to run this in your device. So let's uncomment this code and let's print the board. Okay, so let's run the code right here. And we see this, positions 1, 2, 3, 4, 5, 6. We see all the positions. And we also see right here below a board with empty cells, of course, because the board is initially empty. We only have spaces. But what happens if right here, just for testing purposes, we change these values to, for example, X, O, X, X, and O right here. For example, something like this. Not all the cells are empty now, so we should see these symbols right here being replaced. And we see exactly that. Let me make this a little bit bigger so you can see we see the positions. This is a fixed string that we are printing, and right here we are printing the current state of the board, which is the state that we defined right here initially, game board. So we are replacing the values correctly and we have a correct alignment of the vertical bars for the board. Great, so this is the implementation of print board and we tested that our code works correctly. Right here we should bring this back to the original state with empty cells. This attribute, this value will be updated as we run the game. So when we print the updated state of the board, the values will be replaced, the X and the O's. Let me delete this test code and let's move on to the next video. Please feel free to take a few minutes to go over the code again and make sure that you understand how it works because in the next video we will be implementing additional functionality for the board. So when you're ready, I will see you there. Welcome back. Now we will implement a method to submit a move to the board. If we go to the last method of the class, we can start defining our new method. We will name this method submitMove right here. This method will take two parameters, the player and the move. And move is a move object. To submit a move to the board, we will need to know the row and the column of the move. Because right here, we are working with nested lists. So we need to get the index of the row to determine which one of these lists we are going to modify. And we also need the index of the column to determine once we've selected the list, which one of the elements in that list will be modified. These are the row and the column, so we need both of them. Right here, we are going to assign them to variables to improve the readability of the code. You will see why in just a moment. Row and column. You could also name this col if you want to abbreviate the word. Okay, get column. We get both of them, and then first we want to check if that particular position was already taken by another character, if it was not empty. So we can do that by getting the value that is currently at that row and at that column. You can see that I'm using right here 2 indices instead of 1. This is because we are working with nested lists. So the first index is selecting the list that we want to access. This is the row. And the second index is selecting the column. Because once we selected the list, let's say that this was the list selected, we need to get the index of the element. It could be 0, 1, or 2, depending on the position selected in the move. Okay? So we get the value. And we say, if the value is the value that we assigned or used to represent an empty cell, then that means that we can submit the move and it is valid, there are no conflicts or anything of the sort. So, what can we do? We can do this right here. We take that particular position on the board, the row and the column, and we assign the player's marker to that position, to that particular row and column in the game board. We are replacing the value 0 that previously represented an empty cell. That is if the cell was empty, but if it wasn't empty and this condition was false, then what can we do? We can print a message to let the user know that this position is already taken. Please enter another one. In this case, we're going to make the player lose the turn if he or she enters a position that was already taken. The same will happen with the computer. If the computer selects a position that was already taken, the computer will lose the turn. Okay? Awesome. So we have the submit move method. Let's test this to see how it works. Let's see that it works correctly. We create a board instance right here. And then what do we want to do with the board? We are going to submit a move. For testing purposes, we will create a move object with the value 5. And we will also create a player object, a player instance right here. But we see errors because we don't have access to these classes in our module, in our file right here. We can solve that easily with an import statement. From move, import move, and from player, import player. You can also change the order. That is completely fine, okay? And now we see that the warnings are gone. So what are we going to do? We're going to submit a move. First, we need the player, and then we need the move. But to check if the move was successfully submitted, we are going to print the board before we submit the move, and we are going to print the board after we submit the move. So let's save the file and run the code and see how this works. Right here, we see the output of the first line, print board. We are printing the positions to remind the user what integer represents each position on the board. And right here, we are printing an empty board, which is what we expected initially. Then we submit the move. The move is position 5 is to place a marker at position 5. So this marker, the player's marker, should be at position 5. The player's marker is an X, so we should see an X at position 5. And that is exactly what we see right here. This is the output of this line, print board. We see the values from 1 to 9, and right here we see the updated board. The number 5 represents this position on the board. So right here we see an X. The board was successfully updated. And our method is working correctly like we expected. So this is awesome. Now we have our submit move method completed. Since we are not going to need necessarily these import statements, we can just delete them and delete the code that we use to test this method. Okay? So we have the implementation. and we can continue working on our board class. So we'll see you in the next video. Take a moment to go over this code and make sure that you understand how the submit move method was implemented. Now let's implement the methods that we will need to check if the game is over, if one of the players won, or if there is a tie. Let's implement this. If we go to the bottom of our class, we can define this new method. Check is game over. Okay? We can also have a situation where there is a tie, but we will handle this in a different method. We are going to take the player as an argument, and we are going to take the last move that was submitted as the argument. Why? Because when a player submits a move to the board, we're going to check this automatically. We're going to check if the game is over because the last move submitted by a player made the player win the game. We will take the last move and we will check the row, the column, the diagonal, and the anti-diagonal. And we will return true if either one of those cases is true. In that case, we have a game over. The player won the game. And if that is not the case, we will return false. So, how are we going to do this? We're going to write a multi-line condition. And this condition will rely on the results of several checks or several method calls that we will make. We're going to define a method called checkRow. That method is going to take the player and the last move as the argument. That method will return true or false. But we want to check if this condition is true or if either one of the next conditions are true. Or if self.checkColumn, in this method we are going to check if the column is full with the player's marker. Or if self.checkDiagonal, we're going to check the diagonal. In this case, we're only going to take the player because we don't need the last move. The diagonal is only one sequence of values and we don't really need the move. We only need to check those 3 values that are in the diagonal. And we are also going to check the anti-diagonal. Okay, so we have these conditions. So everything is correct. We only need to define these methods and what they are going to do. Why are we using the OR operator? Well, because we want to return true if either one of these conditions or of these method calls return true. If either one of them returns true, then we return true immediately. But if they are all false, then we will return false. So that is why we are using OR. Because with OR, if either one of the values is true, the result is true. Awesome, so let's start implementing these smaller methods. checkRow. This method takes the player and the last move as an argument, because we need to know the row of the last move to check that row. How are we going to check this? First, we need to get the row index. I'm calling this row index to be more descriptive. So we take the last move and we get the row. And we also want to get the actual row from the board. First, we get the index for the row. And then, once we have the index, we know what list we are referring to. Either one of these. It could be list 0, list 1, or list 2. That would be row 0, row 1, and row 2. Either one of them. We will get that index, and then, using the index, we will get the actual list that corresponds to that row. With this, okay? We're getting the row with the values, because we want to count how many times the player's marker appears on that row. If it appears 3 times, then the player won, because the row is full with his or her markers. What are we going to return? We're going to count how many times the player's marker appears on the row. We take the row with the values. This is a list. Initially, it would be 0, 0, 0, but it could be 0 or O, 0x, and this would be something like this. We will take that row and we will count how many times the player's marker appears on that row. So if the marker is, for example, X, if it is the human player, this would return, the count would return 1 because we only have one occurrence of the marker. And we want to compare this with the value 3. If the value is equal to 3, then we return true. Else, we return false. So we can write the condition right here directly next to return, and that will make our code much more concise. And there we go, we have our check row method. Awesome. The logic for the other methods is very similar. Check column. This method will take the player and the last move that was submitted. In this case, we can't use the count method because this is a method that we can use on lists. But for the columns, we are not working with actual lists. We are working with different lists right here. We have 3 lists, and for a column, we have elements on different lists. They are at the same index, but they are part of different lists. So we can't use the count method. We actually have to keep track of a counter ourselves. So we're going to create a variable. We're going to define the variable markers count. And then we also need to get the column index from the move. We take the last move and we get the column. Okay? And we assign it to the column index. After that, we need to do something 3 times. We need to get the value at row 1 at that particular index, at that particular column. Then we need to get the value at that index at row 2 and then at row 3, which are actually rows 0, 1, and 2 when we start counting from 0. Right here, we are going to have a for loop. For I in range 3, because we have 3 rows. We say, if we take the board, at index I will be 0, 1, and 2, so we are like going from row 0 to row 1 and row 2. And we take the element at that particular index. The index of the column is fixed. It is a fixed value because we're taking the values at that index of the different lists that we have, of the different rows. And if that element is equal to the marker, then we increment the count by 1. That is what we will do. And then we're going to return true if the markers count is equal to 3. Else, we're going to return false. So we write the condition right here next to return. Great, so we have our check row and our check column methods. Now we just need to implement our check diagonal and check anti-diagonal methods. For check diagonal, we don't actually need the move because there is only one diagonal. The diagonal is made of these elements that we have right here. At row 1, column 1, row 2, column 2, and row 3, column 3. If we start counting from 0, that would be 0, 0, 1, 1, and 2, 2. So we see the pattern that the index for the row is equal to the index for the column in this case, and we can use that. And that is exactly what we will do. We will also keep track of a markers count, but we will use a for loop for I in range 3. We say, if self.gameBoard at index II, remember that this will return a sequence with the values 0, 1, and 2. So initially, I will be 0, so it will be the game board at row 0 and column 0. That is this element right here. Then it will be 1, 1, which is this element right here, and then 2, 2, which is this element right here. So we will be getting the elements of the diagonal one by one. And right here, we are comparing if that element is equal to the player's marker. Okay, so we update it by incrementing it by 1 if that is the case. And then we return true if the markers count is equal to 3 and false otherwise. Let me delete this comment. And finally, we are going to check the anti-diagonal. The anti-diagonal is this one that we have right here. Instead of going to the right, instead of going like this, we're going to the left, right here. This has a particular pattern that we have to think about and we have to analyze. We start by defining the markers count, and then we're going to do exactly the same. We need 3 iterations. But to get the index for the column, we need to use a specific pattern. right here. We're using I because we want to go row by row, but to get the anti-diagonal, we need to use this right here, 2 minus I. Initially, I will be 0, so we will get the column 2. Then I will be 1, so we will get column 1, and then we will get column 0. We will go exactly like this. Column 2, column 1, column 0. And we are incrementing the value of the row, so we're going down. That is basically what we are doing right here. If that is the case, then we update the markers count. And we return true if the markers count is equal to 3 and false otherwise. Awesome, so we have these 4 methods. Right here we also see a warning because we need to take the player. That is something very, very important. We need to add this to the list of parameters because we need to get the player's marker. Okay, so now we have these 4 methods implemented and they will be very, very helpful to decide if the game is over or not, if the player won the game or not. We can also check if there has been a tie and reset the board. And these are methods that we will implement in a coming video. But in the next video, we will test this method, check is game over. We will check what happens if we win by filling a row, a column, the diagonal, or the anti-diagonal with the player's marker. So take a few moments to go over this code and then go to the next video. I will see you there and we will start testing this functionality. Great, so now that we have our methods right here defined to check if the game is over, if the human or the computer player won the round, and we also have check row, check column, check diagonal, and check anti-diagonal, we can start testing our code. So to do that, we're going to create a board instance. We should add 2 blank lines before this line, and we create a board instance. So after we have the board instance, we're going to test how the game is working so far by playing the game and checking if the game is over. We're going to fill a row, we're also going to fill a column, we're going to fill the diagonal and the anti-diagonal in different rounds. So for that, we're going to create a player instance. We just temporarily need to import the player class from the player module. And we will also need the move class from the move module. We import them like this. And right here, we're going to create those instances. Player, and we create the instance of player. We also want to get a move. And after that, we just want to test what happens when we submit a move. And then we check if the game is over. Okay, so we will submit 3 moves. That's all it takes. 3 moves is all it takes to complete a row, a column, the diagonal, or the anti-diagonal. So we will submit those 3 moves. First, we will print the board to show the initial state. Then we will submit 3 moves. So we need to call this method 3 times, submit move. And finally, after we submit the move, we are going to check if the game is over. We will call this method. And by calling the method, we will get a Boolean value, true if the game is over and false if the game is not over yet. You can see how we are slowly building up all the functionality of the game, and we're also testing how the individual methods work. Great? So we will submit 3 moves. For that, we will have to get 3 different moves right here. We're just doing this to test our code, remember. We haven't reached the phase where we implement the actual game. We are just creating these instances to check that this method works as we expected. Okay, so what move are we going to submit right here? Move 1, then move 2, and then move 3. And right here, for submit move, we also have to pass a second argument that we can check right here. First, we need to pass the player and then the move. So we're going to pass the human player that we defined right here above. Okay, player, and then the corresponding move. And right here, for check is game over, we also need to pass the player to check if the human player won the game. And we need to past the last move that was submitted. And what was the last move that was submitted? Move 3. We are submitting the moves in this order. 1, 2, and then 3. You can see it right here in the 3 method calls. The last move was move 3. So we're going to check if the player won with the move number 3. Great, so let's save the file and run our code and see how this works. Right here we see this. Please enter your move 1 through 9. To visualize the board before we actually enter the moves, we should move this line right here before the method calls to get move. So we will do exactly that and we will rerun the code. And right here you can see the different positions that we can enter for our move. We see board and then we see please enter your move. We will enter the numbers 1, 2, and 3. These are the positions for the first row. Right now we will be checking this method, check row. When we check if the game is over, if the row has been completed, the row of the last move will be this one right here when we enter the number 3. So if this row is full with the player's marker, then the player won the game. And this will be true. So the game will be over. That is what we are checking right now. So we will enter 1, 2, and 3. And we see the value true because the game is over. We filled the first row. And if we want to see this visually, we can just call print board again after we submit the 3 moves. We run the code again, we see the positions and the initial board. We enter the 3 moves, and then we see the updated state of the board. We have the first row completely filled, full of the player's marker, which is X, and right here we see true, because the game should be over after the 3rd move that we submitted right here. Great, so we are testing if check row works correctly. We know that when a row is filled, the game will stop. We can also test if this works with row 2 and row 3. So let's do that, just to double check that the code works like we expected. Now we're going to fill row number 2. So we're going to enter 4, 5, and 6. We can see that the row is full and we also see true. So the game should be over at that point. And for the 3rd row, we will enter 7, 8, and 9. 7, 8, and 9, and we see the row updated right here. So the method is working like we expected. Awesome, now let's start checking if the method check column works correctly. Now we will try to fill a column with our moves. So let's save the file and run our code again. We see the positions on the board, and now if we want to fill the column, we will have to enter 1, 4, and 7 for the first column. Right here we see the first column filled with the player's markers, and we also see the value true right here. So the game should be over. This method is returning true, which is awesome. This is exactly what we expected. Now let's also test what happens with this method if we don't fill a column after the 3rd move. We also need to check what happens if after those 3 moves we haven't filled a row or a column. So let's do that. Let's enter 1, 4. So we will have these 2 positions filled with a marker, and let's enter a different position that doesn't fill the first column. Let's enter the value 2. We see right here the value false. And that is correct because the game should not be over if the column is not full or if a row is not full. In this case, neither one of them is correct and the diagonal is not full and the anti-diagonal is not full. So we see the value false. Great, so let's test this with the 2nd column, 2, 5, and 8. You can see that right here the column is full and we see the value true. And if we test this with the 3rd column, we enter the values 3, 6, and 9. We see the 3rd column full with the markers, and we also see the value true. So this is working for all the rows and all the columns. And it's also working when we don't fill a row or a column after the 3rd move. So far, so good. Now we only have to check if this works with the diagonal and the anti-diagonal. So let's do that. The diagonal corresponds to positions 1, 5, and 9. So let's enter those values, 1, 5, and 9. And this is true. We can see this right here. So the game should be over after the third move right here because we completed the diagonal. We can also check if this works if we enter the values in a different order. For example, 9, 5, and 1. We need it to work for every single combination because it doesn't necessarily have to be from top to bottom. We can fill the board any way we want to. We fill that by entering 9, 5, and 1. And we also see that the diagonal has been filled and we see the value true. So this is working as we expected. And finally, we need to check the anti-diagonal, which is this sequence of positions, 3, 5, and 7. Okay, so if we enter 3, 5, and 7, now we see the anti-diagonal filled with the player's markers and we see that this is true, so the game should be over. Awesome! Our check is game over method is working like we expected, so we have the basic functionality of the board implemented. Awesome! In the next video, we will complete our board class. We will check if the game resulted in a tie, because right here when we check is game over, we are only checking if the player won, the human player or the computer player. But it could happen that the game ends up in a tie. So that is what we will implement in the next video. And we will also add a very short method to reset the board when we start a new round and we start with a blank board. Okay? So take a few moments to go through this code. If you want, you can continue testing it and making sure that you really understand how this works before you move on, and then I will see you in the next video to implement the tie functionality. Welcome back. Now we will complete our board class. I deleted the code that we used to test the methods, and right here we should also delete the import statements that we won't be using since we are not accessing the player or the move classes. Great, so let's go to the bottom of the class and let's start defining our check tie method, or check is tie, if the game is a tie, or if a round is a tie. You could also call this check tie to make it more concise. Great. So how are we going to check if there is a tie? If there is a tie, that means that the board is full. It is full with the human player's markers and with the computer's markers. But neither one of the rows, columns, the diagonal, or the anti-diagonal are full with the same marker. So how can we check if the board is full? We could count how many empty cells we have left. And if there are 0 empty cells left, that means that the board is full. So that is how we will implement this. We will count how many empty cells we have left. And if that number is 0, then the board is full. For each row in the game board, like this, for each row in the game board, we are going to update the counter of empty rows. We're going to take that row and we are going to call the count method to count how many times the number 0 appears on that row. Remember that rows are lists. If we go right here to our representation of a game board, you can see that each row is a list. So when we iterate over the lists for each row, we can call the count method on that list. And we can count how many times the empty cell appears, which in this case it would be value 0, but remember that we are using this to add more context to our code to make it easier to read. After we count how many empty cells we have, we just need to return true if that counter is equal to 0 and false otherwise. So we can do that very concisely with just one line. Right here we are comparing if the counter of empty cells is equal to 0. If it is, this will be true, and true will be returned. But if it's not, then this will be false. So there wasn't a tie. Awesome. Great, now we have a way to check if the game ended up in a tie. The last method that we will implement for the board class will be a method that will let us reset the board. This is the initial state of the board. Let me go right here to the top of the class, and right here we can see it. This is the initial state of the board where all the cells are empty. When the board is completely empty, when the game just starts, so that is the initial state that we want to restore. So we can just copy paste this right here if we want to, and go back right here to the body of a new method that we will define called resetBoard. You can also call this reset. And then we paste this right here. What we want to do when we call this method is to get a new game board that will be completely empty. So we can reset the current state of the board. We can remove all the markers that we added in the previous round. Great, so now we have these methods to check if there was a tie and to reset the board. In the next video, we will be testing these two methods to make sure that the tie works as we expected when the board is full with markers, but there isn't a row, column, diagonal, or anti-diagonal full with the same markers. And we will also test how to reset a board. So I will see you in the next video. Welcome back! Now in this video we have all the functionality that we need for the board class, but we will be testing these two methods, the last two methods that we defined in the previous video. Okay, so we will need to import the player class and the move class. We say from player import player and from move import move. You can see them in gray right here because we haven't used them yet, but we will do that in just a second. Right here below, we leave two blank lines and we start creating our instances. We define a board instance, we also define a player instance, and we get a move from the player like we did last time when we tested other methods. We can get the move from the player and we will have a move object. What are we going to test right here? We're going to check if we have a tie. Okay, first, so we can first print the board to check that it is empty. Just to simulate that we are getting a tie, well, we're going to use a while loop because we are not sure of how many rounds we will need, how many turns we will need to get that tie. We will do that intentionally. So we can use a while loop and we say that while it is not true that the game is a tie, right here, while board check is tie, if there isn't a tie, this value will be false. So by adding a not before that value, we continue the process. While it is not the case that there was a tie, we continue. Right here, I'm going to move this line to the while loop because we want to get repeated moves from the player. This will be the human move, and we also want to get a computer move. Okay? We're going to create another player, which is going to be the computer player, because we need to play against the computer to get a tie. We need to pass false right here, because as you might remember from our last videos, when we define the player class, right here we have a parameter that determines if the player is human or not. By default, this is true, so the player is human. But when we pass false right here, we're making the player a computer player. So we will get a move from the computer player. We will get these two moves, but we also need to submit them to the board. Okay, so we take the human player and we submit the human move. And right here, we also need to submit the move from the computer player. What move are we going to submit? The computer move. And we should also print the state of the board after we submit each move. Okay, so you can see how we are sort of like writing the main logic of the game already, making a simplified version of the logic of the game. We will implement that in a coming video. So we have this, and this while loop will stop when there is a tie. If there is a tie, this will be true. This negation, this not operator, will convert it to false, and the while loop will stop. Okay, and then we will print it's a tie. Notice that this line is not indented. It is at the same level of indentation as the while keyword, so it doesn't belong to the while loop. We will not repeat it. When the loop is completed, this line will run, and we will see this message. Okay? So let's save the file and run the code and see if we need to make any adjustments. Great, so we see the positions, we see the empty board, and please enter your move. Let's say that I choose 1. Right here, you can see my selection. My choice was to add the marker at position 1, and the computer selected the number 2 randomly, the position number 2. Right here, so we see an O. Now let's say that I choose position 3. Right here, you can see my marker at position 3, and the computer selected position number 5. So right here we can see this. We want to have a tie. So right here we should choose position number 8 to block the computer from choosing that position and completing that column. So right here we can see that I selected this position number 8. And right here before the computer selected number 3, but that position was already taken, so we see this message and the computer basically loses the turn. We can select another position, so let's say 6. Right here, the computer also selected number 2, the position was already taken. So we can say, for example, number 4. Awesome, so if we select the number 7, if we select position number 7, we will win. So let's just enter a position that is already taken, like for example, position number 1. We will continue doing this, entering position number 1 until the computer randomly selects position number 7. And you can see right here that the board is full, but neither one of the players has won the game. You can see the X, X, O. We don't have any rows or columns filled with the same marker. The diagonal is not filled with the same marker either, and the anti-diagonal is not filled with the same marker. So that stopped the loop immediately, as you can see, because the game stopped, the program stopped, and we see the message, it's a tie, the print statement that we have right here. Awesome. So this is working correctly. When we had a tie, this returned true. So this not converted it to false and the while loop stopped. We jump to the slide and we see that it is a tie. Awesome. The other method that we had to test before we actually start writing the logic of the game is reset board. We want to test if by calling this method we can reset the board to its initial state with empty cells. So we create the board, we create the player. Right here we won't need the computer player anymore. We will just need to get a move. We will get up the player's move and then we will submit it to the board like this. We also need to specify the player right here. We submit the move. We could submit 2 moves to get the board a little bit more filled with the player's markers. We submit move 1, and right here, if we copy paste this, we can submit move 2. If we print the board before we submit the moves, we will see the empty board. Then we will see the board updated with these 2 moves. And after that, we want to call the reset board method. Okay? Initially, we have an empty board. Then we submit these 2 moves, so we will see 2 markers on the board. We will print the board to see the updated state with the 2 markers, and then we will reset the board to its initial state. So it should be empty again when we print it right here. Should be empty. Initially empty, then it should have 2 markers, then we reset it, and now it should be empty. Awesome, so let's save the file and run the code and check that this works correctly. Please enter your move from 1 through 9. Let's say that I want to select positions 2 and 5. Expand this, you can see right here that we initially have an empty board. And then we have the updated board. I selected 2 and 5, which are the correct positions that you can see right here with my marker. And then after we call reset board, you can see that the board is empty again. So this is working and we are getting an empty board again without the markers that we had right here previously. We just see an empty board. So this is working and we can use that method. We can call that method to start a new round with a new board. Awesome. Now we know that all the methods in the board class are working like we expected. So we can start implementing the main logic of the game in the next video. So go over this code one more time if you need to and make sure that you understand how it works, because we will be using all of these classes to implement the main logic of the game. You should delete the code that we used to test the class and the import statements that we wrote. Those were used just temporarily to test the class. Awesome! I will see you in the next video. Awesome work! Congratulations for reaching this part of the project. We're in the final stage where we will implement the main functionality and logic of the game. So we will have a working game in just a few minutes. Right here, you can see that I have the 3 classes that we defined: move, player, and board. We have to create a new file right here, so we will do that for our main game. New Python file, and we can call this, for example, game. You could also call it tic-tac-toe. Great. So in this case, we're going to define the game as its own class. So we can have different methods that we can call. It's just a way to organize our code. But we can also implement it without defining a class. I'm just going to define the class right here, class tic-tac-toe game. Okay? This class is going to have 2 methods. One is going to be the start method and another one will be start new round. The start method is the method where we are going to write all the logic of the game, and the other method, start new round, will help us start a new round of the game. In this class, we're not going to define or customize a constructor. We're not going to have an init method. And this is a really nice example to illustrate that you don't actually need to implement an init method in all of your classes. If you don't write the init method, if you don't implement it, then you will just inherit all the attributes and methods that all objects in Python really have. So you don't really need to customize it if it's not necessary. Okay? We will start by defining our start method. When the game starts, the first thing that we want to do is to welcome the user, right? For that, we are going to print a message. I'm writing 3 print statements right here, and we will add like a little nice presentation with asterisks. I really liked how this looked when I worked on the game, so like this. Welcome to tic-tac-toe. You can customize this message or this presentation any way you like. So you can make the game your own and customize it to your liking. The first thing that we have to do is to create the instances that we will be working with, just like we did when we were testing the methods of our classes. We have board, we have player, and we have computer. Remember that to create a computer player, we pass the value false to create the instance. Now you can see right here that we have all sorts of errors, and that is because we need to import the classes that we will be working with. So we say from board, import board, and from player, import player. These are the 2 import statements that we need right now, so those are the ones that we are going to write right here at the top of our file. And we should have right here 2 blank lines before the class definition after the import statements. Great, so we have our 3 instances, our board, our player, and our computer. First, we need to show the board to the user. We need to let the user know what positions he or she can enter, and we also need to show the user that the board is initially empty. After we have that, we will have something very, very interesting. We have 2 while true loops right here. One loop nested inside another one. You will see why in just a moment. But basically, this while true loop, the outer loop, is going to let us ask the user if he or she would like to play another round or to continue playing. And this nested while loop is going to have the main logic of the game. We can write this as, for example, main game or game logic. Basically, right here, we're going to get the move, we're going to check if there was a tie or check if the game was over because someone won, and print the corresponding messages. And that is basically the logic of each one of those loops. And you will see why we have to nest them in just a moment. Okay, so just to be more concise, I'm going to remove these comments and we will start writing the nested while loop. First of all, we need to get the player's move, so we will do that like we have been doing so far when we tested the code. We call the getMove method of the human player. Remember that right here with player, we are referring to the human player. And when we write computer, we are referring to the computer player. Okay, so after we get that move, we want to submit the move. We need to specify the player and the player move. We submit the move, and after that, we want to print the state of the board because the player will definitely want to see that the marker has been added to the board. After we do that, we have to check if there has been a tie, if the game is over, or if the computer has to make a move. So we will do that. If there was a tie, what are we going to do? If there was a tie, this will be true. Check is tie will return the value true. Okay, so right here we're going to print a message. It's a tie. Try again. We can also add like these small like emojis and see how they work, how they are printed or displayed in PyCharm. And then we say, else if there wasn't a tie, then we have to check if the player won. Then we say check is game over, but we want to check if the game was over because the player won with the last move that he or she submitted. And what was the last move? Well, the player move that we have right here, the most recent move that was submitted to the board. If that is true, then the player won. And we say, awesome, you won the game. And right here we can copy paste like a confetti emoji. Else, if neither one of these conditions are true, so there wasn't a tie, and the game is not over, the player has not won the game, then we have to get the computer's move and continue playing. How can we get the computer's move? Well, we call the getMove method on the computer. We are getting a move from the computer player and we are assigning it to a variable. After that, the logic is very similar to what we did right here for the human player. It's basically the same, we're just working with the computer player. We're going to submit a move and we're going to submit the computer move. Then we are going to print the board to see that the state of the board has been updated. After we print the board, we have to check if the computer won the game. Board.check is game over. But now we want to check if the game was over because the computer won, with the last move that was submitted, the computer move, right here. If that is true, then we have to print a message. For example, oops. We can have like a little face right here and we say the computer won. Try again. And right here, we have something that we have to add after these print statements. That is a break statement. Let me zoom out right here so we can see this block of code more easily. We have a loop, a while loop, nested within another while loop. This loop, both of these loops, will run indefinitely until one of these break statements is found. When this break statement is found, the inner loop stops immediately, and it jumps to the next line of the outer loop. For example, if we have right here a print statement that says hello right here. Let me remove this blank line so we can zoom in a little bit better. If we have right here a print statement that is not part of the inner loop, right here we have the inner loop, the nested loop, and we have another line that is indented at the same level, so it belongs to the outer loop. This is the body of the outer loop. And this is the body of the inner loop. This line belongs to the outer loop. So when the break statement is found, either one of these, because there was a tie, or because the player won, or because the computer won, then this loop will stop the inner loop. And the program will jump immediately to this line right here. It will continue the outer loop. We will use the outer loop to ask the user if he or she would like to continue the game or not, to play again with a new board. So we will do exactly that. We say play again will be a variable that will determine if we have another round. We ask the user, would you like to play again? Enter X for yes and O for no. We could say and or O for no. And we're going to get the input as an uppercase letter. Because right here we are asking for an uppercase X or an uppercase O, but the user could enter these letters as lowercase characters, so we are converting that automatically to uppercase, so we can use it in a conditional. We say, if play again is equal to O, this is an O in PyCharm, If we have a 0, then we have a small dot at the center, so this would be an O. If the user entered O, that means that he or she doesn't want to continue playing. So we say, bye, come back soon. And we can add like a small waving hand. And then we will break out of the outer loop right here. We have the outer loop that is running continuously until it finds a break statement. Remember that these break statements that we have right here belong to the nested loop. These break statements will only stop this process that we have right here for the nested loop. Once that loop stops, we will go right here below, because this sequence of statements belongs to the outer loop. We go here, we ask the user if he or she would like to play again, and then if the user doesn't want to play again, we just break out of the outer loop and the process will stop. The game will stop. But if that is not the case, if the user wants to play again, then he or she will enter the letter X. And we will call a method that we still need to define that will be called start new round. And it will take the board. Okay? As an argument, we will have to define this method below. Else, if the user entered a character that is neither O nor X, then that means that the character is not valid, but we can continue the game by saying something like this. Your input was not valid, but I will assume that you want to play again. And right here we have a small light bulb. After we do that, we start a new round again. Awesome! We have our implementation of the start method right here. We print a message. We create the instances that we will need, board, player, and computer. Initially, that will be an empty board, and then we start the logic of the game. We will continue the game while the user chooses to continue playing. And while the user chooses to continue playing, we will continue this logic. We will repeat this logic. We get the player's move from user input, we submit it to the board, then we print the board. We check if it is a tie. If it is a tie, we stop the process and we ask the user if he or she would like to play again. But if it isn't a tie, if this is false, then we check if the player won the game, and the game is over. We say, awesome, you won the game. Then we break out of the loop and then we go here and we ask if the user would like to play again. But if that is not the case, if the player didn't win, then we have to get the computer's move. We get the computer's move, we submit it to the board, we print the updated board. And we check if the computer won. If the computer won the game, we print a message and we break out of this nested loop. So we ask the user, we jump right here and we ask the user if he or she would like to play again. And the user's answer will determine if the game continues. That is why we are writing nested loops right here. This outer loop determines if the whole game continues running. And this inner loop determines if the current round continues running. Okay? I think this is the best way to explain this or to describe the role or the purpose of these loops. This loop is in charge of the game logic, and this inner loop is in charge of the round, the current round that we are playing. When this loop stops, we stop the current round, and we ask the user if he or she would like to start another round. But if this loop stops, then we stop the whole game, and the process stops. Right here in the conditional, we're analyzing the user input. If the user entered O, then that means that he or she would like to stop the game and we say bye, come back soon, we break out of the outer loop. But if the user wants to continue the round, then we will call this method start new round, which will do like an initial setup for a new round. And if that is not the case, then the character was not valid, we print a message and we start a new round. Awesome, let's start defining our second method. This method will be called start new round. It will take the board as an argument. So we define this parameter right here. To start a new round, we want to present a nice message to the user. To be more friendly, not just present the empty board without any messages or confirmations. What do we want to do with the board when we start a new round? Well, we reset the board. That is the first thing that we have to do because we want to start with a blank board. We don't want to keep the markers that we had in the previous round. And then we want to print the board after resetting it. Okay, we want to print it before we actually make the move right here. Because remember that when we print the board right here initially, that method call is not part of the loop. We print it right here, but that is not part of the loop, of the outer loop. Okay? Another thing that we could do to avoid writing this line right here could be to add this line right here before the nested loop. So when we start a new round, before we actually start the round, we print the board. Okay? We would delete this line and write it right here so we don't have to write it in the method. But let's just keep it in the method because that will help us determine what we have to do when we start a new round. Awesome, so we have the basic functionality implemented and we can start playing our game. For that, we have to create a tic-tac-toe game instance right here below. Notice that we are not indenting this, so this is part of the main program. This is not part of the class. We already have our class defined right here and we have the import statements that we need. So we create the game instance and to start the game we have to call the start method. The method with the main logic of the game. So let's save the file and run the code and see how this works. We right click right here and we say run game. And we have our tic-tac-toe. So let's play. Welcome to tic-tac-toe. Positions 1 through 9. We have an empty board initially. Please enter your move. Let's say that I want to select the number 5. Right here you can see the updated board and the X, the player's marker, was added to position 5. The computer's move was 1. So right here we see the O at that position. Now let's say that I want to choose position 2. Right here you can see that I selected position 2 and we have the marker right here. We have the updated board and then the computer chose position number 9, which is this one right here. And finally, if we select the number 8, the position number 8, we fill this column with our markers and we see this message. Awesome, you won the game. We're also asked if we would like to play again. Would you like to play again? Enter X for yes or O for no. One small detail that we could fix right here is that we currently don't have a space to enter the input. So if I write, for example, the X, it will be right after the message. It's always best to add a space after this message. So if we go to the line where we ask for user input, we should add a colon and then a space. So the prompt will be right here. So that is a change that we will make, but we will continue playing just to test this and then we will run the game again to see that it was updated. Now we see that we start a new round, we see the positions and we have an empty board. So the reset board method is working correctly. Please enter your move, let's say 6, 3, and 9. Awesome, you won the game. Would you like to play again? Enter X for yes or O for no. We can enter O and we see bye, come back soon. So you can see how the nested while loops are really making the logic of the game come to life. We have the outer loop that is controlling the main game, the main logic of the game, and we have the inner loop that is controlling the main logic of the round. And it continues running while the round is alive, while the round hasn't been completed. And the outer while loop determines if the whole game continues running after we print in the board initially. Awesome, so let's run the game one more time to check that this was solved, that we have a space after that message. Let's say 1, 2, and 3. Awesome, you won the game. Would you like to play again? And right here we see the colon and the space that we added. So right here we see the prompt and we can enter our answer. We can also enter the answer in lowercase because right Here on this line, we are converting the input to an uppercase letter. So it is equivalent if we enter X. We start a new round. So the program detected that this X was equivalent to the uppercase X. Okay, because we converted the input to uppercase. Let's try this again, and now let's try entering an invalid input. When we're asked if we want to play again or not, let's just enter 1, 2, and 3. Would you like to play again? Let's enter the letter A, for example. We see your input was not valid, but I will assume that you want to play again. And we start a new round with an empty board. Awesome! Now you have your working tic-tac-toe game that we built following the principles of object-oriented programming. You use classes, methods, instances, and basically you combine everything that you've learned in the course so far. Well, great work! You completed your tic-tac-toe game. I will see you in the next section of the course.